Hello and welcome to this Cisco Press live lesson on MPLS Fundamentals. I am Luc Degene and I will be your presenter throughout this course. I will cover the basic material on MPLS so you have a thorough understanding of the architecture and functionality of MPLS, as well as the MPLS services using MPLS as a transport mechanism. By the end of this course, you should be able to understand most of the MPLS protocols and services out there. Some of the more advanced topics, such as multicast over MPLS, will not be covered. I will be focusing on the basics in order to lay a foundation of knowledge in order for you to understand, configure and troubleshoot MPLS. This live lesson is not about configuring MPLS and trying to cover all aspects of it. Rather, it is to make sure you have enough information to deploy and operate any MPLS network. I have been working with routing protocols for over 23 years and have spent the better part of that as an escalation point for all issues related to routing protocols, MPLS and multicast in the Cisco tag. I'm the author of the Cisco Press book MPLS Fundamentals. I sincerely hope to relay most of my knowledge on this topic to you throughout this course. Some practical aspects. I have divided the main MPLS topics into sub-lessons, which cover specific details of each lesson. I'll provide you with the necessary theory on that sub-lesson and, where needed, provide further information through a live demo. Enjoy! Hello and welcome to Lesson 1. In the very first lesson, I'll provide some history on MPLS and how it got started. I will also go over the great benefits of MPLS, discuss the main MPLS services and why it became so popular in such a short time. Let's have a look at the benefits of multi-protocol label switching, MPLS. So when did it start off? It really started off in 1998 as tag switching. Now tag is just another word for a label. And later on we just kept on using the name MPLS, so label switching. It's really about a technique where we no longer do an IP lookup to forward an IP packet, but we just look at a label and use that label to forward a packet. And the label lookup will happen in a special table that we will see later on. You can have one or more labels. We can just put them in a label stack and put the label stack on top of the IP packet. ATM, FrameRelay, X25, other WAN protocols were pretty popular back in those days, so pre-2000, but they were all replaced by MPLS, which became very, very popular. And one of the reasons is actually MPLS VPN Layer 3. That was the killer app. This was the app or the service that made MPLS so popular and made every service provider out there use MPLS. So what are the benefits of MPLS? Well, one thing it's not about faster forwarding of packets. It's not because we put a label on top of the packet that the lookup will happen faster than an IP lookup. So forget about this one. This one is just not true. These days we can forward IP packets or even IP and IP packets as fast as we can forward MPLS packets. The ASICs out there, the hardware forwarding, make sure these days that the IP forwarding is as fast as MPLS forwarding. A big benefit is the use of the unified network infrastructure. So basically today we can forward IP, IPv4, IPv6, all kinds of layer 2 frames like Ethernet and FrameRelay, ATM cells and so on, over a unified infrastructure. So if this network is running MPLS, it can forward all of these services. A big benefit back in those days was the better IP over ATM integration. They tried a few times to have IP integrated over ATM. None of the attempts were very successful. With MPLS it was much better, but guess what? ATM just died very quickly. So now we are just left with MPLS and no ATM. A big benefit to service providers is the BGP-free core. As we will see, in the past they had to run BGP on all of their routers. Now they will just need to run BGP on the edge routers and no longer in the core. Another benefit is the optimal traffic flow. Instead of working with virtual circuits and forwarding the traffic in a non-optimal traffic flow, if the service provider deploys MPLS, the traffic flow will always be optimal throughout the network. And then the big one, the big benefit, is really the peer-to-peer model that is used by MPLS VPN Layer 3, as we will see on the next slides. And then finally, traffic engineering or source routing is about forwarding the traffic through the network, but not on the shortest path. So what about the BGP-free core? Well, as I mentioned in the past, a service provider had to deploy BGP and make sure it was running on all of their routers so that the traffic, typically towards the internet, could be forwarded by every router in the network. But once the service provider deploys MPLS in the network, this is no longer needed. If the service provider deploys MPLS, he just needs to make sure that BGP is running on the edge routers. Because if we are forwarding traffic through the network, let's say from router A to router B, the edge router will do an IP lookup of the destination IP address, of course, will find the BGP route in the routing table, and there will be a next hop associated with that BGP prefix. The BGP next hop is typically the loopback IP address of the remote edge router, so the egress router in the MPLS network. And that loopback address is typically known throughout the network in the IGP, or the Interior Gateway Protocol, OSPF, ISIS, EIGRP, and so on. That edge router will then slam one or more labels on top of the packet, and the core routers will be forwarding the packets based on a label lookup and no longer on an IP lookup. So because they don't do an IP lookup, these core routers, they don't need to have the route, the BGP route, in the routing table. Hence, they do not need to run BGP at all. So when we have a look at the packet forwarding through the network, when we receive an IP packet, this edge router will slam one or more MPLS labels on top of the IP packet, and the packet will be forwarded through the network, and the egress router will just remove the MPLS labels and forward the packet as an IP packet. These core routers only do a lookup of the MPLS label in a special table. They will no longer do an IP lookup through the routing table. Optimal traffic flow. In the past, we had WAN protocols running here, ATM, FrameRelay, X25, and so on. And typically, this service was built by using virtual circuits. And the virtual circuits were typically very costly. That's why if a customer wanted to transport its traffic over the service provider network, it typically opted for getting as least amount of virtual circuits as possible. So they typically went for a hub and spoke solution where we had all the virtual circuits towards a hub site that we have here, router B. That meant that all the traffic was going from the spokes to the hub and from the hubs to the spoke. But in some cases, we might have traffic going from spoke to spoke, while the traffic had to go through the hub, back out into the core of the network, towards the remote spoke. So this is not really optimal. With MPLS, we will always have optimal traffic flow. So from any side to any other side, the traffic flow through the MPLS core will take the least cost path or the optimal path. And then the big one, the peer-to-peer model for MPLS VPN Layer 3. Again, in the past, we had WAN protocols here. We had ATM, FrameRelay, X25, and so on, with virtual circuits deployed in the core of the network. This meant, however, that when we connected the customer to the service provider network, these customer routers did not pair at layer 3 with the provider routers. The customer routers, router A, B, and C, in this case, they had a layer 3 adjacency or routing protocol adjacency directly between them over the virtual circuits, over the service provider network. However, with MPLS VPN and MPLS VPN Layer 3 specifically, the customer routers A, B, and C, they now peer directly, Layer 3-wise, with their connected provider edge router here. So we have a Layer 3 adjacency or routing protocol adjacency between the customer router and the service provider router that we have here. What are the benefits of this? Well, there are many benefits or advantages of this. First of all, again, we have the optimal traffic flow throughout the network, even without a full mesh of virtual circuits as we had with WAN protocols. The big one is the better manageability. When the customer added one router in the past with WAN protocols, the service provider had to deploy several virtual circuits from the newly deployed site to the existing site. And this was a pain to keep track of. Now with MPLS VPN layer 3, the service provider, he just needs to hook up one provider edge router and create a layer 3 adjacency or routing protocol adjacency with a directly connected customer router. So that's much easier. So provisioning wise, this was much easier for the service provider. And also the scalability is a lot better because we don't have to deal with virtual circuits anymore. Now to be fair, this is also a disadvantage to the peer-to-peer model. It is that the service provider needs to participate in the routing with the customer. So the service provider needs to set up a routing protocol adjacency with the customer edge routing. It also means, of course, that it receives all the routes and prefixes onto its edge routers. And the final one is traffic engineering or source routing. If you look at this network, then in the past it was impossible for router A and B to forward traffic to router E and make sure that the traffic took the bottom path. Why? Well, because the top path is the shortest path. So if the traffic was IP traffic, then router C, no matter what, would always do an IP lookup of the destination IP address in its routing table and forward the traffic over the top path. With MPLS, we can do something else. We can do source routing. Router A and B can put labels on top of the packet so that router C is forced to forward the traffic over the bottom path, right? Router C just does a lookup of a label and forward the traffic based on that. It no longer does an IP lookup, and this gives us the possibility to do source routing or traffic engineering. Hello and welcome to Lesson 2, which explores the MPLS architecture, meaning the building blocks that make up MPLS. MPLS labels, LSP, LSRs, FEC, etc. I'll explain how the label distribution works and how the MPLS forwarding table is built. So let's have a look at MPLS labels, LSPs, and FECs. So what is one MPLS label? One MPLS label is basically a field of 32 bits. The first 20 bits are reserved for the label value itself. So 20 bits means we have a value which is in the range of 0 to 1 million and a little bit. So that's a lot of labels that we can have. Then the next 3 bits are the experimental bits, but they have been renamed more recently to traffic class bits. These bits are solely used for quality of service. Then we have the bottom of stack bit. It's just 1 bit. If this bit is set, it means that this label is at the bottom of the stack. So basically you will have a stack of labels. It could be 1 label, 2 labels, 3 labels, and so on, but only the bottom label will have this bit set. And finally we have the 8 bits, which are the TTL or time to live bits. This functionality is the same as with IP packets, so this field is used to make sure we can do routing loop prevention. So this is what a label stack can look like. We have more than 1 label, they're just stacked on top of each other, and only the bottom label has the bottom of stack bit set to 1, to indicate that whatever follows is the payload. The payload could be an IPv4, IPv6 packet, or a layer 2 frame. Note that there is no protocol identifier, no protocol field in here. So basically, by just looking, for example, at a Wireshark capture, it's not possible to figure out what the payload would be if you would look at a protocol field, because there is no protocol field in the label stack. There is, however, inside the layer 2 header, a MPLS protocol identifier. So this is typically a field what identifies the protocol that follows the layer 2 header. Usually it's the IP protocol field and so on. But here we are not carrying an IP packet anymore. We are carrying an MPLS packet. So for the different encapsulation types like PPP, Ethernet, HDLC, frame relay and so on, we now have an ETH type value or a protocol identifier which indicates that the protocol following the layer 2 header is actually MPLS. So the ether type or protocol identifier typically is 8847, indicating that we are carrying an MPLS packet. So we'll have an MPLS label stack, and behind the MPLS label stack is then the transported protocol, which could be IPv4, IPv6, or a layer 2 frame. Let's have a look at an LSR or label switch router. When a packet comes in unlabeled, it's an IP packet. It might be switched out of the router as a labeled packet, so it has one or more labels. We call that an ingress LSR or an imposition LSR. On the other hand, the packet can come in to the LSR already labeled and be switched out as an IP packet, so there are no more labels. We call that an egress LSR or a disposition LSR. And finally, we can have intermediate LSRs. Typically, these are the LSRs that receive a packet which is labeled, and they forward out the packet also labeled. So they will just do a label swap of the top label. A label switched path is really an ordered list of routers. So a label switched path is a path through the network from one LSR to the other one. And those LSRs are forwarding the packets labeled. Now we can have one LSP end-to-end through the MPLS network, or we can have back-to-back LSPs. And it is possible that the router in the middle here connecting the two LSPs actually does an IP lookup as well. Another possibility are nested LSPs. That means that we might have one LSP inside another LSP. The packets will be forwarded as labeled packets end-to-end, but here, for the nested LSPs, the packets will receive an additional label in the label stack. And that additional label identifies the nested LSP. What is a FEC? Well, a FEC is a forwarding equivalence class. It's basically a group or flow of packets that is forwarded along the same way, the same path through the MPLS network, and all those packets are also treated the same way when they are forwarded. Typically, when you look at a FEC, all those packets, they will have the same label because they need to be forwarded along the same path. But it could be more than just the same label. Since they need to be treated in the forwarding path the same way, it also means that those packets, they will have the same quality of service. So all those packets that follow the same FEC, they will also have the same experimental bit value in the top label. That's basically what a FEC is. All those packets belong to the same group or flow of packets, and they are forwarded along the same path, and the forwarding treatment is the same. What are some examples of a FEC? Well, a FEC could just be all packets forwarded towards the same layer 3 destination IP address, so the same prefix. So all the packets that are forwarded after an IP lookup in the routing table will receive the same FEC, they will receive the same label. Another example of a FEC is a multicast group. So basically, all the packets which are multicast packets forwarded for a certain multicast group. But it could also be a group of packets forwarded towards the same destination and also having the same diffserv code or quality of service field. Fourth example is it could be that a FEC is also all the layer 2 frames forwarded in the same way through the MPLS network. And finally, it could be that a FEC are all the packets, not necessarily the same destination, but all the packets forwarded towards the same BGP next hop. This means that we could have a bunch of prefixes that all share the same BGP next hop IP address in the routing table, while all those packets will be forwarded according to the same FEC, the same way through the MPLS network. Let's have a look at label distribution protocols. So why distribute labels? Well, otherwise MPLS won't work. We need to distribute labels from router to router to be able to forward labeled packets, right? One LSP will carry labeled packets, and we need to make sure that each LSR along the path is able to forward a packet. So basically it will receive labeled packets, so it must do a lookup of the top label on top of the packet, and then do a lookup in the label forwarding table. Figure out how the packet should be forwarded. So it typically means that the top label will have to be removed or swapped out by another label. and then be forwarded out on a particular interface. So each LSR must be able to figure out that when a labeled packet comes in, how that packet should be forwarded. We basically need a local and a remote label, or an incoming and an outgoing label. If you look at the example on the left, we have an LSR advertising labels towards the previous LSR. This label will be seen by this LSR as the remote label. It means that when it needs to forward a packet to the downstream router, which is this LSR on the right-hand side, then it must slam the MPLS label that it received from that LSR on top of the packet. So basically, the outgoing label will be the remote label it received from the downstream LSR. On the other hand, each LSR must first assign a local label. That local label is the label that it expects on top of the packet when the packet comes into the router. And this local label is also the label that we just saw gets advertised upstream to the upstream LSR. So how does the distribution of labels actually work? Well, we basically have two ways to distribute the labels. Either the labels can be distributed by a separate protocol. So we really have a label distribution protocol that just distributes the labels or the label bindings. The label bindings is just a prefix with the associated label. The second way is we can piggyback the labels on an existing routing protocol. In the first category, we have two main examples. We have the Label Distribution Protocol, or LDP. It is a protocol that was invented just to distribute the label bindings, so the prefixes and the labels for whatever routing protocol you might be running. Second example is RSCP for TE. So we basically have reservation protocol for traffic engineering, which will advertise labels specifically for traffic engineered LSPs. In the second category, where we have the labels piggybacked on existing routing protocols, we might have BGP or multi-protocol BGP. There we have BGP advertise a BGP prefix, of course, and an associated label. We also have an existing routing protocol like OSPF or ISAS that has been modified not only to carry the prefixes, but also a label associated with that prefix. And as we will see in later lessons, that is typically used with segment routing. LDP. Well, we have LDP, and LDP only distributes labels for IGP prefixes. It will never ever distribute labels for BGP prefixes. And the reason is, of course, that BGP will do that job itself. BGP can distribute the BGP prefixes and the associated labels. When you deploy LDP, when you enable LDP on routers, then automatically LDP will assign one local label, which is unique, per prefix. So for every prefix in the routing table, if it's an IGP prefix, so OSPF, ISIS, ERGP, static route, and so on, but not BGP, it will assign one unique local label per prefix and advertise it to all its neighbors. So LDP will have to form neighborships or adjacencies with all the directly connected routers to be able to advertise those label bindings. In the end, all the routers learn all the MPLS labels for all the IGP prefixes from all the neighboring routers. Each LSR or router will typically pick one label associated with one IGP prefix. But which label? Because it has received labels or label bindings from all the LDP neighbors. Well, it will pick the label associated with the IGP prefix, associated with the next hop router or the downstream router that it finds in the routing table for that particular prefix. As you can see here, each LSR will just start to advertise a label binding through LDP, and a label binding is a particular prefix and a label. This label binding will just be advertised to all its LDP neighbors. Here we might have a prefix on the right-hand side, 10.1.1.0/24. Even though this prefix is on the right-hand side, the LSR in the middle here will just advertise the label binding to all its neighbors. The other example is RSCP-TE. Now, RSCP-TE, because we have traffic engineering, it will work slightly different. Here, the label will be advertised hop by hop in sequential order from what we call the tunnel tail-end router towards the tunnel head-end router. And per tunnel, we will have one label assigned. So each router will have assigned one local label for the tunnel and then advertise it upstream towards the upstream router, where it becomes the remote label or the outgoing label for that particular tunnel. So the difference with LDP here is that the label distribution happens on demand, whereas with LDP it was not on demand. Let's have a look at label distribution modes. There are basically two distribution modes, the downstream on demand and the unsolicited downstream. With the downstream on demand, each LSR will actually request its next hop for a particular label for that LSP. What is the next hop? Well, basically the next hop router is what you find in the routing table as the next hop for a particular prefix or flag. So it will request the downstream neighbor for a particular label and it will wait for that downstream LSR to come back with a label. With unsolicited downstream, in that label distribution mode, there is no request. Each LSR will just distribute label modes ad hoc to all its LDP neighbors. There is no requesting of labels at all. So you have the downstream on-demand label distribution mode, or DoD. Basically, because there is a request and a reply for a particular label for a particular LSP, there will only be one remote binding per LSP. With the unsolicited downstream label distribution mode, there can be one, but there can be many more remote label bindings, because each LSR will typically get from each of its neighbor a remote binding for each LSP. So let's have a look at the unsolicited downstream label distribution mode. Basically, as soon as each LSR learns about a particular prefix, in this case the prefix 10.1.1.0/24 on the right hand side, it will start to advertise a label binding in any given order. As soon as the route is in the routing table, LDP will advertise the label binding, so the prefix and the associated label, to all its LDP neighbors. In the end, every LSR will have a label binding for that prefix from all its LDP neighbors. With the downstream on-demand label distribution mode, we basically need to have an LSR that starts a request. So imagine here that the LSR on the left-hand side sees in its routing table the prefix 10.1.1.0/24. It could send out a request for a label for that prefix, and it will send that request downstream. So when it looks up the prefix in the routing table, it will find the next hop router, which is this router, in the routing table, and it will send a request for a label for that particular prefix to that router. That LSR will do the same in turn, and the downstream routers will do the same as well, until we reach the LSR where the prefix is actually connected. In that case, that LSR will initiate the reply. So it will send the label binding back upstream towards the initiator of the request. Only when the LSR that initiated the request receives the label binding, now the packets can be forwarded downstream towards the destination prefix. There's also something which is called the label retention modes. We basically have two label retention modes, the liberal label retention mode and the conservative label retention mode. With the liberal retention mode, every router is going to store the label bindings for every prefix from each and all of the LDP neighbors it received a remote binding from. There's an advantage to that. The router will adapt quicker to routing changes if there are any. With conservative label retention mode, the LSR will store only one remote binding per prefix. All the rest it will not store at all. So the advantage here is, of course, that it will need to store fewer labels. The disadvantage is that it will not have this quicker adaptation to routing changes, which is what the liberal label retention mode has. So let's have a look at the quicker adaptation to routing changes with the liberal label retention mode. In this case, we will look at router A and it is forwarding label traffic towards the prefix 10.1.1.0/24. Router A receives a label binding from its two LDP neighbors, neighbor router B and from router D. The traffic will be forwarded over router B because the top path is the least cost path. So the traffic from router A will be forwarded towards the destination to the next hop, router B, with a label 123 on top of the packet. However, if there is a routing change, like the link between router A and B going down, then router A will look what other labels it has stored. And it will look in its routing table and it sees now that the routing has changed. The next hop for the prefix is not router B anymore, but it's now router D. As soon as it figures out that the routing table has changed and the next hop router is now router D, it will look for the remote binding that router D has advertised. And it will find the remote binding for that prefix and it will figure out that the label is 99. So now router A, as soon as the routing table has converged, can now switch over the traffic with label 99 over router D. Whereas if we would not have the label retention mode, router A would have to wait for router D to advertise a new label binding. So that would introduce an additional delay. We also have two LSP control modes. We have the independent LSP control mode and the ordered LSP control mode. With the independent LSP control mode, the LSR can create a local binding as soon as it learns about the FEC or the LSP, and this happens independently from the other LSRs. The disadvantage is here that the router or the LSR might start to forward labeled packets where the downstream router is not ready yet to forward labeled packets, and then that downstream router will drop the labeled packets. This is not something that will happen with the ordered LSP control mode, because with the ordered LSP control mode, the LSR will only create a local binding if it recognizes that it's the egress LSR for the FEC. For example, if the prefix is directly connected to that LSR, or if the LSR has received a label binding from the next hop router. The disadvantage is here that it takes more time to create the LSP end-to-end, but the advantage is here that the packets only are forwarded when every router along the path is ready to forward labeled packets. Let's have a look at some routers and let's have a look at the label distribution modes. So let's have a look at the lab. I have a lab set up here and it's actually running on Whirl, which is some software that Cisco has to be running virtual lab routers. Throughout the course I have a few setups. For this particular lesson I have this setup. All the routers are running iOS. It's kind of easy to use. It's also kind of the de facto standard. Most people still know how iOS works. They know the CLI and so on, so it's pretty easy to use. With this network, I have 7 routers here. The loopbacks typically have a loopback IP address, which is 10.100.1.something/32. And all the link IP addresses are 10.1.something.something/24. And I'll use that scheme throughout this live lesson course. So let's have a look at some of the routers. Here we have router 1, and it is running MPLS LDP with its neighbors. We can have a look at that. So we can see that this router 1 actually has 3 LDP neighbors. And that makes sense because router 1 has router 2, router 7, and router 6 as LDP neighbors. But we are here to look at the bindings. What do we have as bindings? We just type show MPLS LDP bindings, and we see all the bindings that router 1 received from its LDP neighbors. So what do we have here? Well, in the lib, which is the label information base, so it's basically the table where we store all the label bindings, either the local ones or the remote one. And typically we will see here the prefixes, different prefixes. These are all the IGP prefixes that this router has. So if you do show IP route, you will see all the prefixes in there. And for all the IGP prefixes in the routing table, you will see an entry here. For each of these prefixes, we will have one local binding, one binding only, and one or more remote bindings. How many remote bindings? Well, it depends on the number of neighbors that you have. In this case, router 1 had 3 LDP neighbors, so we have 3 remote bindings. For each entry, for each prefix that we see here, we have a local binding. Now, if the prefix is directly connected, we see an implicit null label assigned to it. We'll come back to that in a later lesson. And then we have the remote bindings. So we either have implicit null again, which was advertised by the LDP neighbor, or an actual label value, which is between label 16 and 1 million and a bit. Remember that the labels between 0 and 15 are actually reserved labels. They have a special value, so they will not show up as a number here. You can see that each neighboring router, this is neighbor 2, this is router 6, and this is R7. They all advertised a particular binding, a label, or that particular prefix. We can also look at a particular binding in detail. So let's have a look at 10.100.1.5, which is the loopback of router 5. So if you look at the topology, we are at router 1 here, and we are looking at 10.100.1.5/32, which is the loopback of router 5. And we can see that we have a local binding for it, label 26, and we have 3 remote bindings, one received from router 2, one received from router 6, one received from router 7, each with a respective label. Let's have a look at the label forwarding instance base. The LFIP, or the label forwarding instance base, is a new table used on routers to forward incoming labeled packets. We used to have the FIP table before, and we still have it, which is the forwarding instance base. It's not the routing table, it's not the RIB. The routing table is used to store prefixes. It holds information like the prefix, the mask, the outgoing interface, the cost of the prefix, and so on. The FIP is really a distilled table which holds only the necessary information to forward the packets, such as the prefix, the mask, the outgoing interface, and the next hop IP address. That's all which is needed to forward an incoming IP packet. So this FIP table or CEF table is used to forward incoming IP packets. As we can see here, on this LSR, if an IP packet comes in, it could be going out as an IP packet, but it could also be going out as a labeled packet. That's why this FIP table is enhanced so that we can find outgoing label information for the particular prefix after doing an IP lookup. Now we also have this new table, which is the LFIP table. This is a table used to forward incoming labeled packets. So the packet will be coming into this LSR already with an MPLS label. And then the packet will go out either with another label on top of the packet or unlabeled. So it goes out as an IP packet. It depends on the result of the lookup in this LFIP. So what do we have in the LFIP? Well, in the LFIP we have entries. It could be an IPv4 prefix, an IPv6 prefix, a VPN, layer 2 or layer 3 prefix, a T tunnel entry, a layer 2 forwarding entry, and so on. It basically can be anything. What we must have is one local label or one incoming label. The packet will be coming in with that particular label. And then we have one outgoing label, so one label which is swapped or pushed on top of the packet, or more than one label. We can push more than one label on top of the IP packet. And then we'll have one outgoing interface with the next hop. It could be more than one outgoing interfaces, but then we have load balancing, and we'll explain that on a later slide. How do you look at this LFIP? Well, you just use the command show MPLS forwarding on all the operating systems that we have, and you will see the complete content of the LFIP table. You will see an incoming label, outgoing interface, and so on. And optionally, you also have counters to count the number of packets or bytes forwarded per LSP. As I mentioned, you can also have load balancing, meaning you have a packet coming in which is labeled, and then it can go out on one or more outgoing interfaces, but because we have load balancing or equal cost multipath for a particular prefix. Of course, the packets coming in, they will not be forwarded over multiple interfaces, let's say at the same time. They will be forwarded over one outgoing interface based on some load balancing algorithm. And the load balancing algorithm or scheme depends on the operating system and typically also the platform which is being used. But no matter what, the load balancing is always per flow. So packets belonging to the same flow will take the same outgoing interface. Always. We do not do per packet load balancing. That is deemed to be evil because you can have out of sequence packets. So let's have a look at an example. If we have the LFIP, the minimum amount of information that we have there is an incoming label or a local label, outgoing interface, and which prefix or LSP entry that we are looking at. And in this case, we actually have load balancing. We have two parallel links between a pair of routers. We have two outgoing interfaces, interface 1 and interface 2. For this entry, which is tied to the prefix 10.0.00/8, we have one local label, so the packet comes in with label 18, and then we'll go out with label 31, either outgoing interface 1 or 2, either one. By chance, here the outgoing label is the same, but that will typically happen when we have two parallel links between a pair of routers, because there's really only one LDP session between the pair of routers, and over the LDP session, this router advertises the same label 31 for this particular prefix to the router on the left-hand side. There is another case of load balancing, namely on the LSR on the left-hand side, we have two outgoing interfaces, but towards two different downstream LSRs. And typically, those routers will be advertising a different label for that particular prefix. So now, the router on the left-hand side has two different outgoing labels on the two different outgoing interfaces, 1 and 2. But still, per flow, when packets come in with the label 18, the router will pick either outgoing interface 1 or outgoing interface 2 to forward the traffic. Let's have a look at the LFIP or the forwarding table used to forward labeled packets on some routers. Alright, let's have a look at our network again. Just a reminder, all the loopback IP addresses of the routers are 10.100.1.something/32. And all the link IP addresses are 10.1.something.something/24. We'll have a look at the prefix of router 5, its loopback, it's 10.100.1.5/32. And we'll have a look at the LFIP on router 2. So let's bring up router 2. Let's first have a look what we have in the routing table. Show IP route 10.100.1.5. And we can see we have the entry here, it's OSPF prefix, and we have two outgoing interfaces. That's because we have load balancing out of router 2 towards router 3. We have two parallel links between router 2 and router 3. So what labels to be used? What are we going to put in the LFIP? Well, let's first have a look what we have in the lib. What are the labels that we have as a local label and remote labels put there by LDP? So show MPLS LDP bindings. Again, we have lots of IGP prefixes here, each time with a local label and one or more remote label. So what do we have for the prefix 10.100.1.5? We have one local label, label 24, and 4 remote bindings. Now, which one are we going to use? Well, when we looked at the routing table, we had two outgoing interfaces towards router 3. The loopback of router 3 ends at .3. So the label we are going to use to forward packets towards router 3 for 10.100.1.5 is label 27. And we were going to use this label in two places. Actually, we are going to use it in a FIB. When the packet comes in IP, we forward the packet labeled. When the packet comes in labeled, we forward the packet according to the LFIB table. Let's first have a look at the FIB or CEF table. So we do show IP CEF 10.100.1.5. And indeed, we see two entries. We are load balancing, and we see that the outgoing label is labeled 27. This label 27 that we received from router 3. What do we put in the LFIB? Well, let's first have a look at what we see in the LFIB. We just do show MPLS forwarding table, and we see the complete LFIB. Quite a bit of entries here. What do we have in an LFIB? Well, we always have per prefix a local label, only one local label, and then one or more outgoing labels. We have the prefixes, then we have some accounting, It's possible to track the amount of bytes for the packet switched per LSP. And then we have the outgoing interface and the next hop IP address of the downstream route if it's not a point-to-point interface. So that's what we have, but we only want to look at the entry for 10.100.1.5. So show MPLS forwarding table 10.100.1.5. What do we see? We see that indeed the local label is 24, which was the local label assigned by LDP. And we have the outgoing label again, 27, the same outgoing label as in the FIB or the CEF table. And again, we are load balancing towards router 3. There's one more thing you can do, which is you can specify the detail keyword behind the command, and it will show you a bit more information. Notably, you can see the complete label stack being pushed. Now, in some cases, we push more than one label. It could be 2 or 3 labels. Then you will see the complete label stack that we push here. So if you want to see, in the case we are pushing 2 or more labels, all of the labels, you will have to use this show MPLS forwarding table command with the detail keyword. Another thing that might be useful is that if you don't know that you are forwarding packets for a particular prefix, but you know that the packets will come in with label 24, for example, you can look at an LFIB entry by specifying the incoming label. And you just do that by typing the command show MPLS forwarding table, labels, and then the incoming label, in this case 24. And again, you see our LFIB entry that we have here for the incoming label 24. Hello and welcome to lesson 3, which explains label stacking and the need for it. I'll explain the label operations performed by a router, the special labels and their function, and how time to live or TTL is handled in MPLS networks. Let's have a look at the label stack. One MPLS label, as I mentioned before, is 32-bit long. The first 20 bits are actually reserved for the label value itself, so from 0 up to a value of 1,048,575. But first 16 labels are the reserved labels, they are special labels, so the label value is 0 to 15. Then we have the 3 bits, the experimental bits. They have been renamed to the traffic class bit and solely used for quality of service. We have 1 bit at the bottom of stack bit, and then the 8 bits for the TTL or time to live value. So what about this label stacking? Well, we can have more than one label in the label stack. So we have seen that the label stack sits in between the layer 2 frame header and the transported protocol itself. You can have more than one label, they're just stacked on top of each other. It's just that the last label has the bottom of stack bit set, indicating that whatever comes behind this label is the actual transported protocol itself. So why do we do this label stacking? Why do we need more than one label? Well, in principle, one label would have been enough if you just wanted to get a packet across from the ingress LSR to the egress LSR through the MPLS network. But from time to time, we want to do more than just transport a label from ingress to egress LSR. Let's have a look at an example where we will use 2 labels. And this is a very typical example. We will see later that with the MPLS VPN layer 3 service, we will always use 2 labels. We will have 2 labels in the label stack, and the top label is what we call the transport label. It is the label used to transport a packet from the ingress LSR towards the egress LSR. So every router in between, any core router, will just look at this top label value and switch the packet out according to that value. So the packet goes from ingress to egress LSR solely based on the value of the top label. But we have a second label, the bottom label. That bottom label is used to identify the service itself. In our case of MPLS VPN layer 3, it identifies the service. In that case, it identifies the VPN. So once the packet hits the egress LSR, this bottom label is used to indicate the VPN. So it tells the router, the egress LSR, to which VPN or which customer the packet should be switched. So we can have multiple labels. There are other examples, and throughout this course we will see that we have other services where we use more than one label in the label stack. So here's just an example of label stacks. We can see an IP packet with one label, we have an IP packet with 2 labels, 3 labels, 4 labels, and so on. There's really no limit to the amount of labels that you can have in a label stack. Of course, when we add a lot of labels, there's just one thing you need to watch out for, and that's the MTU, or the maximum transmission unit size. Basically, a packet will grow in size as you add more and more labels to it. In the case of Ethernet, for example, typically the MTU size is there 1500 bytes. If you add 1, 2, 3 labels, we might cross that limit, and the packet might be too big to be forwarded as is by an LSR. And in that case, the packet would have to be fragmented, just like IP packets who are too big need to be fragmented. However, routers doing fragmentation is something we want to avoid at all times. It's not a good thing. Fragmentation should be avoided because it is a burden on the forwarding performance by routers. So that's something we need to watch out for. Also, the label stack can grow or shrink while the packet is forwarded through the MPLS network. We will see that there are examples where routers actually pop off one label or remove 2 labels from the label stack. Or in the opposite way, sometimes in the middle of the network, a router can add 1 or 2 labels for whatever reason. So it's perfectly possible that while a packet is transferred from the ingress to the egress side of the MPLS network, that the label stack size grows or shrinks. Let's have a look at forwarding with labels. So there's a few label operations that you need to know about. The first one is swap. Basically, on an LSR, we'll have a packet coming in with 1 or more labels, but we only care about the label at the top. In this case, we can see the packet only has 1 label, and the top label, hence, is 99. Now, if we look it up in the LFIP, we'll see that we do have a local label, or an incoming label, 99, and the outgoing label is 32. So that means that the LSR, the label switch router, needs to swap the local label or incoming label 99 with an outgoing label of 32. So we just do a swap of the label and we forward the packet out of interface 1 and it goes on towards the destination. So that's basically the operation of swap. Important to note here is that the number of labels in the label stack remains the same. We only swap the top label. For the rest, we do not touch the label stack at all. The second label operation is the push operation. It basically means that we add 1 or more labels to the label stack. Now, it might be that a packet comes into the router with no labels at all. Hence, as I mentioned before, we will do a lookup in the FIP or CEF table because it's an IP packet. We can see here in the CEF table that the outgoing label is 32 and we only push 1 outgoing label. So we push 1 label on top of the IP packet and the LSR forwards the packet out of interface 1 with that particular label. Or there is a possibility that we actually push more than 1 label. In this case, when you look at the FIP or CEF table, we see that the packet gets an additional 2 labels pushed. And we see that here between brackets. And we always go from left to right. So the top label is the 612 label and the bottom label is the 32 label. So those 2 labels get pushed onto the packet and then the packet is forwarded by the LSR out of interface 1. Now this is an example in the FIP or CEF table. The same push operation can also occur in the LFIP table, of course. But then the packet would already be coming in as a labeled packet. We also have the pop operation. Pop means remove 1 and exactly 1 MPLS label. So if the packet comes in to the LSR with 1 label at the top, in this case label 99, we do a lookup in the LFIP and we see that the outgoing label is actually pop. So the operation is pop, which means remove 1, exactly 1 label. So in this case, because the packet only came in with 1 label, the packet would be switched out with no labels at all. So it becomes unlabeled. It could also be possible that the packet comes in with actually 2 labels or more. Still, the pop operation means remove 1 label and forward the packet onwards. So in this case, the LSR removes the top label, the label 612, and the packet is forwarded onwards with only 1 label remaining in the label stack, the label 32. So you must remember, pop means remove exactly one label from the label stack. What about if an LSR gets a label packet? So a label packet comes into the router, but it does not know the top label. In this case, we see that the LSR receives a packet with a top label of 612. But when it looks into the LFIP, it doesn't find the incoming label of 612. There is a 611 and a 613, but not a 612. In that case, the router could do a few things. But in reality, it will do one thing and one thing only. It is drop the packet. It is a golden rule that if the incoming label is not present in the LFIP, the packet is dropped. And why is that? Well, imagine that the router would still try to forward the packet. What are the options that it could do? It could do, for example, remove all the labels and then try to do an IP lookup. So a lookup of the destination IP address into its routing table. But remember what we said, for example, with the BGP3 core, it might not even have the route for that destination IP address. So in that case, it would not be able to forward anyway, so the router would just drop the packet. There is another possibility. It might not even be an IP packet being transported. It might be a layer 2 frame. So imagine that you are a router in the core of an MPLS network and you receive a labeled packet, but you do not know the top label. You did not assign that top label. In that case, even trying to do an IP lookup would not make sense. It wouldn't work because we are not transporting an IP packet, we are transporting, for example, an Ethernet frame, a layer 2 frame. So in that case, the lookup would fail as well, and the router would have to drop the packet anyway. So that's why we have a golden rule. If an LSR does not know the incoming label, it will just drop the packet, and that's it. Let's have a look now where these operations typically happen. So remember, we have the swap, push, and pop operations. Where do they occur? Well, if we have the ingress LSR, so this is an LSR, a router, which receives non-labeled traffic and sends them out into the MPLS network as labeled packets. So the packet becomes labeled for the first time, so the operation is push. We push one or more labels, and typically you will see that being done in the CEF or FIP table. Because the packet comes in as an IP packet, we have to do an IP lookup in the FIP or CEF table. And then the incoming LSR, router A in this case, will find an outgoing label or more than one label and push those labels on top of the packet and forward the packet onwards into the MPLS cloud. We also have the swap operation, and that typically occurs on an intermediate router, so an LSR in the middle of the LSP. That router or LSR will receive labeled packets. So a packet will come in with one or more labels in the label stack, but the router only cares about the top label. In this case, the top label is label value 32. It will do a lookup in the LFIP. Because the packet is coming in labeled, the router needs to do a lookup for the incoming label in the LFIP, the label forwarding instance space. It finds the incoming label or local label 32, and then we'll see that it needs to swap or replace label 32 with label 99 and send it out of interface 1. And finally, we have the pop operation. That's a typical operation that will happen at the end of the LSP, so towards the end of the MPLS network. And it means that the packet comes in, for example, in this case with one label, and we pop off or remove one label and forward the packet onwards with no label, so the packet becomes unlabeled. In that case, the router does a lookup in the LFIP, finds the local label 99, pops off one label, and removes the packet as an unlabeled packet. Now, if the packet comes in with two labels or more, the pop operation still means only remove one label. In that case, the packet is still forwarded as a labeled packet. That can occur as well. And notice here that while router D is the egress router, it's actually not the router doing the pop operation. It's the one router before. It's typically something that occurs all of the time. And we will call that penultimate hop popping. It's not on the penultimate router, router D, that we pop off the last remaining label, but it's at the penultimate hop router, the one router before the last hop router. So let's have a look now at forwarding with labels on some of our routers. So we're back here with our network. We'll have a look at the label operations through the network, How do we get the packet from router 1 to router 4? We will be forwarding a packet towards the loopback of router 4, so the destination is 10.101.4, the loopback of router 4. So let's have a look first at router 1. First of all, do we have a route towards the loopback of router 4? We do show IP route 10.101.4. Yes, we have a route, and we actually have load balancing out on two interfaces. But what label are we putting on top of those packets? Well, we have to look at the FIP or CEF table. So we do show IP CEF 10.101.4, and we see indeed that we are pushing the label 23 on top of the packets. And again, we still have load balancing over the same interfaces, of course. We can actually verify that this is happening or not by doing a traceroute, because the traceroute command has been enhanced to show the MPLS label stack. So we do a traceroute of 10.101.4. We can see indeed that the packet is going out with a label of 23 at the top. We can actually already see that at the second hop, router 2, the label is swapped from 23 to 26. And then at the third router, so router 3 here, we have this pop operation where we pop off the top label. Let's have a look at the label swapping operation at router 2. At router 2, the packet will already be coming in labeled with label 23. So how do we look at it? Well, we have to look at the LFIP. So we do the command show MPLS forwarding, and we know the labels, so we put label 23. Incoming label 23, outgoing label is 26. And again, we have load balancing, we have two links towards router 3. So the packet will be going out with label 26. So here we have the label swap operation. So what happens at router 3? Well, at router 3, the packet will be coming in with label 26. Let's verify that. So at router 3, we know that the packet will be coming in with label 26. So we need to look into the LFIP and try to find label 26. So let's do show MPLS forwarding labels 26. And indeed, we have an entry here for 10.101.4. Incoming label 26 and outgoing label is pop label. So here we do the pop operation. We remove this one label and forward the packet as is. So the packet is forwarded as an IP packet. And actually, if we go back to our traceroute command on router 1, we see that the output we got from the traceroute command is correct. The packet was first forwarded with label 23 towards router 2. Label 23 was popped with label 26 when the packet was forwarded to router 3. And router 3 popped off the label 26 and forwarded the packet onwards towards router 4. Let's have a look at reserved labels. So we have a label range of 0 up to 1,048,575, which is 20 bits of labels, but the first 16 labels are actually reserved for special operation. So labels 0 to 15 are reserved. They're only used for specific operations. It could be that the forwarding is differently than normally. It could be that we look at certain quality of service information, and it could be that this reserved label is actually present in the label stack, or it's not present in the label stack. Let's have a look at the first one, reserved label 3 actually, which is the one which is used the most. First of all, label 3 will never be present in the label stack. It's implicit null label. It will be advertised, for example, through an LDP label mapping advertisement, where we advertise the label binding. So we do advertise through LDP the label 3. But it means to the router receiving this label, do the pop operation, meaning remove exactly one label from the label stack and forward the packet onwards. And this is, by the way, the default behavior. So wherever possible, the penultimate hop popping, so removing one pop at the end of the LSR, is the default behavior. In this case, let's say we are looking at a prefix which is connected to router D. For that prefix, router D will actually advertise label 3, and we call that label the implicit null label. It tells the router upstream, so router C in this case, pop one label, do the penultimate hop popping operation. So router D here is the ultimate router, the last hop router on the LSP. The router one hop before, so the penultimate hop router, needs to do a pop when forwarding label traffic for that destination. So when the router receives a labeled packet, in this case the label is 99, it will do a pop operation. It will remove label 99 and forward the packet onwards to router D unlabeled. In the LFIP, we can see that the incoming label is label 99 and that the outgoing label is pop. So actually we do a pop operation to remove the top label and forward the packet onwards towards router D or the egress router of the LSP. So the LSP is actually terminated one hop short at the penultimate hop router. So that's why we call it penultimate hop popping. But why do we do that? Why, if we wouldn't do it, then router D would actually receive the packet still labeled. It would have to do a label lookup in the LFIP, remove the label, and then probably do an IP lookup for the destination IP address in the IP header and forward the packet according to whatever entry we have in the routing table or actually the FIP table or CEF table. So in that case, router D, the ultimate router, the egress router of the LSP, would have to do two lookups, a label lookup in the LFIP and an IP lookup in the CEF table. So to avoid this, by default, penultimate hop popping is always enabled. We distribute the load. The penultimate hop router, which is router C, will actually do the LFIP lookup, and then router D will just need to do an IP lookup. Another reserved label is label 0, and that's the explicit null label for IPv4. It's called explicit because this null label will actually be present in the label stack. So we will actually have a label with value 0 in the label stack. And this kind of neutralizes the penultimate hop popping behavior. We will not have the penultimate router do the pop operation anymore. So why do we do that? Well, basically, we want to make sure that the packets are still labeled when they are received at the egress router. This will allow the egress router at the end of the LSP to have a look at the experimental bits or the traffic class bits inside that label. And it can base its forwarding behavior on those traffic class or quality of service bits. But label 0 by itself doesn't hold any forwarding information. If the label is 0, it doesn't mean to the router forward the labeled packet this or that way. The label 0 is only there to hold the traffic class or quality of service information. So in this case, with explicit null enabled, the egress router, the last hop router of the LSP, will advertise the prefix with the actual label 0 to the upstream router, router C in this case. Router C, when it receives a packet which has a label, in this case label 99, it will actually do a swap operation and swap the label 99 with label 0. And then router D, when forwarding the packet, will have to do a lookup of the MPLS label. Now it's label 0, so it doesn't know how to forward the packet, but it will look at the experimental bits or the traffic class bits in that label and figure out what the quality of service is of the packet. And then after removing the explicit null label, it can forward the packet based on an IP lookup. So it will look up the destination IP address and the IP header in the routing table of router D. So router C in its LFIP will have an incoming label 99 and an actual outgoing label of 0. Router D, it can now forward the packet also based on the quality of service information, which is present in the experimental bits or traffic class bits. We also have the reserved label 2, which is really similar as the reserved label 0, but now it's for IPv6. So this is the explicit null label for IPv6 prefixes. It will be advertised by router D, the egress router of the LSP. Router D will advertise an IPv6 prefix with the associated label, label 2. So the penultimate hop router, router C, will receive a labeled packet and will now swap out label 99 with label 2, the explicit null label for IPv6. So in the LFIP of router C, we have an incoming label or local label 99 and an outgoing label of 2, the explicit null label for IPv6. Again, router D can now forward the packet based on the quality of service information embedded in the experimental bits or traffic class bits, and then do an IP lookup in the routing table to forward the packet onwards. And the last reserved label is label 1. It's a very specific label. It's called the router alert label. And it's really only used for MPLS OAM. And OAM stands for Operation, Administration and Maintenance. Those packets are really used only for troubleshooting and verification in an MPLS network. The whole point of this router alert label, label 1, is to make sure that the packets are forwarded in, quote, a safe, unquote, mode, meaning that the packets are certain to reach the destination. And the way we do that is by making sure that those labeled packets bypass any forwarding. So they bypass the forwarding in the ASICs or the TCAMs and so on the router itself. So typically those packets will actually be punted to the CPU of the router, be process switched, and then be forwarded onwards. So what will happen is the following. A router, in this case router A, will put a label stack on top of the packet, making sure that the top label is label 1. For router B, when it receives this labeled packet, it sees that the top label is label 1. The first thing it does is it will punt this packet to the CPU. It will then remove label 1, do a lookup in the LFIP of label 32, swap this label out with label 99, and then put label 1 back on top of it. And this goes on until the label packet reaches the egress LSR. The whole point here of this label 1 is to make sure that all the intermediate routers, all the LSRs here, routers B, C, and D, they will actually punt the packet. So in that case, the routers can be certain that the packet is forwarded correctly. In the LFIP, we will actually not see this label 1. We will just have the regular LFIP. We have an incoming label 32, outgoing label 99, and so on. But the label 1 is actually not shown in the LFIP itself. That is because the label 1 just means punt the packet to CPU. The other reserved labels, so we had the reserved labels between 0 and 15, are actually not used yet. So let's have a look at some of these reserved labels on our routers. So let's have a look at the reserved labels in our lab environment. So we're going to look at the prefix 10101.4/32, which is the loopback prefix of router 4. Let's have a look what we have at router 3 for that prefix. So we do show MPLS LDP bindings for 10101.4/32. And we see that we have a local binding as usual, label 26, and we have two outgoing labels. One is back towards router 2, we don't care about that one. And we have one further downstream. So the one we received from router 4 is implicit null. So in reality, this is label 3. It will get advertised through LDP as label 3. And we can see that in the LFIP, we have label 3 as an outgoing label. But in reality, it doesn't say label 3, it says pop label. So this is the implicit null label seen in the LFIP. We see it as pop label. So when the packet comes in router 3 with label 26 as a top label, we remove that label and the packet will be forwarded out towards router 4 with one label less. That's penultimate hop popping. Why is it penultimate hop popping? Because we look at router 3 for a prefix connected to router 4. Router 4 is the last hop router, the ultimate router. Router 3 is the last but one router, so it's the penultimate hop router. Can we change this behavior? Yes, we can do explicit null. How do we do that? We go to router 4, and on router 4 we change the behavior to explicit null. We do that with the following command, MPLS LDP explicit null. As of now, we no longer have penultimate hop behavior from router 4, but we will be using explicit null. So now if we go back to router 3, let's check again what label binding we have for the prefix 10101.4/32. We now have a label binding, and the label is explicit null. So router 4, instead of advertising the label 3, advertises now the label 4. So we have explicit null for IPv4 prefixes. Now if we look again in the LFIP, we now see that if a packet were to come in with label 26, we would forward the packet out of router 3 with the explicit null label. So now we just swap the outermost label 26 with label 0 when forwarding traffic towards the destination 10.101.4/32. So now we have the explicit null behavior at the end of the LSP. How can we double check that? Well, there is one way to double check this, but please don't do this on live routers. It's not a safe way because it's a debug command. On router 3, we can enable debugging MPLS packets. So we type debug MPLS packet, and from now on, we will see the packets going through router 3. Let's send a ping from router 2 towards the destination 10.101.4. So we have router 2 here. We send a ping towards 10.101.4. Only one ping, so we do repeat 1. And what do we see on router 3? We see that we received, it says RX here, received a packet with this as a label stack. This means the top label is 26, the experimental bits or the traffic class bits are 0, there's no quality of service information, and the TTL is 255. That's what we received on router 3. Router 3 will forward the packet out of gigabit 0/2, so transmit, with this label stack. And now we see the first value is 0. So the label is 0, explicit null label. The experimental bits or quality of service bits are still 0, and the TTL, of course, is 1 lower than it was when we received the packet. So this is proof that now we forward packets towards the ultimate router with the top label 0. Let's have a look at the TTL handling with MPLS packets. TTL is something which is well known from the IP world. We had an 8 bits field in the IP header always. Basically, it's used to prevent routing loops in an IP network. At every hop, every router will lower the TTL with a value of 1. When the TTL hits 0, it's game over, the packet will be dropped. And the router will generate an ICMP message which is sent back to the source of the original packet, saying we had to drop the router because the TTL expired. And this is an ICMP message which is type 11 code 0. Basically, TTL expired in transit. So this will prevent the packets from looping forever. And we have a similar thing in MPLS. There, the MPLS TTL value is also 8 bits long. So the maximum hop count will be 255. Every router will lower this TTL value by 1. And every router or LSR only looks at the top label. Only the TTL field in the top label will be lowered by 1 at every hop. And this will prevent, as in the IP world, the MPLS packets to be looped forever. So let's have a look at the MPLS TTL propagation. Now there are some rules in play. We basically have to be a little bit careful because with the label stack it can actually grow in size. So we can add extra MPLS labels, or it can shrink in size when we remove MPLS labels. So what are those rules? Well, the first time a packet becomes labeled, so when we go, for example, from an IP packet to a labeled packet, we do copy the TTL field from the IP header into the label stack. So all the TTL fields and all the labels will have that TTL value -1, which is copied from the IP header. When an LSR does a swap operation, we will just copy the TTL field from the incoming top label to the outgoing label -1. When we have a pop operation, so at the egress side of the LSP, we will copy down the TTL from the incoming top label to the newly exposed top label at the outgoing side, -1 of course. And when we have a push operation, so when the packet comes into the router already labeled, we will take the TTL field of the top MPLS label, subtract 1, and copy that into the TTL field of all the pushed MPLS labels. And finally, there's one thing where we have to be careful. When we go from the labeled side of the network to the unlabeled side of the network, or the IP side, then we do copy the TTL field of the top MPLS label down into the TTL field of the IP header, unless the MPLS TTL value is bigger than the IP TTL value. And we do that to avoid routing loops. Let's have a look at an example where we have TTL propagation. On router A, we have an incoming IP packet. This is the ingress LSR, so it will push one or more labels, in this case 2 labels. We copy the TTL field of the incoming IP header, and the TTL is 16. We copy this value, -1, into all the MPLS labels, and then we forward the packet onwards. Router B will only look at the top label, subtract 1 from the TTL field of the top label, and swap it out with a new label with TTL value 14. This router is an intermediate router. It does not touch or change in any way the TTL field of the underneath labels or the TTL field in the IP header. And finally, when we do the pop operation, the router will remove 1 label and then copy down this TTL value of the top label, -1, into the newly exposed top MPLS label. At the egress LSR, we have another pop operation. In this case, we remove the last MPLS label. We will take this value, 13, again subtract 1, and copy that down into the IP header, unless the MPLS TTL is actually bigger than the IP TTL. But in this case, it's not. So here, we put a new TTL value of 12 in the IP header. Let's have a look at example 2. Here, router B receives a packet with 1 label, and it's actually going to perform first a swap and then a push. Now, we take the TTL value of the top label, subtract 1, and put that value in the swapped and all the pushed labels. In the end, it's possible that the TTL does expire. If that's the case, as in the IP world, the router will actually generate an ICMP error message. And it's the same error message as in the IP world. It's an ICMP message code 11/0, which means that the MPLS TTL has expired. And this is done, of course, to prevent routing loops. What a LSR typically will do is, when it sees that the TTL has expired in the top MPLS label, it will remove all the MPLS labels and generate an ICMP error message for that IP packet that's underneath the MPLS label stack, and send the error message back to the source of the original packet that caused the TTL to be expired. One good thing is that when you are trace routing in networks, you can actually see the label stack. And the reason for that is that the ICMP messages have been enhanced to carry that MPLS label stack. So when you are doing some troubleshooting, and you are doing, for example, a trace route through an MPLS network, you can see that the ICMP message that is returned from each router each time the TTL has expired for each probe you send, you can see the label stack there. So basically, when you do a trace route, you force the router to send out a packet, in this case a UDP packet, from the Cisco router, first with TTL1, that packet has TTL expiry on the first hop router, then with TTL2, that packet has a TTL expiry on the second hop router, and so on. So in the end, you have a nice trace route output, but now you can also see the labels that were on top of the packet for which the TTL has expired. What would happen if at the egress side, we copy the MPLS TTL down into the IP header, disregarding the rule? Well, the following could happen. Imagine that on router A, you put a command so that the IP TTL is not copied into the MPLS TTL header. In that case, the TTL value in the labels is 255, the maximum value. That packet is forwarded throughout the network and arrives at router D. What will happen at router D, the egress LSR of the LSP? Well, if we would disregard all the rules, then this TTL value, -1, which is 255, would be copied down into the IP header, even though that value is much bigger than the TTL value inside the IP header, which is 15. Now, in reality, this will not occur. We do not do this. But if it were to happen, then this IP packet might be routed back to the ingress LSR, LSR A, and there the IP packet would have a TTL of 250. We still have this command. So now again, we put a label stack on top of this IP packet, and the TTL is 255 in all the labels. So now the packet is back where it was in the beginning, and it will follow the same path again and again and again. So we have a routing loop, and the TTL would not expire in that case. So that's very bad. So that's why we have this rule that at the egress LSR, we will not copy down the TTL value of the top label, -1, if it is bigger than the TTL value in the IP header. Hello and welcome to lesson 4. Now we are really getting into the details that matter when it comes to learning MPLS. The first main architectural pillar to learn is LDP, or the Label Distribution Protocol. I'll explain how LDP sessions are built from scratch, the LDP discovery process, the session establishment, and how the lib and LFIP tables are created. These two tables are important in getting the MPLS packets forwarded. The LFIP, or Label Forwarding Instance Base, is the main goal here, because the router needs to forward MPLS packets in the end. I'll also briefly touch on label binding filtering and LDP session protection. Let's have a look at LDP operation. So what are some of the basics for LDP? Well, the whole idea of LDP is to make sure that all the LSRs are ready to forward labeled packets. To be able to do that, they must have the knowledge of labels. They must know which labels to put on the packets to be able to forward them. One solution is LDP, Label Distribution Protocol. This protocol, its sole purpose is to advertise labels. So it will actually advertise label bindings. A label binding is a prefix plus a label. It's IGP independent, so it's protocol independent. No matter what the protocol is that you are running, OSPF, ISIS, EIGRP, even static routing, LDP is the protocol that advertises labels. And it will only advertise labels for the IGP prefixes. It will never advertise labels, for example, for BGP prefixes, because that's what BGP does itself. It always installs a local label. So for every IGP prefix there is, LDP will install one local label. That's the incoming label for the LSP. It will advertise those local labels to all its LDP neighbors. So once it has formed LDP neighbors or adjacencies with its directly connected neighbors, it will advertise labels or label bindings to all those neighbors. And it will store the label bindings, so the prefixes plus the labels, in a table that we call the lib, the label information base. In the end, all of this is used for one purpose and one purpose only. It is to build the forwarding table for labeled packets, which is the LFIP. So the label forwarding instance base is built from information that we get from the lib. Basically, in the LFIP, we will, for every prefix, install one local label and one outgoing label. With that information, we are able to forward packets coming in labeled, and the router will be able to forward them out, of course, with another label. LDP has 4 major functions or building blocks. First of all, it needs to discover who its neighbors are. And for that, it will advertise a few packets to figure out who are the neighboring routers of the particular LSR. After it has discovered who the neighbors are, it will set up a TCP session or an LDP session with each of those neighbors. And once that TCP session is set up, it will advertise its label binding, so the prefixes plus the associate label, to every single one of its neighbors. And finally, once the session is set up, there will be some housekeeping. There will be some maintenance to check if the session is still up. If there is something that occurs which was not expected, there is some mechanisms to do notification. So basically LDP will be able to send error messages as well. So the first building block is the discovery. Basically, as soon as you have configured LDP, as soon as it's enabled on the router, LDP will start to send out link hello messages. And those messages are only sent on the link itself. That's why the destination IP address of those packets is 224.0.0.2. It basically means that these packets will be going out with a hop count of 1, the TTL is 1, so it will go only one hop far, and those messages are UDP. and its port is 646. Basically, by default, every router will send out a hello every 5 seconds, and the hold timer is 15 seconds. That means if any router does not receive a hello packet for 15 seconds, so if it misses 3 consecutive hello messages, then that neighborship is declared down. One of the main purposes of advertising these link UDP messages is to make sure that the neighboring routers have the transport IP address. The transport IP address is important because it's this IP address which is inside those UDP hello messages, which will be later on used to set up the TCP session between two neighboring routers. And most of the time, the transport IP address is actually a loopback IP address of the router. If the hold time expires for one link, that link will be removed from the LDP discovery list. So basically, a router will keep a list of all the neighbors being discovered per link. If the hold timer expires for one link, then typically that link will be removed from the discovery sources list. However, it's possible that there is a parallel pair of links between a pair of routers. In that case, if only one of the two links goes away, that link will be removed from the discovery link, but the TCP session, the LDP session, will still be kept up on the remaining link. However, if both of the links are gone from the discovery list, that's the end of the story. The LDP session will be torn down. So then we have the next step, which is the session establishment and maintenance. Basically, once the two LDP routers have learned of the transport IP address of the neighboring router, they will set up a TCP session to that neighboring router. So typically that will be a TCP session between the two loopback IP addresses of the routers. Also here for the TCP session, the ports used are 646. Again, like I just mentioned on the previous slide, if the last link goes away from the discovery list, actually the TCP session will be torn down. But the TCP session has its own protection as well. Basically, there will be a keep alive timer, and there will be hellos sent on top of the TCP session as well. If no hello was received for 60 seconds, then the TCP session will be torn down as well. It really doesn't matter how many links you have between a pair of routers. It could be 1, 2, 3 or more. You will only have one TCP session between the loopback IP addresses of the pair of routers. And then the important point, that's the whole purpose of LDP, they need to advertise, send to each other LDP messages. And the most important one is the label mapping advertisement. These are the actual label bindings which are sent from router to router. And a label binding, again, is a prefix plus a label. That's the whole purpose of LDP. There are some other messages, for example, like a label withdraw. If something changes, it might be that it needs to withdraw the label or the label binding. Typically, that will happen when the prefix is removed or the local label, for whatever reason, changes. So how do we create the LFIP? So LDP is a must-to-have to advertise labels. Once the labels are advertised, every router for every IGP prefix will have a local label and one or more remote labels. But in the end, to build the LFIP, we need for every IGP prefix one local label and one remote label. And then we can forward traffic over that LSP. How is that actually built? Well, we actually have 4 components here. The 3 components, the lib, the rib, the routing table, and the LDP neighborships or peers, together will be used to form the LFIP. Let's have a look at how it works. So we start off by receiving LDP bindings. As you can see here, for this prefix 10.254.4/32. LDP assigned a local label. Alright, so for this prefix, we already have a local label, label 20. We can install that in the LFIP. We still need the remote label, and that's a bit more complicated to find out. We know the prefix, so we go into the routing table and we find the prefix. What else do we have there? Well, the outgoing interface. The outgoing interface here can now be installed in the LFIP as the outgoing interface. So we know now which interface to forward the packet on to, but we still don't know the outgoing label. We know that the prefix has a next hop IP address in the routing table. We can find that next hop IP address back attached to one of the LDP peers. So basically, in the list of the LDP peers or neighbors, we have to scan for that IP address. And there is a list here, addresses bound to peers. Every LDP neighbor will advertise a list of IP addresses. Those are the link IP addresses bound or attached to that neighbor. Eventually, for one of the LDP peers, that IP address, which is the next hop IP address in the routing table, is found. Now we can deduce who is the LDP neighbor. This is the neighbor, 10.200.254.3. Once we know the neighbor, we go back into the lib. The labels are stored, and we can find that LDP peer in the list. And for that peer, we have an associated label that we received, a remote label. That remote label will now be used in the LFIP as the outgoing label for the entry. So now the LFIP entry is complete for the IGP prefix. We have an incoming label, an outgoing label, and an outgoing interface. We can start to forward label traffic for that entry. How does it work on a network? Well, each router will have to build an LFIP. Again, LDP will be used here. We'll have a look at the prefix 10.1.1.0/24. Basically, when we look at the routers closest to the destination, they will start off by building a local label. In this case, router D has local label 99, router E has local label 18. That label, plus the prefix of course, will be sent as a label binding to the upstream router, router C. Router C will now install an outgoing label over that interface towards that LDP peer. And it will do the same for the prefix binding it got from router E. However, when router C looks in the routing table, it figures out that only one of the two entries is the best one according to the routing table. In the routing table, we'll only store the best routes. So we can eliminate the label binding we received out of interface 2. Alright, router C will now pick a local label, label 23, and advertise that with the label binding towards router B. Router B now learns what the outgoing label is, label 23, and installs that as an outgoing label in the LFIP for that prefix. In its turn, it will assign a local label and advertise that upstream towards router A. So router A now has incoming and outgoing label and an outgoing interface for the prefix, and the same is true for every other router that you see here. So now we can start forwarding traffic from beginning to end. When router A receives a packet with label 311 on top of it, it will just do a label swap the label with label 19, forward the packet onwards, and so on, until the packet reaches D. So now every router, every intermediate router can just do label swapping, and the packet will reach from the beginning of the LSP to the end of the LSP by just doing a label swap at each hop. And finally, we discussed about LDP sessions. LDP sessions are really, by default, only set up between neighboring routers, directly connected neighboring routers. So one hop away, just one link is between the two routers. However, there's also something what is called a targeted LDP session. That's an LDP session or adjacency or neighborship, if you want to call it that, between routers which are multiple hops away. Now there is no easy way for those routers to discover each other. So that's why it is something that actually must be configured manually. They are sometimes used, it's not that frequent, but some of the scenarios where you might see targeted LDP sessions are MPLS VPN with TE tunnels, remote protection if LFA, loop-free alternate, is used, and there are a few other examples. Typically, explicit CLI is needed to configure this. So there's a command, in this case the iOS command is MPLS LDP neighbor targeted. And you have to specify the IP address, typically the loopback IP address of the remote neighbor that you have to configure. And you basically have to configure this command on both routers. So in this case, this command was configured on router A and router B. Once it's configured on both routers, a targeted LDP session, so multiple hops, a targeted LDP session will be set up. Let's have a look at the LDP operation in the live demo. So here we are with our network again. We are looking at MPLS forwarding, of course, but now we will have a detailed look at LDP. Let's first look at the discovery of the neighbors. We'll have a look at router 1 and see how it discovered its neighbors. we see that router 1 has 4 links. 2 of the links go to router 2, 1 link goes to router 7, and 1 link goes to R6. So what about the discovery? Well, there's a show command to look at that. Show MPLS LDP discovery. And we see that indeed router 1 discovered 4 links. But on gigabit 01 and 04, it's actually the same LDP peer that we discovered. So in total, we have 3 different LDP peers here. And we are sending, transmitting, and receiving the LDP link hello messages. And the router ID of this router is 10.100.1.1, which is just the loopback IP address of this box. You can do the same command with detail. Then you see a little bit more information. You can see the hello interval of the link UDP hellos, 5 seconds. You see the transported IP address, which is typically the loopback, the highest loopback IP address on the router. Its router ID, the hold timer, 15 seconds, which is the default, and some other information. Do we form neighborships? Well, we can do show MPLS LDP neighbor, and we see that indeed we have 3 different neighbors or peers, the one to router 2, one to router 6, and one to router 7. We are sending and receiving messages, so everything looks fine. For the peer router 2, we actually have 2 discovery sources, 2 links. And remember what I said in the slides, we also have these addresses bound to LDP, which is needed in the end to build the LFIP. So in the end, we have the discovery process, we have LDP neighborship set up between this router and its directly connected neighbors. But what about a targeted LDP session? There's no targeted LDP session here, but you could set that up. Let's have a look. We might set up a targeted LDP session between router 1 and router 4 example. Let's try to do that. So let's configure a targeted LDP. We go to configuration mode, MPLS LDP neighbor, the IP address of the remote router of router 4, so it's 10.100.1.4, and we put the targeted keyword. Do we now have a peer already, an LDP peer with router 4? Let's have a look. We first look at the discovery. We now see targeted hellos. It's active and we are transmitting, sending hellos, but we are not receiving. So the peer is not up yet, and the reason is router 4 is not sending the hellos back to router 1. So we need to do something at router 4 as well. So let's do that. There are actually 2 things we could do here. We could configure the same command as on router 1 on router 4, and the neighborship or the targeted neighborship would come up. Or there is another command, MPLS LDP discovery targeted hello accept. And now it will accept incoming requests from router 1. It should take a couple of seconds before the peering is established. There it is. So now we have a neighborship which is up between router 1 and router 4. Let's check again. Discovery, yes. Between router 1 and router 4, we are sending and receiving UDP hellos. Now it's multi-hop, of course. And with show MPLS LDP neighbor, we now see that between router 1 and router 4, we actually have, instead of a link here under the discovery sources, we have targeted hello between router 1 and router 4. That's how you set up a targeted LDP session. Let's have a look at label advertisement control by LDP. We can do label advertisement control. We can actually do it in 2 ways, either in the outbound direction or in the inbound direction. Now you might think, why is this needed? Well, by default, LDP will advertise a label binding for all its IGP prefixes. You might have a lot of IGP prefixes in your routing table, so to make it more scalable, you might want to be more specific and say only advertise the label bindings for the prefixes for which it's really needed. And typically, in an MPLS VPN network, for example, you really only need to advertise LDP bindings, label bindings by LDP for the loopback IP addresses of the PE routers, because those loopback IP addresses are the BGP next hop addresses for the service prefixes. And those are the only one which will carry the customer traffic end to end. So we can do it in two ways, outbound or inbound. Outbound, you will have to configure a command on the router, in this case MPLS LDP advertise label, and then you specify basically a prefix or access list, specifying which prefixes only to advertise. And after the to keyword, you can again specify an access list, specifying to which peers you make that restriction. So the command would look like, as you can see here in the example, MPLS LDP advertise labels for access list 1 to access list 2. And then access list 1 would just hold a set of prefixes for which you would advertise the label binding. Access list 2 would hold the number of peers to which you restrict the label advertisement. The only thing is, in iOS, you must not forget to configure no MPLS LDP advertise labels, otherwise the router will, in any case, always advertise all labels, even though you might have configured this first command, MPLS LDP advertise labels. The second possibility is filtering in the inbound direction. You can filter incoming label bindings. So the router might receive incoming label bindings, but it will filter them out. And the ones who are filtered out, the router will not install those label bindings into the lib, the label information base. How would you do that? For that to work, you would have to configure the command MPLS LDP neighbor with the labels accept keyword and an access list. Here's an example. MPLS LDP neighbor. From that neighbor, you restrict incoming label bindings. How? Well, according to the access list 1. In access list 1, you would specify for which IGP prefixes you accept the incoming label bindings. For all the other ones, you would deny the incoming label bindings. Let's have a look at LDP session protection. We have something called LDP session protection. It means that we have a TCP session, which is the LDP session, between neighboring routers. If the link goes down, then by default the LDP session over the TCP session will go down as well. Now we can actually protect that, meaning even if the links go down, we can keep up that LDP session over TCP over an alternate path. Now, what would be the point? Well, sometimes we have links flapping, sometimes even rapidly in a network. So a link can go down and go back up pretty quickly. When the links go down, the LDP session can go down pretty quickly. When the links come back up, the LDP session will come back up as well, but this will take time because a TCP session needs to be established, and then we need to advertise label bindings across this LDP session. If you have a lot of IGP routes, it can take quite a bit of time to send all those label bindings across the LDP session. In the meantime, before all the LDP label bindings have been exchanged between neighboring routers, the packet forwarding can already start. It is possible that the IP routing convergence is pretty quick, so quick that it has converged before LDP session has finished sending all the label bindings between a pair of neighboring routers. In that case, it's possible that the packet's forwarding starts to occur again over the link that came back up, but then the outgoing packets will be IP packets and not labeled packets. And that will cause a problem, because for a lot of services, we must make sure that all the labeled packets are sent from ingress to egress routers over an uninterrupted LSP, meaning there is no possibility to have a link somewhere along the LSP where the packets become unlabeled. If that were to occur, the LSR could attempt to do an IP lookup of the destination IP address in the IP header, but sometimes that will fail, as we have seen before. So the LSP must be uninterrupted. So to prevent this from happening, we have something what is called LDP session protection, and we will keep up the session even though the link is down. The purpose is, once the link comes back up, the LDP session has already been established, be it over an alternate link. When the link comes back up, then we will just switch the LDP session from the alternate path back to that link that has just come up. That will speed up the convergence, that will speed up the forwarding of the labeled packets again once the link is back up. Let's have a look at an example. We have an LSP here from router 1 to router 4. The packets are label switched from router 1 to router 4 over the intermediate routers, router 2 and router 3. It is possible that the link between router 2 and 3 goes down. A little bit later, the link can go back up, but as soon as the routing protocol, be it OSPF or ISIS for example, has converged, we will create an entry in the routing table, but also in the LFIP. But now, for the incoming label 26, we have no outgoing label. That means that when a labeled packet arrives at router 2 with label 26 at the top, it will be forwarded as an IP packet out towards router 3. But that means that the LSP has been interrupted, and that's not what we want. So what's the solution? We will have LDP session protection. If that link between router 2 and 3 goes down, that LDP session will be kept up. Not over this link, it is right now, but it will be kept up over router 4. So a multi-hop session. It will be a targeted LDP session, which is automatically created. So this LDP session from directly connected becomes a targeted LDP session, just because you have enabled LDP session protection. For the moment, nothing occurs, but when the link comes back up, then as soon as the routing protocol has converged, the packets can be switched out again over this link, and the packets will be labeled because the LDP session between router 2 and 3 has been kept up. All the label bindings on router 2 are still there from router 3. So there's no need to exchange the label binding again over a newly established LDP session. The LDP session between router 2 and router 3 has been kept up at all times. Let's have a look at LDP session protection in the live demo. So let's have a look again at our lab setup here. We are going to look at router 1 and the LDP session towards router 7. We have an interface between them, of course. So right now we have an LDP session between router 1 and router 7, but it's directly connected. So let's pull up router 1 and let's see what we have. So show MPLS LDP neighbor 10.100.1.7 detail, and let's see what we have. We have a session, it's up of course, and we have one discovery source, it's gigabit Ethernet 0/2. So there is a session there, but it's directly connected. So we want protection, so let's configure that. MPLS LDP session protection. Do we have protection now? Let's have a look. Show MPLS LDP neighbor detail again. And it says protection is enabled, but state is incomplete. Now, why does it say that? Well, session protection is something that needs to be bidirectional. So we'll have to configure the same on router 7 as well. Let's do that. So on router 7, we have to configure LDP session protection as well. There we go. So let's have a look now what we have on router 1. Same command again, neighbor detail, and we see that now protection is still enabled and the state is actually ready. So it's not active yet, the session protection is not active because we still have the session over the link, so a directly connected session over gigabit 0/2. So to check if it's working, we actually have to kill that link. So let's shut down the gigabit Ethernet 0/2 and let's see what happens. Shut down. Okay, routing protocol, OSPF in this case, goes down, interface goes down. Let's look at LDP again, and we see that the session is now in protecting state. So actually, this session between router 1 with its router ID 10.100.1.1 and router 7 with router ID 10.100.1.7 is kept up. How? Well, over an alternate path. So if on router 1 we would do show IP route 10.100.1.7, you would see that actually we have still 3 alternate routes, equal cost multipathing, to get to router 7. And you can see that on the topology, we have gigabit Ethernet 0/1/4 and /3 still available. So right now, the session is protected. We still have all the label bindings from router 7 available. We can check that. yes, we still have label bindings from router 7 available. So now if the link comes back up, we do a no-shut on gigabit 0/2, the LDP session will still be up and the conversions will be much, much faster. Hello and welcome to lesson 5. This is the big one. It's the most detailed and most important lesson in this course. MPLS VPN Layer 3 is by far the most popular MPLS service implemented by service providers and enterprise networks. This is why it's so important to discuss this topic in detail. I'll build it up gradually, starting with an overview and nailing down some definitions. Pay special attention to the sub-lessons on how the routing occurs in MPLS VPN Layer 3 and how the packet forwarding is done through the MPLS core. Those two things are a must to understand. I'll also cover the routing protocols between the core and customer routers, how internet connectivity is provided, and VRF Lite. I'll round it off by explaining how we provide IPv6 service as an MPLS VPN Layer 3 service. Let's start off with MPLS VPN with an introduction. Remember the VPN models? We had the overlay versus the peer-to-peer model. Now with MPLS VPN Layer 3, we have the peer-to-peer model. And that's really what made MPLS VPN Layer 3 an instant success. With the peer-to-peer model, we really have the customer routers have a direct Layer 3 connection with the provider edge routers, meaning they have a routing protocol adjacency. So it's all about VPNs, and VPN stands for Virtual Private Networking. So each customer is in its own context which is completely separate from any other context of other customers. So it's completely private. It's virtual because in the end, all of the traffic from the different customers go over this same MPLS network. MPLS VPN was the real killer app for MPLS. Back in the year 1999-2000, it was an absolute and instant success. And this is what made MPLS great and last so long. So let's have a look at some of the terminology with MPLS VPN Layer 3. Well, we have an MPLS enabled network, of course. We have what we call provider routers, P routers of the service provider. They're all MPLS enabled. Basically, at a minimum, you would need to run an IGP there, a routing protocol, and a label distribution protocol like LDP. And at the edge, we have provider edge routers, PE routers. They have a direct connection at layer 3, so routing protocol, with a customer router. And we call those routers CE routers for customer edge routers. So we will always have a direct connection at layer 3 between a PE and a CE router. Now on a PE router, we must make sure that every customer sits in its own virtual private network, its own VPN. And we do that by configuring a VRF, a virtual routing forwarding, on the specific interface. This command alone makes sure that each customer is in its own separate context. So for example, here we have on this PE router on the interface a VRF statement. It will say VRF red to make sure that the routers of the red customer are in the red context on the provider edge router. Equally so, on this link towards a green CE router, we will have a VRF statement saying this router is in the VRF green context on the PE router. So again, a couple of definitions which are important, which we actually just covered: the P router, the PE router, the CE router, and the C router. The C router is just a router of the customer, which does not have an interface with the PE router. Always we have a layer 3 adjacency, so routing protocol adjacency, between the PE and the CE router, over a VRF interface on the PE router. And we call that interface the PE-CE interface. Now it could be any routing protocol that we support, could be OSPF, eIGRP, static routing, BGP, or even a static route. The P in VPN stands for private. Now, it's absolutely important that customers in different VPNs can have their own addressing scheme. They can use whatever IP addresses, be it IPv4 or IPv6, that they want. It could even be that they use private IP addresses, which are typically IP addresses which are mentioned in RFC 1918. Examples are the 10/8 network range and the 192.168 network range. Those IP addresses are never leaked into the global context of the service provider router. Also, whatever one customer has in its VPN, it will not be leaked out into the VPN, of course, of another customer. So two customers in their own VPN, they might even have overlapping IP address ranges. So it's possible that the customer VPN red and the customer VPN green actually use the same addressing schemes. For example, they have the same 10/8 IP addresses configured and in use. Very important is that on the PE router, we have a separate context for each VPN. And that context is the VRF, the virtual routing forwarding. We will have a context for the red VRF, one context for the green VRF, and so on. And in each context, which is separate from all the other contexts, we make sure that we have a routing table, so a RIB, and we have a forwarding table, a FIB or CEF table. So what about this VRF? Well, VRF stands for virtual routing and forwarding. It's just a terminology for something that you put on the router. It's how you configure the VPN context on a router. Specifically, you will have to put that as a minimum on the interface on the PE router towards a CE router to make sure that the customer routes or customer routers are belonging to a specific VRF context. Over that VRF context, we then have a layer 3 adjacency or routing protocol adjacency from the PE router to the CE router. But this is completely isolated. This is 100% only in that VRF context. There is never any leaking towards the global context or the context of any other VPN. Let's have a look at virtual routing and forwarding, or the VRF, in more detail. So on a PE router, we will have VRF. For every VPN, so for every customer on a PE router, we will have a VRF being configured. So the VRF, or the virtual routing and forwarding, is a concept. The concept being that we make sure that each customer, each company, sits inside its own virtual and unique context. That way, we can make sure that each customer in each VRF or VPN can have its own addressing scheme, which might be overlapping even with the addressing scheme of another customer, and make sure that the routing and forwarding to and from the MPLS network will work. Now, the VRF is only defined on a PE router, and it's defined globally and on the VRF interface towards the CE router of the customer, of course. On the CE router, we don't need to change anything. It doesn't need any special software, because on the CE router, it's just a router as we are used to. There's no VRFs, no VPN, no nothing. It's just everything in the global context as we are used to. In the end, the VRF is there to make sure that we can have routing and packet forwarding in the VRF context. So let's have a look at the PE router in more detail. On each interface towards a CE router, we will have to configure a VRF. And you can configure only one VRF per interface. And this command only, is what makes sure that this customer sits in its own VRF. So typically on an interface, you would configure VRF forwarding and then the VRF or VPN name. This command will make sure that whatever comes from this customer router, this CE router, is treated into the red context. We also have some global configuration for each VRF. Here we have VRF definition red, and then there are two important parts, the RD or route distinguisher and the route target. But both of these concepts are explained in a later lesson. So if we look at a PE router, we will still have the global context, of course. This is also sometimes referred to as the default context. So on a PE router, you can still do show IP route and look at the global or default routing table. You will see there the routing table that you are used to. But now we will also have a routing table per VRF. So if you do show IP route VRF red or show IP route VRF green, you will see that we have a routing table for the red VRF and one for the green VRF and so on. So we have one routing table per VRF, and it's completely isolated from any other VRF routing table or default routing table. And that routing table in the red or green VRF is actually exactly the same as a regular routing table. You have prefixes, so a route and a mask, you have interfaces, you have routing protocols, distances, metrics, and so on. It's a regular routing table, but it's completely isolated from any other VRF or the default routing table. And on top of that, we also have the forwarding table, which is the FIP table or CEF table. This is the table which is actually used to forward incoming packets from the VRF interfaces. So if you would do show IP CEF VRF red or show IP CEF VRF green, you would see that we also have a FIP or CEF table for the red VRF and the green VRF. So the FIP tables are also unique and isolated for each and every VPN or VRF we have connected to the PE routers. Let's have a look at route advertisement in MPLS VPN Layer 3 networks. We have here the important building blocks of MPLS VPN. We have already seen what VRF is and how it's being used, and it's a really important one, but there are three more. We have the route distinguisher, or RD, we have route targets, RT, and VPN v4 or VPN v6 prefixes. How are they used? Well, we have a route distinguisher. What is it used for? It's basically to make a customer route unique when we transport that customer route or VPN prefix across the MPLS VPN network. And that's more or less the only thing it does. There's no other implication than making the route unique. When you configure a VRF, you will have to assign a route distinguisher or RD to it. And you will have to make sure that this route distinguisher is unique on that PE router. Other VRFs on the same PE router cannot have the same route distinguisher. In fact, if you try to configure that, the router will complain about it. This route distinguisher is also used to uniquely identify the VRF table, so the context of the VRF or VPN. The route distinguisher is always a 64-bit value, and this 64-bit value will be used as an attachment to the IPv4 or IPv6 prefix of the customer VPN. And that's what makes the customer prefixes unique. There are actually three formats possible for the route distinguisher. The first format is ASN:NN, or Autonomous System Number: number. That's the type 0 for RD. In that case, the autonomous system number is a 2-byte autonomous system number, so 16 bits. So that means that the value is smaller than 65,536. And there is an example of that on the right-hand side. The second format is type 1. This is IPv4 address: number. So it's typically an IPv4 address of that specific VPN or VRF customer plus whatever number. And there is an example of that on the right-hand side. The third format is actually a 4-byte ASN number: number. So the autonomous system number here is 4 bytes, 32 bits, so it's actually a number which is bigger than 65,535. That's the type 2 RD format, and there is an example of that on the right-hand side as well. How is the route distinguisher used? Well, it's used to make a VPN, v4 or v6 prefix. We will use the route distinguisher as a unique value to be attached to the IPv4 address. A route distinguisher plus an IPv4 address makes a VPN v4 address. You can see an example here on the right-hand side. We have the route distinguisher 1:2 and then the IPv4 address. So together, this is an example of a VPN v4 prefix. This route distinguisher has just one purpose: make the prefix unique when we transport the prefix across the MPLS VPN network, because it is possible that another VPN customer is using the same IP addressing scheme, so it might have the same prefix in that VRF. but then the route distinguisher will be different. For IPv6, it's the same thing. We'll have an IPv6 address with a route distinguisher in front of it. So again, 64 bits for the route distinguisher, but now 128 bits for the IPv6 address. And here we have the example. The route distinguisher is again 1:2, and then behind the second colon we have the IPv6 address, which could be 128 bits long. This VPN v4 or VPN v6 prefix will be transported by multi-protocol BGP from one PE router to the other PE router. So that's how we transport the VPN or VRF routes of the customers from edge to edge, from PE router to PE router. It's through iBGP or internal BGP, multi-protocol BGP. It could be a full mesh of iBGP, so full mesh between the PE routers, or it could be from PE router to route reflector and back to another PE router. What is a route target? A route target is also a very important concept. We have seen that the route distinguisher makes the routes unique. But now we need to guide the routes from and to the correct VRFs when we transport the routes from PE to PE router. How do we do that? Well, we kind of have two concepts. We have the route target importing and route target exporting. And the route target is really just another extended community of BGP. It is something that gets attached to BGP prefixes. In this case, we are carrying VPN v4 or VPN v6 prefixes from PE router to PE router. So we are going to attach one or more of these route targets to the routes, to the VPN v4 and VPN v6 routes. Here's the global configuration of a VRF red. You configure the route distinguisher to make the route unique, but we also configure route targets, import and export. Why? Well, route target export means that we would attach that particular route target, which is an extended community, in this case the value is 1:2 as well, to the VPN v4 or VPN v6 prefixes when we send it out through iBGP to the remote PE routers. So exporting the route target is all about attaching the route targets, one or more, to the specific VPN v4 or v6 route. What is importing the route targets? Importing the route targets, it's all about trying to match a route target which is attached to a VPN v4 or VPN v6 prefix with what you have configured as an import statement under the VRF. So for example, if here for VRF definition red you have a route target import 1:2 statement, it means we look at the received iBGP VPN v4 or VPN v6 prefix. We see if a route target 1:2 is attached or not. If it's not attached, we will not import or put the IPv4 prefix inside the VRF table. The IPv4 prefix is the VPN v4 prefix, but the route distinguisher has been stripped off. If there is a match, so if there is such a route target 1:2 attached to the VPN v4 prefix, then we take the VPN v4 prefix, strip off the route target, and put the remaining part, which is the IPv4 address or route, into the VRF routing table. In this case, the VRF routing table red. So the import has succeeded here. So the route target is really about route propagation guidance. Which route target do we attach to a VPN v4 prefix when we send a prefix out? And importing means which VPN v4 prefix, or at least the IPv4 part of it, do we put in the specific VRF routing table. So how does the route propagation work? Well, in this case here, when you look at the slide, we have three VPNs, a red, a green, and a blue one. And they will try to advertise three different IPv4 prefixes. This is the configuration we have on the left PE router. We have a VRF definition red with two export statements and one import statement. VRF green has one export statement, one import statement. VRF blue has one export and one import statement. Now we really care on this side only about the export statements, because that would tell the router which route target to attach to the iBGP VPN v4 prefix that we advertise. So let's have a look. When the PE router advertises the red prefix, it will take the IPv4 address 10930 with a mask of /24, with a mask of /25, put the route distinguisher of 1:2 in front of it. That's the VPN-v4 prefix. And then because we have two export statements for VRF red, export 1:2 and 1:9, he will attach those two route targets to the VPN-v4 prefix. And this will be sent to all the remote PE routers. If you look at the PE router on the right-hand side, he will receive that VPN-v4 prefix. He will look for the route targets attached and will find that, oh, there is a route target 1:2 attached. And if I look at the VRF red, I do import that route target 1:2. He will take that VPN-v4 prefix, strip off the route distinguisher and install that IPv4 route in the red VRF routing table. It's important to notice that you can have multiple route targets attached to a VPN-v4 prefix. But on the receiving side, it is enough for the PE to find one matching route target as an import statement. If he finds at least one import route target that matches, he will take the IPv4 prefix and install that in the specific VRF routing table. Let's have a look at VPN green. The PE router on the left-hand side advertises that prefix with a route distinguisher 1:3 and then attaches one route target 1:100 because that's the export statement. On the receiving side, so the PE router on the right-hand side, he will try to match this attached route target of 1:100 with all the VRFs here with the import statements. He doesn't find any VRF which imports route target 1:100. Basically, this PE router is just going to drop the VPN-v4 route and not install the IPv4 part of it into any VRF routing table. For VRF blue, the left-hand PE router advertises this prefix with route distinguisher 1:4 in front of it. He has one export statement, so he attaches the route target 1:200 to the VPN-v4 prefix. The receiving PE router on the right-hand side receives that VPN-v4 prefix, tries to match route target 1:200 with all the VRFs, doesn't find any import statement, so again, this PE router will actually drop that prefix and will not install it into any VRF routing table. The point here is that you will have to be careful with the route targets that you configure. You can see here that on the left and on the right-hand side, you have a VPN green site, but the green prefix, which was advertised from the left-hand side to the right-hand side, actually does not get installed into the green VRF on the right-hand side. And that's because the green VRF on the right-hand side did not import route target 1:100. One more thing is about VPN extranet. Usually, we have VPN intranet. Now, what is VPN intranet? Typically, the sites of one customer or one VPN is allowed to communicate to the other sites of the same customer or VPN. For example, all the red sites can communicate to any other red site. In some cases, even if we have two different companies, so two different VPNs, we might want the sites of different companies of VPN be allowed to communicate with each other. Is that possible? Yes. You would just have to play with the route target import and export control and set it up in such a way that this communication between VRFs is allowed. And that's why we call it extranet VPN. So in this case, we have a red VPN configured and a green VPN. The red VPN typically imports and exports the route target 1:2. The green VRF or VPN typically imports and exports 1:3. Now, if you would stop there, then any red site cannot communicate with any other green site. There is no extranet. To make it extranet, on the red VRF, we configure route target import and then the green route target, which is 1:3. So now the red VPN sites, they can import the green routes. Equally so, on the green VRFs, we configure the extra import command 1:2. So route target 1:2 can be imported into the green VRFs. But this is the route target used by the red VRFs. So now the green VRS or VPN routers, they can receive the prefixes from the red VPN. Once you have both of these extra configurations, one for the VRF red, one for the VRF green, then sites from the red VPN can communicate to the sites of the green VPN, and hence we have VPN extranet. Let's have a look at route advertisement and MPLS VPN Layer 3 networks in the live demo. So let's have a look at route propagation in the lab. We have a new network here, which depicts an MPLS VPN network. We have 2 core or P routers, we have 2 PE routers, and on each side we have a VPN site, a VRF red site with 1 CE router. We also have a backdoor link, which does use the MPLS core, but we will not talk about that now. So let's have a look at router PE1 and see what we have there. Let's first have a look at the configuration for the VRF red. So we can do show run VRF red. What do we see? We see that we configured a route distinguisher 1.2 for the VRF, and we import-export the route targets 1:100. Now you can configure this route targets import-export statements globally, so both for IPv4 and IPv6, or you can have a different set for IPv4 versus IPv6. And the other important part, of course, is configuring the VRF interface. So we configure this interface, gigabit 0/1, which is the interface towards CE1, to be part of the red VRF. So what else do we have? Well, now PE1 and PE2, they will start advertising the VPN v4 prefixes to each other. Let's have a look at that. Show BGP, VPN v4, unicast, all summary. We see that PE1 has one neighbor. It's PE2, it's 10.100.1.2, the loopback of PE2. We have a session which is up, and we received 4 VPN v4 unicast prefixes. Let's have a look at those prefixes. So we remove the summary keyword, and we see those prefixes here. Now they're really VPN v4 prefixes, because if you put this route distinguisher together with the prefixes that we have, this will make up the VPN v4 prefix. Let's have a look at such a prefix in more detail. Let's have a look at PE1 for the prefix which is remote 10.2.2.0/24, which is the prefix that we already see here, this one. We need to specify the route distinguisher 1.2 and then the prefix. There we go. What do we see? The next hop is 10.100.1.2, the loopback of PE2. We have a bunch of extended communities here. The only one we care about is the route target, and we see that the attached route target is 1:100. This route target was attached by PE2. So on PE2 we had an export statement for route target 1:100. Also important is the label attached by PE2. We have a label here 21. This is the MPLS label attached to the VPN v4 route by PE2. And finally, we do have a routing table which is isolated per VRF, so we can do a show IP route VRF red here and see that we have installed those routes after stripping off the route distinguisher, of course, installing those IPv4 routes in the VRF red routing table. And it looks like a regular routing table that we are used to. Let's have a look at packet forwarding in MPLS VPN Layer 3 networks. So what about the forwarding? Well, the P routers are not going to have VPN routing tables. That wouldn't make it scalable anyway. Plus it would be a burden on how to forward those packets. We could have had every private routing table for every customer on every P and PE router. That would have been very difficult. Each time one VPN would have been added to the network, a new routing protocol would have been added to every P router. So obviously that's not very scalable. Furthermore, if an IP packet enters a P router, how would the P router determine which VPN the packet belongs to in order to figure out which private routing table to use to forward the packet? If the packet is an IP packet, it's not really possible. One could add an extra field to the IP packet indicating what the VPN of the IP packet belongs to. Then the P router could then forward the IP packet based on this extra field and together with the destination IP address. Again, all P routers would then have to be aware of this extra field. So that's not really scalable. What is scalable is to use MPLS VPN, of course. So we're going to use MPLS forwarding in the core of the network. And as I explain in more detail on the next slide, the customer IP packets will be labeled in the service provider's network in order to achieve a VPN that is private for each customer. Furthermore, the P routers will not need to have the routing tables of the customers anymore by using two labels for the forwarding. BGP will not be needed on the P routers at all. The VPN routes will only be known on the PE routers, on the edge routers. As such, the VPN knowledge is only present on the edge routers of the MPLS VPN networks. And this makes the MPLS VPN solution very scalable. What about the forwarding? Well, the forwarding will be based on two labels. We cannot really forward the packets as pure IP packets between the sites. The P routers would not be able to forward them as they do not have the VRF information for each and every site. MPLS can solve this problem. We're going to label the packets. The P routers must then only have the correct forwarding information for the label in order to forward the packets. The most common way is to configure LDP between all the P and PE routers so that all IP traffic is label switched between them. RSVP with extension for traffic engineering could be used as well when implementing MPLS traffic engineering, but LDP by far is the most common for MPLS VPN. The IP packets would then be label forwarded with one label from ingress router to egress PE router. A P router would never have to perform a lookup of the destination IP address. This is how the packets are switched between the ingress PE and the egress PE router. This label is called the IGP label, as it is the label bound to an IPv4 prefix in a global routing table of a P and PE router and is advertised by the IGP of the service provider network. Okay, so that's solved. Now, how does the egress PE router know which VRF the packet belongs to? This information is not in the IP header, nor can it be derived from the IGP label, as this is used solely to forward the packet through the service provider network. The solution is to have another label in the MPLS label stack. This label indicates which VRF the packet belongs to. So all customer packets will be forwarded with two labels, the IGP label as a top label and the VPN label as the bottom label. The VPN label must be put on by the ingress PE router to indicate to the egress PE router which VRF the packet belongs to. So how does the egress PE router signal to the ingress PE router which label to use for a VRF prefix? Since multi-protocol BGP is already used to advertise the VPN v4 prefix, it will also be used to signal the VPN label, sometimes also referred to as the BGP label. Let's have a look at an example of end-to-end packet forwarding. On the left-hand side, we have a site inside VPN red, and we have a prefix 10.9.3.0/25. This will be advertised towards the remote PE routers by adding the route distinguisher 1:2 and adding an MPLS label, the VPN label, label 17. And the next hop will be the BGP next hop IP address, which is the loopback 10.100.1/32 of the PE router. On the remote router, we will receive this VPN v4 prefix and see it with the associated VPN label, label 17. In the routing table of VRF red, we will install the prefix and the next hop, which is 10.100.1.1, which is the loopback of the remote PE router. Also, LDP will advertise the label bindings from egress towards ingress PE router. We always advertise the prefix, which is the BGP loopback address plus the label. In the end, when a packet arrives at the ingress PE router, we will do a lookup in the VRF routing table. Actually, the lookup will happen in the VRF FIP table or CEF table. And we can see in the VRF red FIP table or CEF table that for this particular prefix, we will add two MPLS labels. The top label is the label 81, which is the IGP or LDP label, and the bottom label is the VPN or BGP label, which was received through the VPN v4 prefix. Alright, so we put two labels on top of the packet, and we forward the packet into the MPLS VPN network. At each P router, we just swap the top label based according to the entry in the LFIP. At the last hop router, we do penultimate hop popping, so we pop off the top label and we are left solely with the VPN label. At the egress PE router, we just do a lookup of this VPN label, which is also present in the LFIP. We strip off the label and then forward the packet onwards towards the CE router. So that's how the forwarding works in an MPLS VPN network. Let's have a look at packet forwarding in the live demo. Let's have a look again at our lab when looking at the packet forwarding in an MPLS VPN network. We have the same network as we had in the previous lesson. Forget about the backdoor link. We have an MPLS VPN network with one VRF red connected at both sides of the network. We're just going to have a look at router P1 for the prefix it received from the remote PE router from the VRF side. So we will look at the prefix 10.2.2.0/24. Let's have a look. Do we have it in our routing table? Yes, we do. Here it is. And the next hop is 10.100.1.2, which is the loopback of router P2. How did we get it? Well, remember the previous lesson, we received it through BGP VPN v4 unicast. Here is the unicast route. We see that the next hop is of course still the loopback of router P2. We have the route targets and so on, but the important thing is that we have the VPN label. It's labeled 21. So when we put the route from the routing table into the forwarding table or the CEF table, this label, label 21, will be the VPN label. The IGP label will be the label to get to the remote egress PE router P2. So it will be the label associated with 10.100.1.2. Which label is that? Well, let's have a look. Show MPLS LDP binding for 10.100.1.2. It's a loopback, so /32. And we see that the label used will be label 19. So what do we have in the CEF table? Show IP CEF VRF red for the prefix 10.2.2.0/24. And indeed that we see that we put two labels on top of packets that need to go to that destination. We have the IGP label 19, which we saw came from the LDP binding, and we have the label 21, which was the one received from the VPN v4 prefix. So actually you can verify that. If you would do a trace route inside the VRF for the prefix, you can actually see that indeed those two labels are used for forwarding the packet. So when the packet is forwarded out of PU1, those are the two labels that are put on top of the packet. And we can see that we just do label swapping at each P router towards the end. Let's have a look at the PE/CE routing protocols for MPLS VPN Layer 3 networks. Well, we have a lot of possibilities, a lot of options. More or less any routing protocol can be used on a PE router on the VRF interface to form a routing adjacency with the CE router. We can have connected routes, static routes, RIP, only version 2, enhanced IGP, OSPF, and BGP. Let's have a look at those in more detail. Obviously, we have the connected routes, so the PE/CE interfaces, they will have an IP address on it. These IP addresses will show up as connected prefixes in the routing table, in the VRF routing table. Those prefixes can also be redistributed by BGP as VPN v4 routes, but in order to have this, you must make sure that under router BGP, under the address family IPv4 VRF, you put the redistribute connected commands. We have static routes. So you can configure a static route directly into the VRF. For example, IP route VRF red, and then the prefix with an interface and optionally also a next hop IP address. Again, if you want this static route to be advertised by BGP as a VPN v4 route, you have to configure redistribute static under BGP under the address family IPv4 VRF. We can have RIP version 2 it's router RIP and then address family IPv4 VRF. You can configure network statements, whatever you normally configure with RIP. But if you want the RIP routes, so the routes learned on the PE router through RIP across the VRF interface to be redistributed as VPNv4 routes, you need to configure redistribute BGP. Equally so, if you want the VPNv4 learned routes to be advertised by RIP, you need to configure redistribute RIP under address family IPv4 VRF under BGP. OSPF, we can configure a specific OSPF process for the VRF. And there you can put the usual commands, enable interfaces for OSPF, put the network statement, and so on. Again here, if you want the OSPF learned routes from across the VRF advertised as VPNv4 routes, you must have the redistribute OSPF command for the specific VRF under router BGP. And vice versa, if you want the VPNv4 routes advertised by OSPF, you must have the redistribute BGP command under the OSPF VRF process. Now there are a couple of things which are specific to OSPF. If you just configure OSPF under the VRF and you redistribute OSPF to BGP and vice versa, then we will have a specific issue occurring. What is that issue? Let's assume on the VRF side on the left, the PE router receives OSPF prefixes. There will be a route type associated with that. It's either an OSPF inter-area or an external route. This route will be advertised through BGP VPNv4 across to the remote PE router. There, this BGP prefix will then be redistributed into OSPF and advertised through OSPF on the VRF interface towards the remote CE router. But when we redistribute a protocol into OSPF, that OSPF route type becomes external, always. The problem is that if on the VRF red side, on the right hand side, we have another way of learning these routes, then in OSPF we have a certain order of preference. You will always prefer intra-area routes over inter-area routes over external routes. So in this case, if that CE router of VPN red on the right hand side would also learn the same prefix but as an intra-area route through some other path, it would always prefer that route, the intra-area route, and never use the external route. So maybe that's something that we do not want, because in most of the time we would like to have the traffic being forwarded over the MPLS VPN network. So to avoid this, you would have to configure something that we call the sham link, and we'll see that later on. What about the metric propagation? Well, when we redistribute an OSPF route into BGP, the OSPF cost or metric will be copied into the MET, the multi-exit discriminator. And this MET value will be carried across from PE to PE through BGP. At the remote side, when we redistribute the route from BGP into OSPF, the cost used there will be the value from the MET. This is the default behavior. But be careful, if you configure a default metric, then the value of that default metric will be used as a cost of the OSPF route when it gets redistributed from BGP into OSPF. So back to our little problem when we redistribute OSPF routes into BGP and back into OSPF. Remember what the issue was? All of the OSPF routes will become external. And this could be a problem. Let's have a look. Again, on the left-hand side, we propagate an OSPF route. It could be an intra-area or inter-area type. It's carried across by BGP VPNv4, and at a remote PE, this VPNv4 prefix is then redistributed back into OSPF. But because we have redistribution, the route type becomes external. Now we also have a backdoor link. A link which is a native OSPF link between the CE routers of the two different sites. Here we just have OSPF flooding. So the same prefix will be flooded as an intra-area or inter-area route. This CE router of VPN red on the right hand side will now have learned the OSPF route twice. Once as an external route over the MPLS VPN cloud and once as an intra or inter-area route over the backdoor link. That CE router will always prefer the backdoor link because In OSPF, the rules say that you must always prefer the intra-area or inter-area routes over any external routes. So what is the solution for this? The solution is to configure a sham link. What is a sham link? A sham link is kind of a virtual OSPF link between PE routers. So it's really a multi-hop link. So this sham link is a link between the PE routers, and it supports the flooding of OSPF link state updates. So any kind of LSA link state advertisement is supported over this link. It's really like a virtual link. It's also an IP unnumbered link. It's like a demand circuit, so there's no periodic refresh flooding. The flooding typically only happens once, and it's a point-to-point link. But the main point is it supports the flooding of native OSPF link state advertisement. So again, if the PE router on the left-hand side would learn of an OSPF route, any type, inter-area or external, now this route would be flooded as an OSPF route to the right-hand side PE router. And the route type, whatever it was, is kept. So now when the PE router on the right-hand side floods this OSPF prefix to the CE router, we still have the original route type. So even now, if there was a backdoor link between the CE routers, the CE router would learn the prefix as, for example, an intra-area route over the MPLS VPN backbone and as an intra-area route over the backdoor link. And then the CE router could choose between either one of the two paths. There is another thing specific to OSPF, and that is the down bit. Let me explain what it is. When a PE router receives a VPN v4 prefix, it will redistribute it into OSPF and it could go to the CE router. Now, there is a possibility that this VRF site is dual homed. So there are two connections from CE routers to the PE routers. The other CE router might learn about the prefix through OSPF and then flood it through OSPF to the PE router. This PE router will now learn the OSPF prefix and might decide to redistribute it back into BGP. But this could cause issues. There could be suboptimal routing or even a routing loop here formed because of this. So what is the solution? The solution is using a down bit. Each time a VPN v4 prefix is learned and we redistribute the prefix into OSPF, then inside the OSPF LSA, the link state advertisement, we are going to set the down bit. And we do that for the LSA type trees, so the inter-area routes, and for the external routes, so the LSA type 5 route. So the down bit is set. We still have regular OSPF flooding. In the end, the prefix makes it back to the PE router. But now this PE router sees that the down bit is set, meaning it knows that the prefix actually comes from the MPLS backbone and has already been advertised again through OSPF. Because of the down bit, this PE router will not redistribute that route back into BGP, and this prevents possible routing loops in this network. What about EIGRP? Well, EIGRP can also be used as a PE-CE routing protocol. You just configure the router EIGRP process and then configure the usual commands under address family IPv4 VRF. If you want the VPN v4 learned prefixes redistributed from BGP into EIGRP, you would have to configure the redistribute BGP command. Equally so, if you want the EIGRP routes to be redistributed and advertised through VPN v4, you would have to configure the redistribute EIGRP command under address family IPv4 VRF under the BGP process. Now, EIGRP also has a couple of things which are specific for EIGRP when it's being used as a PE-CE routing protocol. One thing is the route type of EIGRP. You either have internal or external EIGRP routes. Again, as with OSPF, if you would redistribute EIGRP into BGP and back into EIGRP, all the EIGRP routes would become EIGRP external routes. And that's not always what we want, specifically if you have backdoor links. Second, when you redistribute an EIGRP route into BGP, you would lose all the metric information. And the metric information in EIGRP is a little bit complex because it's a composite metric of delay and bandwidth and maybe even other fields. So to keep that information, when we transport the EIGRP prefix as a VPNv4 prefix across the MPLS backbone, we will put those EIGRP characteristics like the EIGRP route type or the metric information into specific extended communities and attach them to the BGP VPNv4 prefix. Then at the remote site, when we redistribute the BGP VPNv4 prefix back into EIGRP, we can reconstruct the original EIGRP route by looking at the EIGRP characteristics inside those extended communities attached to the VPNv4 prefix. Let's have a look at an example. We have here EIGRP as the PECE routing protocol. We advertise a prefix through EIGRP from the CE to the PE router, and we typically have a route type attached, which is internal or external, and some other metric components information, bandwidth, delay, and then maybe if it's an external route, some external route information. When we advertise this prefix across as a BGP VPNv4 prefix, we will attach extended communities saying what the route type is, what the metric components is, and possibly what the external route information is. At the remote PE router, when we redistribute the VPNv4 prefix back into EIGRP, we can reconstruct that EIGRP prefix with the original route type, metric components, and so on by looking at those attached BGP extended communities which are attached to the VPNv4 prefix. Finally, we have BGP. We can have an eBGP or maybe even an iBGP session between the PE and CE router. And that's pretty easy to configure. Under router BGP, you would now configure a neighbor command under the address family IPv4 VRF. You would configure a remote AS number and you would see that the BGP adjacency or peering from the PE to the CE should come up. Let's have a look at a live demo at an example with OSPF and an example with EIGRP used as the PE-CE routing protocol. Alright, let's have a look at the lab with OSPF as the PE-CE routing protocol. We have our MPLS VPN network here again with one VRF red, and now we actually do have the backdoor link between the VRF sites up and running. So let's have a look what we have here at the PE routers. Let's have a look at PE router 1, what we can see there. There is a command to look at the OSPF sham link specifically, so let's do that. Here we can see that for the OSPF 100 process, which is the process used by VRF Red, we do have a sham link. It's towards PE2, source IP address is here on PE1. And you can see it's a special link. It is run as a demand circuit, so we don't have periodic flooding. There's no OSPF hellos across it. We have the do not H bit set. This allows to not have periodic OSPF LSA flooding. It's a point-to-point link and so on. So basically, it's similar to a virtual link between P1 and P2. And over this link, we can have the regular OSPF flooding. So this will allow us to keep the type of OSPF route when the OSPF prefixes are flooded over the sham link. So if it's an intra-area route, it will stay an intra-area route. If it's an inter-area route, it will stay an inter-area route, and so on. Let's have a look at OSPF neighbor. Do we have any neighbors? Yes. So we do have the neighbor from PE1 over the VRF interface towards CE1. But as you can see here, we also have a neighbor which is actually P2. So this is the neighbor across the MPLS VPN backbone over the sham link, which has been established. So this sham link allows us to keep the routing similar across the MPLS VPN backbone and the backdoor link. Now the PE router on either side can just choose the best path for any prefix based on the metric or the cost of the OSPF route without having to worry about the type of route because they will be the same. Alright, we're back with EIGRP as a PE-CE routing protocol. We're back with the same network, but this time the routing protocol between the PE and CE routers for VRF Red is enhanced EIGRP. Let's have a look at one PE router. This is router P1. Let's first have a look at the configuration for VRF Red. So show running config VRF Red. We can see that we defined what VRF Red is with the route distinguisher and route targets and so on. We configured VRF on the VRF interface, the interface towards the CE router. And here we have the process EIGRP 100, which is the PE-CE routing protocol. Under address family IPv4 VRF Red, we configure the usual commands for enhanced EIGRP. And here we can see that we configured redistribute BGP 65000, meaning we will redistribute the VPN v4 routes that we receive from remote PE routers into enhanced EIGRP. Equally so, under router BGP, under address family IPv4 VRF Red, we redistribute enhanced EIGRP into BGP. That's the configuration. What do we get as prefixes? So let's have a look at the EIGRP routes being received as VPN v4 routes from the remote PE router PE2. So with the command show BGP VPN v4 unicast VRF Red, we see all the VPN v4 routes that we received, and we received quite a bit of them from the remote router PE2. This looks like a normal BGP table. Let's have a look at a specific prefix that we see here, 10.2.2.0/24, which is the prefix of the remote link, so the link between P2 and C2. What do we see? We see, of course, that the next hop is router 2, but we also see quite a bit of special extended communities which are attached to the VPN v4 route. And those extended communities are the ones used by EIGRP. These are the ones used so that when we redistribute this BGP prefix back into enhanced EIGRP on this router, on router PE1, we can reconstruct all the EIGRP characteristics, such as the route type, internal versus external, everything that has to do with the route metric, and so on. And of course, we also have the VPN label, which is received, which obviously is needed when we are forwarding packets from PE1 through PE2 towards that destination. In this lesson, we'll have a look at internet access with MPLS VPN Layer 3 networks and multi-VRF CE, or also known as VRF Lite. So how do we provide internet access to VRF customers, to CE routers inside a VPN? Well, there are a couple of ways to do it, and we'll go over three possibilities. First of all, we can have internet access from within the VPN through the global routing table of the service provider. Or we can provide internet access to VPN site to one central site of that VPN. Or we can just put the whole internet, so all the routes from the internet, all the BGP routes that we have on the internet today, inside one particular VPN, and then provide internet access to the customer through that VPN. Actually, there is a fourth way, but it's not so popular. The fourth way would be, besides having a VRF interface from the PE router to the CE router, is providing a second interface from PE to CE, which is not in a VRF, so it's not inside the VPN. And through that interface, the service provider could provide internet access to the VRF customer as well. So let's have a look at the first option, internet access through the global routing table. Well, it's a very easy deployment. We will not have to configure a lot. Basically, for our VPN Red that we have here, on the PE router, there's just two routes that you would have to configure, two static routes. The first route is to make sure that packets originating from a VPN Red site can go to the internet. How do we do that? We just configure a static route inside VRF Red for a particular prefix and then point it out to an IP address in the global routing table. That's why we have the global keyword here. And this IP address is actually, per read the loopback, an IP address of the Internet Gateway Router. And that's an IP address in the global space, global context of the service provider. So this static route inside the VRF will make sure that the traffic can go from a VPN site to the internet. But now we need to look at the return traffic. How do we get the traffic back from the internet into the VPN, into the VRF here? We also configure a static route on the PE router. We configure here the IP prefix of the particular VPN red site that we have here and point it just to the VRF interface. That's it. But this static route then must be known, or the prefix that we configure in the static route must be known on every router, specifically on the internet gateway router. So we have to make sure that this PE router redistributes this static route into the IGP, for example, but it could also be in BGP. In that way, the traffic can be attracted from the internet and can flow over the VRF interface towards the VPN red site. This is the second option, how to provide internet access through a central site. That means that for one particular VPN red here, we will have a central site through which we will provide internet access. Typically this is also done for hub and spoke setups where the central site is the hub and every other site is the spoke. Now we have to make sure that the traffic goes from the spoke site to the hub site. We do this by making sure that the route propagation is done in the proper way, by making sure we configure the route targets on all the PE routers in a correct way. So we have to export the route targets on all the PE routers in a correct way so that the traffic flows from a remote site through the particular CE router here at the bottom. Then the traffic might go through a firewall or might even be netted and then be routed out through the other CE router through the internet. Again, this will be done by making sure we have the correct route target import and export statements on the PE router. And then the return traffic will typically flow in the opposite direction through the central site back to the spoke site. And the third option is internet inside a VPN. Notice here on the internet gateway router that the whole internet is connected through this router, which is now a PE router, so the connection is through a VRF interface. It's made gray, so it really doesn't belong to any particular customer. How do we provide the access? Well, this router, the internet gateway router, will advertise, for example, a default route with a route target 1:999 that the other VRF sites, whatever the VPN might be, import if they want internet access. So if they import the default route with the route target 1:999, then the traffic can flow from any VRF site, any CE router, through the MPLS backbone, out of this gray VRF interface to the internet. And for the traffic back, well, we'll have to make sure that for the traffic going back to the CE routers, that these CE routers advertise their particular prefix for which they want internet connectivity with a specific route target towards the internet gateway router. And this internet gateway router imports those route targets, in this case 11 for the VRF red and 12 for the VRF green, into the VRF gray. When that is done, the traffic can flow back from the internet to the specific CE routers in the specific VPNs. What is multi-VRF CE, which is actually better known as VRF Lite? Well, with VRF Lite, we try to extend the VRF functionality one hop further down. So instead of just having VRF on a PE router, we might now have VRFs on a CE router. That's why we call it a multi-VRF CE router. But it's called Lite because we don't need MPLS here. We don't need to enable or run MPLS on that multi-VRF CE router. It's really about extending the VRFs one hop down. It's a bit similar like running VLANs through a layer 2 switch here. And one of the reasons could be that we want to extend the VRFs down towards certain departments of this company and make sure that the departments cannot communicate with each other. Because here, the packets going through this multi-VRF CE router, if they enter on a VRF green interface, they can only go out on a VRF green interface. So here, again, we have complete isolation between the different VRFs that we have on the multi-VRF CE router. There's one small gotcha with that. That is, if you run as a protocol OSPF between the PE router and the multi-VRF CE router, then you might run into a specific problem. And the problem is that once the PE router advertises routes to the multi-VRF CE router, OSPF route, that multi-VRF CE router will not propagate those OSPF further down or again across a VRF interface. Why not? Well, we have seen that before. The thing that stops this from happening is the down bit. Once the multi-VRF CE router receives an OSPF route prefix from the PE router, it cannot further advertise it and re-advertise the prefix over a VRF interface because the down bit is set. Anyway, we want multi-VRF CE or VRF Lite to work even when we run OSPF as the PECE routing protocol. So to make it work, you will actually have to disable that check. And that check, the down bit check, is done for LSA type 3 and 5 routes, so inter-area routes and external routes. To do that, you would have to configure the command capability VRF Lite under OSPF. Let's have a look at 6PE. So 6PE is one of the ways to transport IPv6 prefixes over an MPLS backbone. Now the thing with 6PE is that we don't have VPNs, we don't have VRFs. Everything we do here is in the global context. But we still have an IPv4 only enabled MPLS network. So we have an IGP running for IPv4, we have LDP running, and we have MPLS packet forwarding. Basically here we'll have BGP advertise IPv6 unicast route from PE router to PE router. This will be over iBGP, but it's IPv6 unicast routes, it's not VPN v6. So 6PE has nothing to do with VPN. Again, between the PE and CE, many routing protocols are available. And typically the iBGP session between the PE routers, which is needed to carry the IPv6 prefixes, is actually a session between IPv4 addresses. So it's still an IPv4 BGP session between the two loopbacks of the PE routers. One thing peculiar about 6PE are the IPv4 mapped IPv6 addresses. Well, what is this? Well, think about it. We are carrying IPv6 prefixes through BGP, but the next hop is an IPv4 address. It's the loopback of the remote PE route. So we have an IPv6 prefix with an IPv4 next hop address. This is not really allowed. So what we do to make this work is we kind of fix up the next hop IPv6 address. It is in reality an IPv4 address, but we make it look like an IPv6 address. How? Well, we put a whole string of zeros in front, then we have ::, 16 bits set to 1, and then : the 32 bits for the IPv4 address. So this is a reserved kind of syntax for IPv4 mapped IPv6 addresses. And you will only see that with 6PE, and also as we see in the next lesson with 6VPE. Important also is the forwarding. As with MPLS VPN, we will use two labels to do the forwarding. We'll have again a top label, the IGP label or the transport label, and we'll have a bottom label, which is the BGP label. Between the PE and CE, we can have any IPv6 routing protocol. In this case, for the example, we just have BGP. Between the PE routers, we have iBGP in a full mesh fashion or with route reflectors. Reminder, there are no VRF on these interfaces. So on the interfaces from the PE to the CE routers, there's no VRFs. This interface is in the global context. Let's have a look how the route propagation works. Well, this PE router, when it receives the IPv6 prefix 2001:DB8:1/64, we advertise it through iBGP as an IPv6 unicast route. So there's no VRF, hence there are no route distinguishers here. And we attach the BGP label. So this is a label assigned by this PE router to that prefix, and the label is 17. And then at the remote end, this label of course is stripped off and the prefix is further propagated down to the CE router. What is the configuration needed for 6PE? Of course, you need to have IPv6 unicast routing enabled on the PE router. You need to have IPv6 addressing towards the CE router on that interface, but no VRF. And you need a PE-CE routing protocol. In this case, it's also BGP. So we configure that neighborship just under the address family IPv6. Again, no VRF. But the neighbor towards the remote PE router must have the send label keyword. Why? Well, it's not enough just to send the IPv6 prefixes across the MPLS backbone to the remote PE routers. We must also attach a label to it, because also for 6PE, all the packets will be forwarded with two labels in the network. Top label, IGP or LDP label, bottom label, this BGP label. Let's have a look at this forwarding in a 6PE network. For the same prefix, of course, the forwarding will happen in the opposite direction. So this is the route propagation again. On this remote PE router, we will get this IPv6 unicast prefix and we will have a specific label. The next hop that we see in the BGP table or routing table for this IPv6 prefix is the IPv4 mapped IPv6 address. And this IP address 10.100.1.1 is the loopback of the egress PE router. And then in the CEF table, the IPv6 CEF or FIP table for that prefix, you will see that we will actually have two labels. The label stack is two labels. This bottom label is the label 17, the one attached to the IPv6 prefix. And the top label is the IGP or LDP label 81, which is the one linked to get the packet to the remote PE router. So the loopback 0 IP address 10.100.1.1 of the PE router on the left. Packet forwarding, well, the ingress PE router will get an IPv6 packet. It will do a lookup in the CEF or FIP table, impose this label stack, the two labels on top of this IPv6 packet, and shoot off the packet into the MPLS network. At every PE router, we will just do label swapping. But then at the last but one router, of course, again, by default, we have penultimate hop popping. So we pop off the top label or the IGP label. And we forward the packet just with the BGP label towards the egress PE router. He does a lookup in the LFIP for label 17 and forward the packet as an IPv6 packet towards the remote CE router. Now, a lot of people ask the question, why do we still need one label here? Why do we need two labels here? Is it not enough to forward this packet with just one label? Well, maybe, but we really wanted to have this penultimate hop behavior. And if we would have penultimate hop behavior here between the last P and the PE router, then if the packet comes in on this last P router, the penultimate hop router, with just one label, and we pop it off, this router, the P router, would have to forward the packet as an IPv6 packet. That would mean it would have to understand IPv6 forwarding. It would have to have the necessary operating system code to understand IPv6 routing and forwarding. And from day one we said, no, the requirement is the P routers should be completely IPv6 unaware. If they run IPv6, that's fine, but there is no requirement that they must understand IPv6. So that's why from day one, even with 6PE, even though there is no VRFs or VPNs, we must have the packets forwarded in a 6PE network with two labels. Let's have a look at 6PE in the live demonstration. Let's have a look at our demo for 6PE. So we have a lab here with, again, an MPLS core, two P routers and two PE routers. And we have from each PE router a link to the CE router. But now, of course, we have IPv6 here on either side and no VRF on those interfaces. Let's have a look at how 6PE works. We're going to look at router P1. Let's first see how router P1 would receive the prefix from the remote link PE2 CE2, which is the prefix 2001 DB8 192.168.2/64. Let's have a look. It will receive it, of course, through BGP IPv6 unicast. There we have the prefix, and we can see that indeed the next hop is this IPv4 mapped IPv6 next hop. This is the IPv4 loopback address of PE2. And we can also see that we received the BGP label. So the bottom label when forwarding packets from PE1 to PE2 towards that prefix will be label 25. The forwarding towards PE2 is the same as it has always been. We are just going to forward labeled packets by using the label which is tied to the BGP next hop address, which is 10.100.1.2. So let's have a look at the binding and the label for that particular prefix, which is received by LDP. And the remote binding outgoing label is label 21. So now to forward these 6PE packets from PE1 to PE2, we will use as a top label 21 when the packet goes out of PE1 and goes towards P1. And then the bottom label or BGP label is label 25. And we should be able to verify that if we do show IPv6 CEF. So we're going to look in the CEF or FIP table for that particular prefix. And indeed we see that we have those two labels there in the pushed label stack for that prefix. And to really be sure, we can double verify it by doing a trace route towards the destination. And as the trace route shows, we do have two labels in the label stack as well. Reminder that the P routers might not even be IPv6 capable. So when you do a trace route, they cannot return IPv6 addresses here. They don't understand IPv6. So what they will do is just put an IPv4 address. And then in the trace route, it will actually show up as, again, an IPv4 mapped IPv6 address. Let's have a look at 6VP. So VRF or VPNs is back. The purpose of 6VPE is to carry IPv6 prefixes over an IPv4 only backbone. And that backbone is also MPLS enabled. This is similar to MPLS VPN layer 3, which we covered before, but now instead of having the service routes being IPv4 routes, the service routes are IPv6 routes. Also, on the VRF interfaces, we can still have IPv4 as well. So IPv4 and IPv6 can be used together towards the customer routers at the same time. What routing protocols can we use for IPv6 on the PECE interfaces? Well, more or less all routing protocols are available. And of course, those IPv6 prefixes of the customer, they will be carried in VPN v6 prefixes, which is basically the route distinguisher, 64 bits, to make the routes unique, plus the IPv6 prefixes. Again, we'll have the same problem as with 6PE. We are carrying IPv6 prefixes over the backbone through BGP. Now, IPv6 prefixes, while having an IPv4 next hop address, is not really allowed. So the trick here is again to make those IPv4 addresses look like IPv6 addresses. So we'll use the same trick as with 6PE, and we'll use IPv4 mapped IPv6 addresses. And as with MPLS VPN layer 3 for IPv4, the label forwarding in the core of the network is really the same. We'll be using two labels to forward those packets. The top label being the IGP or LDP label, and the bottom label being the BGP label. So here we have a network, again as PECE routing protocol. We can have any, more or less, IPv6 routing protocol, but in this case it's BGP again. Over VPN v4, that's BGP of course, we will be carrying the VPN v6 prefix. So we'll have the IPv6 prefix, but made unique by a route distinguisher. And this route distinguisher is tied to the VRF, of course. Also, we'll have one or more route targets attached. As with MPLS VPN layer 3 for IPv4, these route targets identify where, in which VRF, at the remote PE routers, that the IPv6 prefixes should be imported into. What about the configuration? Well, again, on such a PE router, IPv6 unicast routing must be enabled. We'll have the VRF configured, in this case for VPN red, but now next to address family IPv4, we can also have address family IPv6. And this is a must if you want to have 6VPE enabled. On the interface towards the CE router, we have the VRF forwarding statement, of course, and now we will have one or more IPv6 addresses configured. Under router BGP, we must have the address family VPN v6. So between the PE routers, we will have iBGP sessions for VPN v6. These sessions will carry the VPN v6 or the customer routes, of course. If you have BGP as the PE-CE routing protocol, then here it will be enabled under address family IPv6 VRF. Here we configure the neighbor statement towards the connected CE router. And for these sessions, we can actually use IPv6 addresses as endpoint for the PGP TCP sessions. How does the forwarding look? Well, it's exactly the same as with MPLS VPN layer 3 for IPv4. So if we look at a remote IPv6 prefix here, we have the prefix 2001 db8:1/64 advertised to the remote PE with a label and some route targets. In this case, the BGP or the VPN label is label 17. It gets imported on the right-hand side PE router into the correct VRF. We strip off the RD, of course, and we install the route. So here we see that the PE on the right-hand side received the VPN v6 prefix, label is 17. In the routing table for VRF red, we installed the IPv6 prefix, but with the IPv4 mapped IPv6 address, this being the loopback of the remote PE router. And then in the CEF table or the FIP table, of course for IPv6 again, for VRF red, we will install the prefix, and you will see that we will have a label stack of 2 MPLS labels. The top label being the IGP label, which is the label to get a packet to the remote PE, so the label tied to the prefix 10.100.1.1, the loopback of the remote PE. And the bottom label is label 17, which is the VPN label, the label carried by BGP attached to the VPN v6 route. So the label forwarding, on the Ingress PE we receive an IPv6 packet on the VRF interface. We do a lookup in the FIP table for VRF red for IPv6. We put those 2 labels on top of the packet and forward the packet out into an MPLS cloud. Again, label forwarding hop by hop. Typically on the P router we do label swapping. At the last hop router, penultimate hop hopping. And then on the last router, the egress PE router, we look up this VPN label in the LFIP, strip off the label and forward the packet as an IPv6 packet towards the egress CE router. That's how forwarding works in 6VPE. Let's have a look at it in the live demo. Let's have a look at the live demo for 6VPE. We have the network, which is very similar to the network we had for 6PE, but now we actually have a VRF interface from the PE to the CE router, and we have a VPN red, actually 2 sides, 1 on either side, and we'll have an IPv6 prefix inside each side that we have there. Let's have a look at PE1, what we have. Let's first have a look at the configuration. We can do a show of run VRF red, and we see that we have VRF red, but we also have address family IPv6 specified. On the VRF interface, you can see that we have an IPv6 address. So from the PE to the CE on the VRF interface, we now have an IPv6 prefix or address configured. Under router BGP, we now have address family IPv6 VRF red, and we have a neighbor defined. This neighbor, that's the CE router. So over this neighborship, we receive IPv6 prefixes from CE1. Let's have a look at what we advertise or receive from the remote PE. Let's have a look at show BGP VPN v6, it's 6VPE now, unicast with all keyword. And here we see now that we have VPN v6 prefixes. Some are local, some are received from the remote end, and they will be grouped by route distinguisher. This is the route distinguisher for VRF red. We can actually specify that if we do rd:2, and we see only the ones for VRF red, the ones with route distinguisher 1, 2. Let's have a look at one specific prefix. This one, 2001 db8:2, is the remote prefix from this link here. What do we see? We see that we receive it from P2. This is the IP address of loopback 0 on P2. We have a VPN label, of course, and that will allow us to forward the MPLS packet with 2 labels towards PE2. Mind you, I have a backdoor link here between the 2 sites, but this one is really not used. We are looking at the path over the MPLS backbone. What do we have in the routing table? Show IPv6 route VRF red for the prefix. We can see that we have the route obviously learned as BGP, that the next hop is 10.100.1.2, the loopback of the remote PE2 router, and we have an MPLS label. So in principle, we are ready to forward packets from the left-hand side, VRF red, to the right-hand side in VRF red or VPN red. Let's have a look at that in the FIP or CEF table in VRF red, of course. And there we go. We see that we add 2 labels. This is the VPN label received through BGP, VPN v6, and this would then be the IGP or LDP label to get a packet to P2. Can we verify that this is actually working? Of course we can. We're going to use traceroute again. So let's do a traceroute IPv6 for the prefix, which is 2001 db8:2:2. And we can see that the packet is forwarded over the MPLS backbone towards the destination here. The packet is forwarded with 2 labels, the VPN label and the IGP label. Again, the P routers are completely IPv6 unaware. They do not understand IPv6. That's why in the traceroute we actually see the IPv4 mapped IPv6 addresses. Hello and welcome to lesson 6. This is really the advanced portion of MPLS VPN layer 3 we saw in lesson 5. I'll focus on how to perform inter-autonomous system services with MPLS VPN layer 3 in a few different ways and also carrier-carrier. I will explain how each method works and provide the pros and cons of each method. Let's have a look at the first option on how to do inter-AS MPLS VPN, option A. So what do we have with option A? Basically, the purpose of inter-AS MPLS VPN is to make sure that we can carry traffic from one AS to the other in case one customer has VPN sites in either of the autonomous systems. The first solution, option A, is to have back-to-back VRF connections between the autonomous system border routers. This will allow us to send traffic for the specific VPNs from one AS to the other. And that traffic will actually be IP traffic. Because we have back-to-back VRFs, meaning we configure the VRFs on the interfaces leading to the other autonomous system border router, we can just have 1, an IP routing protocol, and 2, the packets will just be forwarded as IP packets. So think of it as you have an ASBR and it sees the router, the other ASBR, connected to itself as a CE router. Because all that ASBR will see is a VRF interface leading to a directly connected router with an IPv4 routing protocol on top of it. So it is as if the connected router is just a CE router. So in the end, it is as if both the autonomous systems are running regular MPLS VPN. So the big benefit here is that there are no extra features needed to make this work. This is just back-to-back regular MPLS VPN. There is of course one disadvantage, there always is. Namely here the scalability isn't very good, neither is the manageability. The scalability isn't very good because for each VPN that is shared among the different autonomous systems, you must have a VRF interface between the AS border routers. The manageability is not great either. imagine each time that a VPN customer is put on either side of the autonomous systems, then we'll have to make sure there is an extra link created, a VRF link between the ASR routers. So this puts a heavy burden on the manageability. Let's have a look at the overview of option A. We basically have two autonomous systems, one on either side. For each VPN, which is shared between the two ASs, we must have an inter-AS link between the two ASBRs. And this is a colored link, the same color as the VPN. So this means that this interface belongs to a particular VRF. You must configure a VRF on this interface. You must make sure that you have IPv4 routing, so you must have a routing protocol between the ASBRs over each link per VRF. And in that case, the packets will just be forwarded as IP packets over the inter-AS links. The packet forwarding is really the same as what we have seen with MPLS VPN Layer 3. There's nothing different. So if an IP packet is received on a PE router on a VRF interface, we do a lookup in the FIP table, we push two labels on top of the packet, and we forward the packet in the regular way. Penultimate hop-hopping, the packet arrives at the ASBR, we look up the label 16, we forward the packet as an IP packet over the VRF interface, just as if we would forward the packet to a CE router. And then on the other ASBR, the packet arrives on a VRF interface. Again, we do a lookup in the FIP table, put the labels on top of it, and forward the packet again, as with regular MPLS VPN. Let's have a look at the second possibility on how to do inter-autonomous MPLS VPN, option B. With option B, again we'll have the same VPN in different autonomous systems. The difference here with option A is that we'll have only one connection, one link as a minimum, between the two ASBR routers. And over this link, we'll actually be forwarding label traffic. The traffic will have MPLS labels, it will not be IP traffic. So we'll need a mechanism to advertise those MPLS labels across from one ASBR to the other. We have such a mechanism. We will be using VPN v4 with BGP. But this time it will be eBGP, external BGP, instead of internal BGP. So when we have MPLS traffic being forwarded over this inter-AS link between the ASBR routers, we can actually have one uninterrupted LSP from one PE router to another PE router in another autonomous system. With this option B, we have much better scalability. We have only one link between the ASBR routers. We have much better manageability because we will no longer have to add links between the ASBRs when adding VPNs shared between the two autonomous systems. So here's a schematic overview. Again, we have 2 times MPLS VPN. The two autonomous systems connect through ASBRs, but this time we only have one link in between the ASBRs. Over this link, we will be forwarding label traffic. And we will be forwarding the label traffic for all the VRFs which are present in both ASs. So in this case, all the traffic for the red VRF and the green VRF will be crossing this link as labeled traffic. To make this work, we will now have to configure an eBGP VPN v4 session between the two neighboring ASBR routers. So the ASBR routers, well, you will need to configure eBGP VPN v4, and those ASBR routers need to be able to store those VPN v4 routes. Now be careful, by default the ASBRs, they might not have any VRF interfaces configured. So by that definition, they are not PE routers. If they are not PE routers and they receive VPN v4 routes through iBGP, for example, they will not store them because they will not find matching route targets to import into a specific VRFs, because there are no VRFs on that ASBR. But we need to store those VPN v4 routes. So to make that work, we'll have to change the default behavior. We have to make sure that the ASBR routers store all VPN v4 routes and do not discriminate. So to make that work, you will have to configure a command. and the command under BGP is no BGP default route target filter. In that case, all VPN v4 routes are stored. The forwarding between the ASBR routers must be assured. The packets must be forwarded as MPLS packet at all times. If the LSP for some reason is interrupted, so if packets are forwarded as IP packet, then the whole scheme will just fail. In some cases, to make this work, we will need a static route from one ASBR router to the other. Now, depending on the operating system, this static route needs to be configured by you, the operator, or it can be automatically generated by the router itself. But in any case, this static route for the IP address on the other side of the link needs to be there. And also it needs to be advertised into the IGP of the MPLS VPN network. Why? Because we need to make sure that from the ingress PE, we are able to forward packets out of the inter-AS link, so from one ASBR to the other. Also, normally the eBGP session between the ASBRs is just a directly connected eBGP peering, but it can also be eBGP multi-hop. Typically this is used when you have more than one link between the ASBRs. So if you have a pair of parallel links, you can use eBGP multi-hop. But in that case, because the eBGP multi-hop is typically configured between the loopback IP addresses of the ASBR routers and not the IP addresses of the inter-AS links, you must have a routing protocol, like an IGP configured there over those links. And because you have an IGP running and we must have MPLS forwarding, you will also have to configure LDP, and then LDP takes care of the label advertisement of the IGP routes. Let's have a look at a configuration. On the ASBR, we will now have the no BGP default route target filter command. That means from now on, this ASBR stores all VPN v4 prefixes. But under address family VPN v4, we do not longer just find iBGP neighbors, the PE routers in the same AS, but also the ASBR router, which is a neighbor in a different AS. So we now have eBGP VPN v4. And as soon as you have configured that, then the MPLS forwarding on that link, the inter-AS link, should be enabled by default. And actually you can see that when you do a show running configuration, because on that inter-AS link, which is gigabit 0/1 here, you will actually find a command MPLS BGP forwarding. So the MPLS forwarding has been enabled on this inter-AS link by BGP because you configured BGP or eBGP VPN v4. And just a note on this static route, when you do show IP route connected on the ASBR, you will actually see a /32 connected or static route for the IP address on the other side of the link. And this static route, you must make sure, is advertised in the IGP of the autonomous system. You either do that by redistribute connected in the IGP or by advertising the particular prefix by configuring a network statement command, for example. Let's have a look at the packet forwarding. And there are really two cases to look at. First of all, on the ASBR, when it is forwarding the eBGP VPN v4 prefix as iBGP VPN v4 prefix towards the PE router, it will do no next hop self. That means that the next hop of those prefixes is actually the IP address that we saw here on this link. So when an IP packet arrives through a VRF interface on the ingress PE router, we will put two labels on top of it. The first label is the label to get the packet through the first autonomous system. Not to this ASBR, because this ASBR does not do next hop self. The packet needs to be forwarded to the second ASBR. And that's why we need this IP address of the inter-AS link to be known throughout AS 65002, so that this PE router knows to use label 64 as a top label. And this label 64 is the label tied to the IP address here on this side of the inter-AS link. So the packet forwarding happens as usual, but now this ASBR is the penultimate hop router. It pops off one label and the packet arrives with the VPN label 16 at the second ASBR router. He will do a lookup in its LFIP for this label, will find an entry, do a label swap with the new VPN label 17 and push an extra IGP label 54 to get a packet towards the remote PE. Then it's regular forwarding, penultimate hop popping, and the packet is forwarded as an IP packet towards the remote CE router. So this is how the forwarding works with no next hop self on the first ASBR. You must have this IP address advertised as a /32 prefix in AS 65002. What if you do next hop self on the first ASBR? Well, it's slightly different. When an IP packet arrives on the VRF interface on the Ingress PE router, we put two labels on top of the packet, but now this label 64 is to get the packet to the first ASBR router. Penultimate hop popping, so now the packet arrives at the first ASBR already with the VPN label. We swap it out with the next VPN label advertised by ASBR, well, the second one, over eBGP VPN v4, and this ASBR will swap it out with a new VPN label, put an extra IGP label on top of it, and the packet is forwarded on as it usually does. Let's have a look at the live demo about InterAS option B. Let's have a look at the lab for InterAS option B. So we have a network here, one AS on one side, another AS on the other side, and we have two ASBR routers with an InterAS link here, with on one side an IP address 10.3.1.5 and on the other side .6. And we have one VPN site on each side with one CE router in VRF red. Let's have a look at this forwarding in InterAS option B. Let's have a look first at an ASBR router, in this case ASBR1, how we have set this up. Let's have a look at the show running configuration. At the BGP part, we can see that we have configured this no BGP default route tagger filter command to make sure that the ASBR will store all VPN v4 prefixes. We have two neighbors, the PE1, but also the eBGP neighbor, which is the other ASBR, ASBR2. And that's more or less all that you need on the ASBR router. Let's have a look at PE1, what we have there. So if you look at PE1 for a remote prefix in VRF red, let's take the prefix that we see here, 10.9.2. We see that we receive the prefix as a VPN v4 route. Obviously, there are some route targets attached, and we have an outgoing label. Let's have a look at the CEF table, VRF red, for the prefix 10.9.2.0/24. Yep, we see that we have two labels. One is the VPN label, label 20, that we saw here, and one is the IGP label. Which IGP label is that? Well, it's the IGP label, not to get to ASBR1, but actually to get to ASBR2, because we do not do a next hop self on ASBR1. Let's have a look if we can find it back in the LFIP. So outgoing label 17 would mean it's bound to this prefix, and this address 10.3.1.6/32 is indeed the IP address of this InterAS link at the ASBR2 side. And this prefix must be advertised in the IGP of our AS. So those are the two prefixes used. Does the forwarding actually work? Well, we can have a look at router C1 and just try a trace route and see what happens. Yep, we get to the remote end and we can see we have two labels. Except for when we reach the InterAS link, we only have one label left, which is the VPN v4 label. And then we go back to two labels in the remote autonomous system number until we reach the remote PE router. So here we were doing forwarding based on label 20. So 10.3.1.6, this is ASBR2. Let's have a look at ASBR2. What happens when this router receives packets with a top label of 20. It forwards it out with label 21, and these labels are actually bound to a VPN v4 prefix. This is indeed the VPN v4 prefix that we have here at the remote PE, PE2. But when we look at the trace route, we actually saw that we swapped the label and we pushed the label. So maybe if we do detail here, we'll see something more. And indeed, we do not just swap the label, we swap the incoming label 20 with another VPN label 21, and then we push the IGP label 19 on top of it. And this label 19 is the label used to get the packet, of course, to the remote PE router. So that's how the forwarding works in inter-autonomous MPLS VPN option B. Let's have a look at the third option to do inter-autonomous MPLS VPN, option C. Again, of course, we have the same VPN in different autonomous systems. Again, we will have only one connection between the two ASBR routers. That means, again, we must forward the packets labeled. But now we will not have VPN v4 on the ASBRs. We will move the VPN v4 away from the ASBRs and onto route reflectors. The reason for that is scalability. If we can move VPN v4 away to other routers, we make this option even more scalable than option B. But we have to be careful. If we use route reflectors to advertise VPN v4 routes, we must make sure that the route reflectors are not on the forwarding path itself. So it's important that they never become the next hop, because if they become the next hop for BGP prefixes, they will attract traffic. And if route reflectors attract all of the traffic that goes from one autonomous system to the other, it's very, very likely that they are not able to cope with that and they will just crash. However, now that we move the VPN v4 part away from the ASBR part, we must make sure that the forwarding and the route propagation still works end to end. How are we going to make sure that we have an uninterrupted LSP from PE to PE in between the ASs as well? Well, the trick here is to make sure that one PE router knows about the loopback IP address, which will be the next hop of the VPN v4 routes it learns in another AS. Somehow it needs to learn about that. There are two ways. We can advertise the loopback PE addresses from one AS into the other by redistributing them into the IGP. But typically, service providers do not like that. They do not like to have external prefixes redistributed into their interior gateway protocol, IGP. So while this would work, we almost never see this. The other option is to keep the PE loopback prefixes in BGP and make sure that the PE routers learn about these prefixes through BGP. But how will they learn about it? These are IPv4 prefixes, not VPN-v4 prefixes. So now we have to make sure that through BGP, those loopbacks are advertised as IPv4 addresses to the remote PE prefixes. Also, the traffic towards those remote PE loopback addresses must be labeled. So now we'll have to advertise IPv4 prefixes plus an associated label for those loopback addresses. So once we have all of that set up, we can have an uninterrupted LSP from one PE to the other PE. And that's actually why in option C we have the greatest scalability and manageability. So here's an overview of option C. Again, we have VPNs connected to two different autonomous systems. We moved away the VPN v4 from the ASBRs and we replaced it with eBGP IPv4 plus label. The sole purpose of this is to advertise the loopback prefixes of the PE routers from one AS to the other. So we do that through eBGP IPv4 and attaching an MPLS label. What about the VPN v4 service? Because those are the customer routes. Well, we will carry them from PE to route reflector over iBGP VPN v4 and then to the route reflector and the other autonomous system number over eBGP VPN v4 and then back through iBGP VPN v4 to the remote PE. But, as I mentioned before, we must make sure that the route reflectors are never in the forwarding path. So the route reflectors can never become a next hop. And typically that's what happens when routers advertise eBGP prefixes, they will become the next hop. We want to avoid that. So in this case, we have to override the default behavior. So we have to configure next hop unchanged for the eBGP VPN v4 sessions. In that case, when the VPN v4 prefix is advertised to the remote PE, the next hop remains the originating PE router. Some details again about option C. So the route deflectors must store all VPN v4 routes. By default, if a router is a route deflector, it will store all the BGP routes. You must make sure that the route deflector does not change the next hop address. So you must have this next hop unchanged configuration in place. And the VPN v4 next hop addresses must be known in the other AS. And this is why we now, between the ASBR routers, have BGP for IPv4, sending the BGP prefixes, the remote loopback IP addresses, plus a label from one AS to the other. That will give us an uninterrupted LSP from PE to PE router. The configuration of the route deflector is now a bit special because we have a VPN v4 connection, eBGP multi-hop, that's what I have configured here, between route deflectors and different autonomous system numbers. And also the PE routers are now VPN v4 route deflector clients. And towards the neighbor in the remote autonomous system number, we must have this next hop unchanged command configured. How does the packet forwarding look like? Well, a PE router receives an IP packet over VRF interface. Again, we do the lookup in the FIP table, in this case, the red VRF FIP table. And now we actually add 3 labels on top of the packet. Bottom label is always the VPN label. This will tell the remote PE router on which VRF link or towards which CE router to forward the packet. We have this middle label, which is the IGP label for the remote PE, which was learned through BGP, IPv4 plus send label. And finally, the top label is just to get the packet through the first AS, from the Ingress PE router to the ASBR router. We have the normal forwarding, penultimate hop hopping. Here on the inter-AS link, we have an IGP label. This is not a VPN label. And we replace that with another IGP label to get the packet to the remote PE router. Finally, penultimate hop hopping. The remote PE router will forward the packet after stripping off this VPN label as an IP packet towards the CE router. So what is important? We have end-to-end MPLS forwarding. It was achieved through VPN v4 sessions, iBGP towards the PE, between the route deflectors eBGP and next hop unchanged, and then to the PE routers again iBGP. We have BGP IPv4 plus label advertisement between the PE router to the ASBR, iBGP, to the next ASBR, eBGP, and then to the remote PE router, iBGP again. Let's have a look at inter-AS option C in the live demonstration. Let's have a look at the live demo on inter-autonomous MPLS VPN option C. Let's have a look from the perspective of the left-hand side, so inside VPN red, and we'll be looking at this prefix at the right-hand side, 10.9.2.0/24. So how do we do the routing in between or across 2 autonomous systems? Let's have a look by looking at PE1 and see what we have there. This is PE1. What do we have for the VPN v4 prefix? In VRF red. As you can see, we do have the remote prefix here, and the next hop is 10.100.1.2, which is loopback 0 of the remote PE router, PE2 at the right-hand side. Let's have a look at this prefix in more detail. So there we have it. We have the route targets and we have an outgoing label. So we know that the VPN label will be label 24. Let's check that. Show IPsec VRF red 10.9.2.0/24. And indeed we see that the bottom label is label 24. That's the VPN label. But as we saw on the slide, Ingress PE router actually pushes 3 labels in total. So we have 2 additional labels. Remember what they stand for. One label, the top label, is to get the packet to the ASBRs, either the closest or the furthest ASBR, and the second label is to get the packet further onwards onto the remote PE router. First of all, how did we learn the VPN label? We learned that through, let's have a look at the topology, through the route deflectors. So the VPN v4 prefix goes from PE2 to route reflector 2 to route reflector 1 over this eBGP multi-hop VPN v4 session, next hop unchanged, and then through iBGP towards PE1. Let's have a look at that on route reflector 1. What do we have there? Let's have a look at the configuration, specifically the BGP one. And we see indeed that for VPN v4, the route reflector 1 has an iBGP session towards PE1, but it also has a session towards the other route reflector 2, and we have the next hop unchanged keyword. Meaning, the prefix is received, the next hop will always remain the next hop of PE2. And we could actually check that here, show BGP VPN v4. We cannot put VRF here, the route reflector has no knowledge of VRFs. So let's just have a look what we have here as routes for VPN v4. And then we can look at them by specifying the route distinguisher if we want to. So we put the route distinguisher 65002:1. And then here we can see that we have this prefix for VRF read from the remote PE2 router. And the label is 24. The route reflectors, they don't make themselves the next hop. The next hop does not change, it remains PE2. That's also why the label does not change. The label in VPN v4 would only change when a router becomes a next hop. Then that router would change the label. Alright, so that's how we get the VPN v4 prefix from the remote PE over the route reflectors towards PE1, the local PE1. Now, what about the other two labels? How do we get the packet? Through the autonomous system numbers. Well, let's have a look how we have learned those labels. On PE1, do we have a route towards the loopback of PE2? Well, let's have a look. Show IP route 10.100.1.2, which is the loopback of PE2. We do have a route, but now, not like with intra-AS MPLS VPN, where the route to the remote loopback would be an IGP route. Here it is a BGP route. So we have learned the route as a BGP route. It's distance 200, so it's an internal iBGP route. From whom? Well, the next hop is 10.3.1.6. So the next hop is ASBR2. But actually, this route was advertised through iBGP, address family IPv4 unicast, from the ASBR1 to PE1. That means that when we look at the configuration of PE1, we will see that under BGP, we do have a session between PE1 and ASBR1, which is actually there for IPv4. Here it is. And we have the send label keyword. So that means we get an IPv4 unicast prefix and a label which is attached to that. So this is the route we were looking at. How did we receive it? Through BGP. So we do the command show BGP, IPv4, unicast, and then the prefix, the loopback of the remote PE. So we see again, as we know already, that the next hop is 10.3.1.6. We received it from this router, and now we have a label attached. This was label 21. When we looked at the CEF table on router PE1, we have seen that this was the middle label. So this is the label to get to the remote PE once you're in the next autonomous system then. So what is label 19 then? Well, we first need to get the packet routed to 10.3.1.6 to the ASBR routers. This is the address of the inter-AS link, the remote site. So we will have a route for that. Show IP route 10.3.1.6. We do have a route from that. It's an IGP route. We learned it over OSPF. And if we do show IP CEF for that prefix or IP address 10.3.1.6, we see that indeed we do have a label 19, which is the label to get to the ASBR. And we see this is the top label used on top of the packets going from one AS to the other inside a specific VRF. So we have three labels here. How can we verify that the packet forwarding is actually working and that three labels are being used? Let's go to the CE1 router, the CE router at the left-hand side, and let's just do a trace route towards the destination, which is 10.9.2.2, for example, which is the prefix on the CE router on the right-hand side. And indeed, we see that the packet goes out with these labels, 3 labels towards the destination. So that's how the packet forwarding works in inter-AS MPLS VPN option C. Let's have a look at inter-AS MPLS VPN carrier's carrier. Carrier's carrier is really a solution whereby there is a bigger carrier providing MPLS VPN services towards smaller carriers or service providers. The whole point here is to have more or bigger scalability. How do we do that? Well, the solution is to extend MPLS, so the MPLS forwarding, from the PE router at least down to the CE router. So we will still have a PE router with a VRF interface towards the CE router. Now we're going to enable MPLS forwarding on that VRF interface towards the CE. So the minimum here is we will have MPLS forwarding on the PE-CE link. As soon as you have MPLS forwarding on the PE-CE link, it is carrier's carrier. So basically the bigger service provider provides a carrier's carrier service towards the smaller service provider. And the smaller service providers, they have their own customer. Typically, all those customer routes, they will be carried in BGP because they're external routes. Important here is always to notice that for those BGP prefixes, there's always a next hop address. And for MPLS to work, there must always be a way to get to that BGP next hop through an IGP route. And then we can use the label learned through LDP. That's typically what we have seen for a BGP-free core in MPLS networking. It also means that because we have MPLS between the PE and the CE across the VRF link, that you must have a label distribution protocol between the PE and the CE. That can be LDP or it can be BGP. So here's the schematic overview of carrier's carrier or CSC. We have the big carrier on the top. We have what we call CSC PE routers with a VRF interface towards the CE routers of the smaller carrier. This is carrier A in red here. It's in red because it's really inside a VPN if you look at it from the perspective of the carrier's carrier. MPLS has been extended, so we have the MPLS forwarding also across the VRF interfaces, so the PE-CE links. And then below the carrier A, we have its customers, which in this case, for example, is customer X and customer Y. So we have 2 sites of carrier A, site 1 and 2, and it's connected through the carrier's carrier network, through the MPLS VPN network, to make sure that we can carry the carrier's A's customers' prefixes of X and Y. We need BGP running between the different sites of the carrier A. So at a minimum, to have carrier's carrier, you must have MPLS label exchange between the PE and the CE, and MPLS packet forwarding between the PE and the CE. So that means that you must have, of course, routing exchange between the PE and the CE, so you need a routing protocol, plus LDP, for example. Or you could also have BGP running between the PE and the CE, and then we would have exchange of IPv4 prefixes plus the label. And we often refer to that as BGP LU or labeled unicast. So what are the scenarios here? We have said that the minimum requirement is that we must have MPLS forwarding across the PE-CE link. That's correct. But there are now actually 3 ways or 3 scenarios to deploy carrier's carrier. First of all, the first one is the minimum one. We just have label exchange between the PE and the CE and MPLS packet forwarding, but not on any of the other routers of carrier A on either side. To carry the customer's prefixes of carrier A, we need to have BGP between its routers side to side. So there we will have BGP IPv4 just to carry the customer X prefixes. How is the packet forwarding in this case? Well, all the customer X traffic goes through carrier A as an IP packet. We don't even have MPLS there, so it must be IP. So to be able to forward these packets, all the routers here in the carrier A sites, they must be running BGP because the lookup will be in the routing table and the routers, they need to find a BGP prefix because customer X routes are known as BGP prefixes in the carrier A network. But then as soon as we go onto the PE-CE link, we will see one label there. And this is the one label that we get by looking up the destination prefix, it's a BGP prefix, finding a next hop, which typically points towards the remote side. That's an IGP route, and there, for that IGP route, we will have a label bind to it. So this is the IGP carrier A label. Once we hit the PE, of course, we will have two labels. We have the top label to get the packet across from one PE to the other PE, like regular MPLS VPN. And we have, again, a VPN label, the bottom label. This is when the packet reaches the remote PE or the egress PE to identify the outgoing VRF or the egress CE router that the packet needs to be forwarded to. But here, the VPN label will be replaced by an IGP label in order to get the packet across as an MPLS packet. So that's the first scenario. The second scenario is that off carrier A, all its routers actually run MPLS as well. So we extend MPLS not just to the CSE-CE, but down to the ASBRs, so the routers connecting to the customer X routers. So we have end-to-end, carrier A side to carrier A side, we have MPLS. In the core, of course, for the carrier network, we still have the regular MPLS VPN. Because we extend MPLS down to the ASBRs, we no longer need to run BGP on all the routers here. This is the typical example of a BGP core free. Because we run MPLS everywhere, you no longer need to run BGP on every router because the packets will be forwarded by a label lookup, and that's really guided by the BGP next hop address, not by BGP prefix itself. So that's the only change here with scenario 1. We still have MPLS forwarding, of course, on the PE-CE link. It's just that MPLS is extended down to the ASBR. So typically here, we will have to have LDP enabled on the carrier A sites. So what's the impact of that? The impact of that is that the packets on all the red routers, so all the routers of carrier A, they actually already have one label. This is the label to get the packet from ingress ASBR to the egress ASBR. And this is the label bound to the BGP next hop IP address, which is the loopback of the remote ASBR. And then in the middle, of course, we just have the regular MPLS VPN, two labels, top label, packet to get to the remote PE, bottom label is the label to get the packet out of the egress PE on the correct VRF or towards the correct CE router. That is scenario 2. Scenario 3, which is the most complicated, is the hierarchical MPLS VPN scenario. What do we have here? Here we have MPLS VPN on top of MPLS VPN. Again, we have the big carrier, so the carrier's carrier, the biggest service provider here, providing MPLS VPN services towards the smaller carrier, carrier A, as before. But now, carrier A is also providing MPLS VPN services towards its customer, customer X. That means that at the edge, instead of an ASBR, we will have a PE router with a VRF interface towards the customer X. So customer X is inside a VPN. That means now that here in carrier A, we will have regular MPLS VPN, but also inside the carrier's carrier network, we have regular MPLS VPN. And of course, between the PE, CSE, PE and CSE, CE router, we have MPLS forwarding. So BGP-wise, between the PEs, we have iBGP VPN v4 label exchange, but we also have that between the PE routers of carrier A. Now you might think that for the packet forwarding, we are probably going to use 4 labels now instead of 2. Not so. The packets will actually receive 3 labels. Let's have a look at that. So here is the packet forwarding for the third scenario, hierarchical MPLS VPN. We can see that inside the sites of carrier A, we have regular MPLS VPN with 2 labels. The VPN labels for customer X, the green VPN, and an IGP label to get the packet from one PE to the other PE. This is normal MPLS VPN. However, in the carrier's carrier network, we will have to add one label, because when the packet arrives at the CSC PE router, it already comes in with two labels. This VPN label needs to be preserved. That's the VPN label tied to the green VPN. The IGP carrier A label is a label to get the packet to the remote PE. That will now be swapped with a VPN label, because this is a PE router with a VRF interface. So we swap this IGP label with a VPN label. Then the CSCPE adds another label, the IGP CSC label, which is just a label to get the packet across to the egress CSCPE router. So remember, with the third scenario, hierarchical CSC, we have three labels in the carrier's carrier MPLS VPN network. Hello and welcome to Lesson 7. In Lesson 7, we briefly touch on MPLS VPN Layer 2. I say briefly because this topic is a rather big one. I'll stick to the essentials of the technology and cover the basics without trying to cover all the details and the newer features built on top of the basic MPLS VPN Layer 2 technology. I'll explain what the architecture looks like for both the point-to-point, this is VPWS, and the point-to-multipoint or VPLS services. Let's have a look at the architecture of MPLS VPN Layer 2. With MPLS VPN Layer 2, we will transport Layer 2 protocols obviously across the MPLS backbone. The Layer 2 protocol could be really almost anything. For example, Ethernet, PPP, FrameLay, ATM, and so on. There's really no interaction between the service provider edge routers and the CE edge routers or switches, any device really, at Layer 3. So there's no routing protocol adjacency between the PE and the CE device. And obviously, we will reuse the same network, which is the IP-MPLS core network. Sometimes we also refer MPLS VPN Layer 2 as ATOM, any transport over MPLS. There are really two kinds of services, VPWS, Virtual Private Wire Services. Here we are emulating a leased line. So this is a point-to-point service. Or we have VPLS, Virtual Private LAN Services. Here we have a point-to-multipoint service. The architecture, well, it's MPLS as we know it. In the core, we just use MPLS forwarding as we have seen so far. At the edge routers, we encapsulate and decapsulate the entire Layer 2 frame. The P routers are completely unaware of MPLS VPN Layer 2. They are just doing the forwarding of MPLS packets. For each end-to-end service, the PE routers, they will negotiate what exactly they are doing, which service. Is it a point-to-point or a point-to-multipoint service? But for either one, they will need to establish what we call a pseudowire, a PW, or a virtual circuit, a VC, between them. Once this pseudowire or circuit has been established, the PE routers can switch the Layer 2 frames between them with MPLS encapsulation. Each pseudowire will actually have an MPLS label bound to it. We will call that the VC label. And the signaling needed for these pseudowires to be set up between the PE routers is either done by targeted LDP or in some cases by BGP, but there this can only be done for VPLS. So some terminology, between the PE router and the CE device, be it a router or a switch, we have what we call an attachment circuit. So here, across this interface, the PE router will be receiving Layer 2 frames. We have a targeted LDP session between the PE routers. This is used to signal the pseudowire or virtual circuit end-to-end between the PE routers. Over this pseudowire, we will transport the Layer 2 frame. We'll have a VC label, which identifies to which pseudowire the packet belongs to. And we have the IGP label, a label signaled by LDP or maybe by MPLS TE. This label is also often referred to as the tunnel label or the transport label. What about signaling the pseudowire? This happens by the targeted LDP session between PE routers. The most important thing is that the signaling identifies what kind of a pseudowire is being signaled, what the transported protocol is, and also, very important, what the virtual circuit label is that will be used for the virtual circuit. In LDP, we have this information signaled by a new FEC TLV. We call that the pseudowire identifier FEC TLV. And it holds all the necessary information to signal this pseudowire between PE routers. And by the way, no matter how many pseudowires we have between a pair of PE routers, there is always only one targeted LDP session. So what do we have in this pseudowire FEC TLV element? We have the pseudowire type, also identifying the protocol being encapsulated. The group ID, which might be used as a wildcard to do some signaling for a group of pseudowires. The pseudowire ID, which is a number that uniquely identifies the pseudowire. And then some other parameters that refer to the attachment circuit interface. Obviously behind it we have the VC label, and that's also very important because without the VC label the packets will not be able to be forwarded. What are the possibilities for the pseudowire type? Well, there are a lot of possibilities. You can have frame relay, ATM, HDLC, PPP, and Ethernet, of course. Some are more popular than the others. These days, the real popular one is the Ethernet one. How do we signal the status of the pseudowire? Well, basically, as soon as this pseudowire identifier FEC TLV has been advertised, that should bring up the virtual circuit. To bring it down, there are really two methods. The router can either send a label withdraw message or a pseudowire status TLV. The label withdraw message is the older method. Basically, by redrawing the VC label, the pseudowire will go down. The newer method is the pseudowire status TLV. This does the same as with the label withdraw method, but here we can have more states being signaled. Here's an example. It could be, for example, that the local attachment circuit has a receive fault or a transmit fault, and so on. So there are a couple of more status codes that can be advertised. Very important is also the control word. You might have noticed that in the pseudowire FEC TLV being used, we had a C bit there. That C bit, if it is set, will indicate that we have a control word. It means that in between the transported layer 2 frame and the MPLS labels, we have a control word. The size is 32 bits. The usage is what we will see in the next slide, but there are many usages for it. This is how it looks like. It always starts with 4 bits set to 0. We have some flags. We have a B and E beginning and end bit, a length, and a field for sequence numbers. Now, important to note is that for some protocols, this is a must. The control word must be present, always. For some other protocols, it might or might not be needed. And usually, this is not a worry for the operator. It is the routers that will start to use this control word automatically or not. So what use cases are there for the control word? There are basically 5 functions. 1 is to pad small packets. If the transported layer 2 frame is too small, then we can bring it up to the minimum size needed. Typically, this is needed for Ethernet in some cases. For some layer 2 protocols, we need to carry control bits from the layer 2 header, and we will put those control bits or flags from the layer 2 frame header and put them in a control word. An example is frame relay. There, for example, we will put the FECN and beckon bits, which are used for congestion notification. Those 2 bits we will put in the control word. Third one is to preserve the sequence of the transported frames. So by using the control word, we can add a sequence number. This happens at the ingress PE router, of course, where the control word is added. At the egress PE router, who strips off the control word, he can look at the sequence numbers and sees if, on a particular virtual circuit, all the frames are coming in the right order or not. And then it's up to the implementation to either reorder them, if they're out of order, or just drop the frames altogether. Fourth one is load balancing. It is to make sure that the load balancing always works. One example is where P routers do the load balancing of labeled packets in a particular way. The P routers, they might look behind the MPLS labels, try to find the IPv4 header, and do the load balancing based on the source and destination IP address. Obviously, this will only work if it's an IPv4 packet. That means that the first 4 bits have the value 4. But sometimes it's possible that a layer 2 frame being transported also has its first 4 bits set to 4. Then the P router will go behind the labels, find the first 4 bits being 4, and try to do a lookup of the source and destination IP address, which will fail because it's an Ethernet frame. So to avoid this, we will put the control word in between the labels and the transported layer 2 frame. And then the first 4 bits after the labels are 0. So in this case, the frame, the packet being transported by MPLS cannot be mistaken as an IPv4 packet. Fifth is to facilitate fragmentation and reassembly. This is why we have the beginning and end bits present. The usage of these 2 bits will allow the ingress PE routers to fragment the frames when they are too big to be transported over the virtual circuit. At the remote end, so the egress PE, this router will then be able to reassemble the frames. So how does the packet forwarding look in an MPLS VPN layer 2 network? So we have the targeted LDP session between PE routers. It signals a pseudo-wire end-to-end for the particular attachment circuit. We might have any kind of layer 2 between the PE and the CE device. When the layer 2 frame comes in on an ingress PE router, it will do a lookup and add 2 labels. First, the VC label, signaled by the targeted LDP session, and then the IGP label or transport label, which is the label typically tied to the loopback IP address of the remote PE router. So this is the label that gets the packet towards the remote PE. Again, in the regular cases, we have penultimate hop popping, so the packet actually arrives at the egress PE without an IGP label and just with the VC label. The egress PE will then do a lookup in the LFIP, the label forwarding table, for that VC label. We'll find an entry, strip off the label, and forward the layer 2 frame on the correct outgoing attachment circuit. The most popular case is Ethernet over MPLS. We can transport any kind of Ethernet frame, with or without VLANs, maybe even 2 VLANs or more. Important to note is that there are 2 types of Ethernet emulation. We have what we call the VC type 4 and the VC type 5. The VC type 4, also referred to as the VLAN mode, means that there is a VLAN header present and the PE routers will look at the VLAN header and maybe make a forwarding decision based on that. With VC type 5 or the port mode, there might or might not be any VLAN header present, but the PE routers will never look at it. The typical usage cases here is for the PE routers to transport a complete Ethernet trunk over one pseudo-wire. So what is actually transported with Ethernet over MPLS? We transport the complete Ethernet frame with or without the VLAN header if there is one present, but we do strip off the 7 bytes at the beginning, the preamble, the 1 byte start of frame delimiter, and then at the end the 4 bytes for the frame check sequence. All the rest is transported. Q&Q is a tunneling mechanism used in switched networks. So here we do not have an MPLS network, but a switched network. It's layer 2 end-to-end. This was used by service providers to transport many VLANs, here we have 50 VLANs of a customer, over one backbone VLAN across the service provider network. So in the end, the Ethernet frames were transported with 2 VLAN headers. The customer VLAN between 1 and 50 and the VLAN 800, which is the service provider VLAN end-to-end. The same can be done with MPLS, and we call that Q&Q with Ethernet over MPLS or .1Q tunneling over MPLS. In that case, again, the customer VLANs 1 to 50 are transported over a service provider VLAN end-to-end, transported over the pseudo-wire. In this case, we can carry a lot of the customer VLANs, complete trunk, over one pseudo-wire. What about the VLANs? Well, In most cases, the VLAN number on both sides of the network, so the attachment circuit at both sides, at both PE routers, they have the same number. And you would not have to configure anything special for the forwarding to work. But in some cases, we might have an asymmetric setup. We might have an additional VLAN at one side compared to the other side. And in that case, on one router, you would have to pop the VLAN before forwarding the Ethernet frame. And on the other side, you might have to push the extra VLAN before forwarding the Ethernet frame. And in some cases, there is VLANs on both sides of the network, but the VLAN number doesn't match. In that case, the PE routers are able to translate the VLAN tags from one number to another, so that the forwarding of Ethernet frames works end to end. Let's have a look now at MPLS VPN Layer 2 for point-to-point services, or VPWS. We have a network here, a very simple network with just 3 routers running MPLS, 2 PE routers, 1 P router. At either side, we have an attachment circuit from the PE router to a CE device. Now, it is an attachment circuit, so the PE router will receive Layer 2 frames, Ethernet frames, and transport them over the pseudo-wire towards the remote CE device. The 2 CE devices here are routers, and they are configured to be in the same IP subnet. Let's have a look at router 1. What do we have? The configuration is very simple. We have a pseudo-wire class configured. The name is Atom. And we specified that the encapsulation is MPLS. There are a few other options that you can configure here, but you do not need to use them. And on the interface on the PE router towards the CE device, the attachment circuit, we would just have to configure an xconnect command, point it to the loopback IP address of PE2, specify the VC number, 102 here, specify that the encapsulation is MPLS, and use the pseudo-wire class that we configured before called Atom. If you do that on PE router 2 as well, that should be enough to bring up the pseudo-wire. Now, to bring up the pseudo-wire, we need to have a targeted LDP session. The first time you configure any pseudo-wire between the pair of PE routers, that should bring up the targeted LDP session. Let's have a look. And now we see that indeed there is a targeted session from PE1 towards PE2. Over this targeted session, we will have the pseudo-wires signaled. Let's have a look what we have as pseudo-wires. Show xconnect all, we see that at the moment we have one pseudo-wire. It comes from attachment circuit gig2 on this router, and it ties up with the pseudo-wire, the second segment, the pseudo-wire over MPLS encapsulation, of course, towards router 2, and the VC number or pseudo-wire number is 102, and it's already up and running. Let's have a look at it in more detail. Now we can look at the specific virtual circuit number towards that pair, and we see that we actually have a local VC label 16. That means packets coming in on the pseudo-wire will have a top label of 16. Packets going outbound of this router on the virtual circuit of pseudo-wire will have a VC label of label 19. So if packets are coming in with label 16, we will strip off the labels on this PE router and forward the Ethernet frame on the attachment circuit, gigabit Ethernet 2. The router would find that label by doing a lookup in the LFIP. So we do show MPLS forwarding table, labels, and the local VC label is 16, so we'll have a look at just label 16. Indeed, packets coming in with MPLS label 16, we strip off the label, we forward it outbound as a layer 2 frame on gig 2, which is the attachment circuit, to the local CE device. With the command show xconnect, we did not see too much information. We only saw that the state was up, the VC number, and the VC labels. There is another command to see more details. Show MPLS L2 transport VC102 detail. And here we see a lot more information. We see the complete label stack that we would push on top of the packet when forwarding the packet outward on the pseudowire to the remote PE. This is the transport label or IGP label to get the packet to the remote PE router. We see some other information which relates to the status TLV, but we see that there are no faults here. We see the MTU, so the maximum size of Ethernet frames that we can transport. We see the local and remote VC label again. And very importantly are these values that track the amount of packets or bytes sent and received over the pseudowire. So obviously these VC statistics are very important when you are troubleshooting a pseudowire. You need to be able to figure out if the pseudowire is forwarding Ethernet frames and receiving Ethernet frames. The transport label that we had here was label 17. Where did it come from? If you do show IPsef 10.100.1.2, which is the loopback IP address of the remote PE router, then we see indeed the outgoing label to get the MPLS packet to that remote or egress PE router is label 17. Now, is the virtual circuit really working? Well, let's have a look. So on either side we have two CE devices connected to the PE devices through Ethernet. The two CE devices, they have the same subnet, and I just configured enhanced IGRP on those gigabit Ethernet interfaces. If everything is fine, the layer 2 frames will be sent from CE1 to CE2 transparently. So at layer 3 it is as if CE1 is directly connected to CE2. So if everything is fine, the two CE routers should form an eIGRP neighborship between them. And they do. CE1 sees CE2 as a neighbor over the attachment circuit. That's how point-to-point Ethernet over MPLS works. Let's have a look at point-to-point versus point-to-multipoint services. So we have two kinds of services. The VPWS, the Virtual Private Wire Service, emulating a leased line, and VPLS, Virtual Private LAN Services, emulating a LAN. This is really a point-to-multipoint service. With VPWS, we have point-to-point, so we will just have one virtual circuit or pseudowire between a pair of routers per attachment circuit. With VPLS, the point-to-multipoint service, we will actually have a full mesh of pseudowires between all the PE routers per attachment circuit. So if we have a network of MPLS VPN layer 2 for one particular customer who's going to do VPLS, so point-to-multipoint service, we will have a full mesh of pseudowires. This is done by configuration, and because we have a virtual circuit between every pair of routers, so we have a full mesh, there's no need anymore for a spanning tree in the core. However, we must make sure that the layer 2 frames are not looping. So when one PE router receives a layer 2 frame over one pseudowire, it will not forward it back out into the MPLS core over another pseudowire. So we have split horizon between the pseudowires, and this is enabled by default. And of course, every customer must sit in its own private VPN. So each VPLS instance will have its own VPN identifier. In the end, the PE router will just switch Ethernet frames from the attachment circuit over the pseudowires, and also it will switch received Ethernet frames from the pseudowires over the attachment circuit. With VPLS, we are emulating a LAN. In the end, the goal is for the whole MPLS VPN cloud to look like a layer 2 switch towards the VPLS customer. So the whole MPLS VPN cloud must behave like a layer 2 switch. What does a layer 2 switch do? It will forward out broadcast traffic. It will forward out multicast traffic and of course also unicast traffic. But for it to be able to do that, it must have MAC address learning and MAC address aging. Also, if it receives a frame for which it has not learned the destination MAC address yet, it will forward it out over all interfaces. We call that unknown unicast learning. What about the VPLS data plane? It's similar to the data plane as we have seen with point-to-point Ethernet over MPLS. We just have a tunnel or transport label to get the packet across from ingress to egress PE router, and we have a VC label per pseudowire, of course. That's it, just two labels. In the core of the network, we just have MPLS forwarding. The encapsulation, hence, is just the Ethernet layer 2 frame with a VC label on top of it, and the IGP or transport label or tunnel label on top of that. How do we configure it? Well, the configuration must somehow be like an Ethernet layer 2 switch. We are going to tie in the attachment circuit with the pseudo wires at the other side. In the end, we will have something which refers to the layer 2 VPN with a unique identifier for the VPLS customer, and then tie in the pseudo wires which are configured here, one to each remote PE router, with the local attachment circuit. All of that together will be in a particular bridge domain. So in the end, the PE router or the whole VPLS setup will behave like one Ethernet switch for that particular VPLS customer. If there is a need for layer 3 termination at the PE router, there is a possibility to configure what we call a bridge domain interface. With that, we can have an interface at the PE router with layer 3 enabled, so it will have an IP address. Then we can terminate for the bridge domain the frames as layer 3 on that interface. What about multicast traffic? Well, multicast traffic is different than unicast, obviously. It will have to be forwarded out on more than one interface, typically. So with VPLS, there is the possibility that multicast traffic is forwarded out on several pseudo wires at the same time. So what we do not want is that multicast traffic is forwarded out like broadcast traffic. So it is forwarded out on all pseudo wires. To avoid this, what we can do is enable PIM or IGMP snooping. With these features enabled, what the PE router will do is typically sniff or sense the PIM or IGMP control messages and figure out which port, be it the attachment circuit or pseudo-wire port, where we have receivers behind which are interested in receiving the multicast traffic. If it finds out such PIM or IGMP messages, then it will keep on forwarding the multicast traffic on those ports. If it does not find any PIM or IGMP messages indicating that there are receivers behind the attachment circuit or pseudo-wire, then it will not forward the multicast traffic on those ports. What about HVPLS or hierarchical VPLS? We still have a VPLS core in the center with a full mesh of pseudo-wires between the PE routers. But now we will extend the VPLS into the access layer. From what we now call the network-facing PE router, we will have either Q&Q, so double encapsulated VLANs, or point-to-point pseudo-wires to what we call the UPE, the user-facing PE routers. So there's a possibility here to have point-to-point pseudo-wires. In the end, the traffic from the CE user devices will be forwarded first over a point-to-point pseudo-wire if we are using MPLS in the access layer, then across the true VPLS domain where we have the full mesh of pseudo-wires, and then back out on point-to-point pseudo-wires. The thing here is that on the NPE router, we might receive a layer 2 frame on the point-to-point pseudo-wire, and we need to forward the Ethernet frame onto the pseudo-wires in the VPLS domain. So for this traffic, the split horizon will have to be disabled. And finally, instead of using targeted LDP between the PE routers, IBGP can be used. Now there are two functions that IBGP can do. The first one is auto-discovery. With IBGP, the PE routers can discover each other and figure out, hey, this and that PE router wants to do VPLS. The second thing is IBGP can actually be used to signal the pseudowire itself. For that we need a new address family, L2VPN VPLS. And over this address family, layer 2 information will be sent by IBGP. And IBGP, typically it means that we have a full mesh of IBGP, or there might be router reflectors in between. But whatever one PE router sends out is received by all other PE routers. And the most important thing to set up the pseudowire is the VC label. What a PE router will do is send out a block of VC labels. That block of labels will be received by all the other PE routers. Then it's up to the remote PE router to tie one particular label out of that block to one particular pseudowire. And it will use a particular algorithm to do that. Once both sides, both PE routers, have picked a VC label, it will program that VC label as an incoming label in the LFIP, and the pseudowire will have been signaled. So for the BGP signaling, we will have this IBGP full mesh, or through router reflectors, between all the PE routers. Through the address family L2VPN VPLS, certain information will be advertised, like the PE router endpoint, the VPLS identity, identifying the customer, the block of MPLS labels, which is the most important information, and encapsulation, for example, some Ethernet encapsulation information. Once that is advertised, all the PE routers will pick out of the block of MPLS labels one particular label according to an algorithm, and this will mean that the pseudowires will have been programmed in hardware and set up for the VPLS instance. Let's have a look at VPLS in the live demo. We have a sample network here. We have 3 PE routers, and each time we have one attachment circuit, Ethernet of course, towards a CE device, in this case each time a router. So we have 3 CE routers, and they're all connected through VPLS. So we have a full mesh of pseudowires, and they are signaled by targeted LDP. Let's see how it works. Let's have a look first at the configuration. Show running config. We have the L2VPN defined here for a context of a specific customer, the VPN identifier, which uniquely identifies the VPLS domain, and then we have the 2 pseudowires defined. The pseudowire towards router 3 with virtual circuit 103, the virtual circuit towards router 2 with virtual circuit 102. In the end, we only have 3 PE routers, so this would make up the full mesh of pseudowires. And then we look at the attachment circuit. At gigabit Ethernet 2, we defined what is called a service instance. So this means it's tied in to some L2VPN service. Service instance is tied here into a bridge domain 100. So here we have 2 members. On the one side, the attachment circuit, service instance 1 for gigabit Ethernet 2, and on the other side, the VPLS. So the VFI stands for the virtual forwarding instance, which means all the pseudowires participating in this particular instance of VPLS. Let's have a look at this VFI. It is active. We see that the signaling is LDP, not BGP. It's point-to-multipoint, obviously, and it has been signaled. So we have the 2 pseudowires, each with their own virtual circuit, and both of them are up. Are the targeted LDP sessions actually up? We can, of course, verify. We show MPLS LDP neighbor, and we see indeed that we have a targeted LDP session towards router P2 and a targeted LDP session towards router P3. So what about the virtual circuits? We can do show xconnect all, and indeed we have the 2 virtual circuits up and running, one to router P3, one to router P2, and also considered to be an xconnect is the VFI under bridge domain 100. Let's have a look at one of them in more detail. Show xconnect peer 10.100.1.2, which is P2, VC ID 102, detail. We have this pseudo wire again. Now we also see the local label is label 19, the remote label is label 16. Well, those are the VC labels. Local label is VC label 19. That means that this label must be programmed locally into the LFIP. Let's have a look at that. So show MPLS forwarding table labels 19, and indeed when packets come in with label 19, we would strip off all the labels, forward it as layer 2 frame onto gigabit 2, the local attachment circuit. There is another command to look at the virtual circuits, which is show MPLS L2 transport. And here again we can see lots more details. We can see the outgoing interface into the core. We see the complete label stack being pushed, the VC label 16, the transport label 18. We see some of the status TLV entries. There are no faults here. We see if the control word is used or not. And importantly, again, are the VC statistics, proving that the VC is actually forwarding and receiving packets or not. We had a transport label of label 18. Where did that come from? Well, that is the label to get the packets into the core towards a remote router PE2 in this case. Let's verify that. So we type show IPsef 10.100.1.2, which is the IP address, the loopback IP address of the remote router PE2. And indeed, we see that packets here will be going out towards that router with a label 18. So what about that bridge domain that ties in the VPLS side on the PE router with the attachment circuit side? Let's have a look at that. Show bridge domain 100, which was the bridge domain number tied in with this VPLS instance. We see that it's up and learning, MAC address learning is enabled. We have 2 pseudo wires tied into it and 1 attachment circuit. And actually the MAC address learning is working. We see that we learned 1 MAC address on one particular pseudo wire, another MAC address on the other pseudo wire, and a MAC address from the locally attached CE device over gigabit Ethernet 2, the attachment circuit. Now, depending on the platform, there will be a command to figure out which port this is exactly. This is easy, this is gigabit Ethernet 2, but this is one particular pseudo wire port and this is another. Which ones exactly? We can check with the command show platform software Ethernet FP active VFI. And now we see exactly what those 2 ports mean. This port was tied to bridge domain 100, both of them, but it's virtual circuit 102, so the virtual circuit going to PE router 2. And this one is the pseudo wire port bound to VC ID 103. So that's how we figure out the port mapping for the pseudo wires. One more thing, let's verify that VPLS is actually working. So the 3 CE routers, they have been configured with the same IP subnet on this interface towards the PE router, which is the network 10.2.1.0/24. And I configured enhanced IGRP. So in principle, the 3 CE routers should see each other directly connected as eIGRP neighbors now. Let's verify that. We have CE1 here. Let's verify that it sees the other 2 routers, CE2 and 3, as neighbors. Yes, so both CE2 and CE3 are seen as enhanced IGRP neighbors over the link towards PE1. So we know that VPLS is working. Both unicast traffic and broadcast traffic will be working, and multicast as well. And we know that because eIGRP hellos are actually sent out as multicast traffic towards the VPLS domain. Hello and welcome to lesson 8. This is another long lesson and it covers MPLS traffic engineering or MPLS TE. I'll start off by explaining what traffic engineering is and what the advantages are. I will then explain the routing protocols extensions made for MPLS traffic engineering, which signaling protocol is used for MPLS TE, and how it functions. There is a sub-lesson of how the routing works and how the cost of the TE tunnel is calculated. The next sub-lesson is also very important, as I'll explain how to get traffic onto the traffic engineering tunnel. I'll round off this big lesson by explaining the protection, the so-called fast reroute or FRR, with traffic engineering, and by explaining why you should be careful when using TE tunnels together with MPLS VPN Layer 3 services. Why would we do traffic engineering or TE? First of all, what did we do with IP routing? What was the paradigm of IP routing? Well, with IP routing, it's really all about getting IP packets through the IP network on the least cost path. So get them through the network from ingress to egress side as fast as possible. We've always followed this least cost routing principle. Basically, it means that at every hop through the network, we do a lookup of the IP destination address from the IP header, look it up in the routing table, and forward the packet onwards. So every router at every hop makes a decision, and in the end the forwarding will be on the least cost path. Basically, every router does this independently from what any router has done before or after it. With MPLS TE, this will not be the case. What are some of the downsides of IP routing? While if every router forwards all the packets on the least cost path, it might happen that some of the links are overutilized and some of the links are not utilized at all. Look at this small network at the right hand side. If we have traffic to be forwarded from router A to B, typically the traffic will only take the top path, even though there is an alternate path available. But this introduces a second hop. This might not be bad because one of the links actually has a higher bandwidth, but all of the traffic will take the top link and the bottom link will be underutilized. With traffic engineering, we will try to avoid having overutilized and underutilized links. Typically, when you have overloaded links, packets will be dropped in the IP world. There is no feedback to change any kind of routing, so there is no adaptive routing at all. With MPLS TE, you can have adaptive routing. So based on the usage of a link, the routing of packets can change. So with IP routing, there's no easy way to affect this routing. Let's have a look at this small network on the right-hand side. Router A can forward IP packets to router B. But no matter what it does, it will always forward the IP packets to router B, and then router B will make a decision to forward the packets over the top or bottom path. Probably here over the bottom path because the bandwidth is higher and then typically the link cost for IGP is lower. So A cannot make really here a decision to forward the packets over the top path. With MPLS TE, because we will use the advantages of MPLS forwarding, router A will be able to put a label on top of the packet so that router B is forced to forward the traffic over the top path. In an IP network, you might say, well, we can play with the metrics and affect the routing. Yes, this is possible. Typically, when you change the cost or the metric of a link, it will affect the routing, but it will affect all prefixes, not just one or two. So you might want to change the routing of one or two prefixes, but the side effect might be that it changes the routing of all the prefixes. And that's probably not what you want. You want to be able to be very selective in this. So what are some of the advantages of MPLS TE? Well, as we mentioned before, we have these overutilized and underutilized links. With MPLS TE, we will be able to have an efficient spreading of the traffic over the different paths and links. Also, we can take into account the bandwidth of the links and how much traffic is forwarded over the link. So the bandwidth usage as well. And this will be adaptive. So there will be feedback from routers who see a particular bandwidth usage on a link back to the source router, because MPLS TE is source routing in the end. And this will affect how the traffic is forwarded through the network. So MPLS TE is adaptive. Like I mentioned before, we will have source-based routing. That means that it is the source or the ingress router that determines the path of the packet. It can do that by using the power of MPLS, because it chooses which label to put on top of the packet. That will nail down the path that the packet will take through the network. Routers further downstream that receive the packet, we will just have to do a label lookup in the LFIP, swap it out with another label, and forward the packets onwards. They do not make a routing decision. They just forward the packet based on the label. And that label has been assigned to the packet by the ingress router. Hence we have source routing. And last but not least, it's probably even, maybe, sometimes the most important reason is fast protection. So if a bad event happens in your network, like a link going down or a complete router going down, these days we want the traffic to be rerouted around the failure very quickly. And that's what traffic engineering can give you. Traffic engineering was invented quite a long time ago, and in that time we could not have fast protection with IP. Nowadays, in a pure IP network, we do have solutions to have fast protection for IP traffic. But many years ago, the only way to deploy fast protection in your network was to have MPLS traffic engineering. Let's have a look at the distribution of traffic engineering information by the IGP. First of all, the routers need to be able to calculate a path through the network. If a router needs to do this source routing or calculate a path through the network, it needs to have a good topology view of the whole network. Otherwise, it would not be able to calculate such a path. Which routing protocols have a good view of the network? Well, it's typically the link state routing protocols. And we have two of those, OSPF and ISIS. Typically in OSPF, there is a database per area. And typically in ISIS, there is a database per level. So a router can have a good topology view of that specific area or level. So for traffic engineering, there will be one requirement. You need a link state routing protocol. So what is the topology view? Well, if you just look at IGP, what we've always had with link state routing protocols is that in the database, we find back routers, links, IP addresses, and link costs or metrics. And that's typically what is present in the database of OSPF or ISIS by default. But for traffic engineering, we want something more than that. We want to be able to route traffic based on reservable bandwidth downstream or bandwidth available. So we must have a mechanism to advertise this bandwidth information. Also, there is something what is called affinity bits or resource bits, which I'll explain on a later slide. And we have MPLS TE metrics, which are different than the IGP, OSPF or ISIS metrics. So all of these kinds of information we cannot by default advertise by OSPF or ISIS. So we needed to have TE extensions to OSPF and ISIS so that OSPF and ISIS can advertise this TE specific information. And that's what we did both to OSPF and ISIS. In the end, the source router can then calculate a path for a specific flow of traffic through the network based on this topology. So based on the IGP topology and the TE information. One of the TE resources is bandwidth. By default, the bandwidth is just the default speed of the link. But if you want to, you can override that by configuring a bandwidth statement on the link, for example. There is also something as the maximum reservable bandwidth. This is the maximum bandwidth that can be reserved by TE. And of course, that value can be lower than the total bandwidth of the link. You would change that just by configuring the RSVP bandwidth interface command on the interface, of course. This will allow the head-end router to calculate a path based on the available bandwidth of each link along the path. And then we have the affinity bit, or the color bits, or the resource bits. They have different names. Typically, this is a field of a number of bits which is mapped to a link. For example, you could have 32 bits in the field, and those 32 bits you can configure on a link. There's no official meaning of each bit in that field, but the meaning is given by the operator of the network. For example, the operator might say bit 2 means do not cross the ocean. So that's a link that doesn't cross the ocean. Or, for example, bit 3 means the delay is under 50 milliseconds. So for the affinity bit or the color bits, the operator can set 1, 2, 3 or all 32 bits in that field, and each bit will have a specific meaning that the operator gave to the link. And based on these bits, because these bits will be attached to a link, and that information is flooded, of course, by OSPF or ISIS throughout the whole area or level. And then the head-end router can calculate a path based on those bits, because the operator can assign the same bits to a tunnel. And he might say the tunnel or the traffic engineered path through the network should be crossing only links with a delay less than 50 milliseconds. In that case, the tunnel will try to only cross links where the third bit is set. And it might be that it does not find a path. In that case, the tunnel will not be found, and we will not have a path through the network for that requirement. The MPLS TE metric is an alternate set of metrics or cost of the links. So we have the cost of the links, which is set by OSPF or ISIS. Now we have another set of links, which is governed by traffic engineering. And basically this will allow traffic engineering to have a different view of the topology than OSPF or ISIS. That's just in case that you want your IP routing to be different than your routing in the TE world. But by default, the TE metrics is the same as the IGP metric. So if you want to have a different TE topology, you would have to configure the TE metrics on the specific links in your network. So how does this TE information get flooded? Well, we need extensions. So the first link state protocol is OSPF. For OSPF to be able to flood the TE specifics or characteristics or resources throughout the network, it needed some extensions. The RFC 2370 provided those extensions really, because there 3 new LSAs or link state advertisement packets were defined. We had the type 9, which had a scope which was link only, so that LSA is flooded from router to router, just one hop, and that's it. We had the type 10, which was area-wide, so those LSAs are flooded throughout the area, but not beyond, not into another area. And LSA type 11s are autonomous system-wide LSAs. They are flooded throughout the whole AS, in all areas. These opaque LSAs are really LSAs which are opaque to OSPF, or kind of transparent. OSPF will use it to advertise information, but this information is not really related to OSPF directly. So we can use it for traffic engineering, because those opaque LSAs could be used to advertise traffic engineering information, but that traffic engineering information is not directly related to OSPF. OSPF will not use that TE information. For traffic engineering, LSA type 10s were chosen. So those opaque LSAs, the type 10s, are used to advertise traffic engineering information, like the TE metric, the affinity bits, and so on, throughout the whole area. For ISIS, similar extensions had to be made. Now, ISIS works differently. It doesn't have LSAs, but it uses TLVs, or type linked values, which are packet formats used by ISIS. There was also an RFC 3784 which defined those extensions or new TLVs to be used to be able to support MPLS traffic engineering. Those TLVs will be carried in the LSPs. Typically an ISIS router advertises one LSP per router per level. Inside that LSP or the link state PDU, we will find this new TE information. And mind you, when deploying traffic engineering, you must have wide metrics deployed. Typically by default, ISIS still uses narrow metrics, which means that we'll have only 6 bits to define the metric or the cost of a link in ISIS. But for TE, you must enable wide metrics, which means that we will have a 24-bit field for the cost or metric per link. What about the flooding? Well, all of this TE information needs to be flooded throughout the area or level. So typically in OSPF, it will advertise an opaque LSA type 10 when needed. And in ISIS, it will re-originate the LSP when needed. But what does it mean when needed? Well, typically, when there's a link status change, of course, OSPF or ISIS will reflood. The same if you make a configuration change, but we also have periodic flooding, both in OSPF and ISIS. But specifically to TE, so to traffic engineering, if there's a change in the unreserved bandwidth on the link, meaning a tunnel was just set up, crossing the link, and the available amount of bandwidth has lowered. In that case, the routers on both sides of the link will reflood their opaque LSA or LSP if it's ISIS. And the same will happen after a tunnel setup failure. It might be that the tunnel head and router thinks he can set up a tunnel or a traffic engineering path end to end. And once the signaling proceeds, we will see how that works later on, it might be that somewhere in the middle the signaling fails. The router will notice that. And maybe the reason is that the headend thought there was enough bandwidth, but some of the bandwidth was just taken by another TE tunnel, a couple of milliseconds before, for example. Then the second tunnel that tries to be signaled across that link, it will fail. And that would be the trigger for the routers connected to that link to reflood their information and say, okay, now the reservable amount of bandwidth available on that link is now actually lower. And then the headend router who tried to signal that tunnel, but which failed, will now know, right, there's now less bandwidth available on that link. I need to calculate a new path avoiding that link. Let's have a look in the live demo how the IGP distribution of TE information works. We have our lab network here, 7 routers. We are actually running OSPF. We could have been running ISIS as well. It's really very similar, but throughout lesson 8, we'll be using this particular network and only showing OSPF. Every router has a loopback prefix, which is 10.100.1. something. And the dot something, the last octet, is really the number of the router. The link prefixes are 10.1.something.something/24. Let's have a look at the TE information that gets distributed. This is router 1. Actually, first of all, let's have a look at how traffic engineering will be configured, which is actually the easiest part. Let's have a look at the show running configuration. We can see here that traffic engineering has been enabled globally, and also what you must have is on each interface you must have MPLS traffic engineering tunnels configured so that TE is enabled on that interface. Now there is one other command which is needed on the interfaces. This is the IP RSVP bandwidth command, and then a value. Here the value is 1 gigabit per second. Often this command is forgotten. Then under the IGP, OSPF or ISIS, you must enable traffic engineering. Here traffic engineering is enabled only for area 0, and we also set the traffic engineering router ID to be the loopback 0 IP address. And that's really it. As soon as you do that, the TE information gets flooded by OSPF. As it's OSPF, the TE information gets flooded by opaque LSA type 10s, the opaque area LSA. Since this is link state protocol, we can look from router 1 and you should see the database of the whole area. So all our 7 routers are in area 0. And then we'll have a look specifically in router 2, which has 3 links one to router 1, one to router 3, one to router 6. And we'll have a look at the OSPF LSAs and the TE information being flooded. So let's have a look at the OSPF database. It's a simple area. Inside this area 0, we only have router link state LSAs, so LSA type 1s, describing the links of each router. We can see that we also have the type 10 LSAs, the opaque LSAs. And these are used to carry the TE information throughout the area. And we can see, because we have traffic engineering enabled on every router, that every router advertises one or more type 10 LSAs, and we'll have a look now inside what TE information we can find there. So let's have a look at opaque LSAs, and they are area LSAs, only at one specific router. So let's have a look at the opaque area LSAs advertised by router 2, which has router ID 10.100.1.2. So this is the information that we get. So the advertising router is 10.100.1.2. What should be inside? Inside we should have links. And the first one is the link from router 1 to router 2. We have another link from router 2 to router 3. And we have the third link from router 2 to router 6. So all three links are there, and each link has a specific amount of TE information. What exactly? Well, we have the IP addresses on either side of the link. We have the admin metric, which is actually the TE metric, typically the same as the OSPF metric or cost of the link. We have the maximum bandwidth of the link. Now notice that all these values here are actually in bytes per second. So to get the value, for example, that you configured on the link, you must multiply it by 8, so you get the value in bits per second. We have the maximum reservable bandwidth. This is the IP RSP bandwidth command on the interface. You can have tunnels of different priorities and how much bandwidth is left per priority. We have these affinity bits or resource bits or attribute bits or color bits. They're all the same thing. So this is a field where the operator can set each bit individually, and each bit means something to the operator. For example, a certain delay or jitter. And then finally the IGP metric, which is just the OSPF cost, in this case, of the link. And this will be repeated for each link from that router 2. In the end, a traffic engineering topology database, or TED, will be built. Let's have a look at that database. So we have the command show MPLS traffic engineering topology. Let's do brief, limit the amount of output. And we can see here different routers. We can look at the IGP ID. So we see here 10.100.1.2 is the router ID of router 2. It advertises 3 links. They're all point-to-point links. And we have a certain amount of information there, like the TE metric, the attribute flags, or the resource or color bits, and so on. If you want to look in more detail, you do the command without brief. And now you see the full amount of information, meaning the TE metric, IGP metric, attribute flags. But now you also see the reservable bandwidth still available at a specific priority. These priorities will indicate how important the tunnels are. The lower the priority, the more important. So a tunnel with a lower priority will actually take bandwidth away, which is no longer available to tunnels at lower priority, meaning a higher number here. Let's have a look at RSVP. RSVP, or Resource Reservation Protocol, is really a protocol that was around even before traffic engineering. It's a signaling protocol. Now we need a signaling protocol for traffic engineering for several reasons. But the main thing is, for example, that we need to have a mechanism to propagate the label from the tail-end router to the tunnel head-end router. So RSVP was around. It was mainly used before TE for integrated services, which is a kind of quality of service signaling, but it was not very popular. It was enhanced through an RFC 3209 so that there were extensions to RSVP, so that RSVP could do the signaling for traffic engineering. And then RSVP actually did become popular, but solely because it is used for signaling traffic engineering. Remind you that RSVP is a soft state protocol. There are no acknowledgements. So when RSVP sends an update, it will need to repeat that periodically. That's why it's a soft state protocol. If something does not get periodically updated, the state that it created will eventually time out. So that's something to keep in mind. There are really only two messages which are important in RSVP. These are the path and reservation messages. The path messages are always sent from head-end router to tail-end router. So when traffic engineering calculated the path through the network, you will have a tunnel. And the tunnel will be from the head-end router, the calculating router, to the tail-end router, or the egress router of the tunnel. And reservation messages are actually sent in the reverse direction. They're always sent by the tail-end router towards the head-end router, or the calculating router of the tunnel. Let's have another look at the path messages. So these path messages are sent out after the head-end router has calculated a path through the network. It does that by looking at the TE database, finding possible paths, picking one, and then this path must be signaled end to end. So that means that the head-end router shoots out a path message through the network, which will be forwarded hop by hop towards the tail-end router. Reminder, this path is not necessarily the least cost path. And because of that, we must have a mechanism so that the path messages follows the path which was calculated, which is not necessarily the least cost path through the network. And to be able to do that, we have what we call an explicit route object, or an ERO, inside the path message. This is really an ordered list of IP addresses, and each IP address identifies a link or a router that this path message should cross. So imagine that your tunnel head-end router calculates a path of 8 routers. Then inside this ERO, the explicit route object, we will find 7 IP addresses. So the 8 routers minus the head-end router. This is how the path message will be forwarded throughout the network. Basically, the router will look at the ERO, figure out what the next hop is, so the next downstream router, that the path message needs to be forwarded to. And then it will shoot off the message to the next downstream router. The next downstream router again looks at the explicit route object, finds the next IP address, removes that, forwards the explicit route object further downstream, and so on. So the ERO is really the path which is explicitly mentioned in the path message. Another thing that the path message holds is the resource request. It could be the bandwidth, and it's probably the most important one. So if the tunnel wants to set up a tunnel end-to-end of 500 megabits per second, for example, this bandwidth request will be mentioned here. But another resource request could be, for example, the affinity bits. It could be that, for example, the tunnel should be crossing only links with a delay of less than 50 milliseconds. So one of those bits then will be set requesting that specific resource or affinity. Also important is protection. A lot of people deploy traffic engineering for protection. So you have a choice. You want your tunnel to be protected or not. If you want the tunnel to be protected at every hop along the path, you must configure it on the tunnel head end. If you do so, then there will be a bit set in the path message saying that protection is requested. And finally, also important is the label request object, because without MPLS labels, there will not be MPLS forwarding end-to-end. So the tunnel does request a label. This path message will be forwarded hop by hop through the network, and each time the path message crosses a router, the router will keep track of the path message by storing a little bit of that information into the path state on the router. The reservation messages, they travel back along the same path, but from tail end to head end router. It must be on exactly the same path, of course. And one of the reasons is that they will carry the MPLS label. So along the path, each intermediate router will store a little bit of the reservation information on some reservation state on the router. Each time the intermediate router will assign a local label to that tunnel and advertise this label back upstream. So the reservation message, its most important purpose is to carry this MPLS label upstream back to the tail-end router. And this way, at every intermediate router, we will always have an outgoing label and an incoming label. The incoming label is the label assigned by the router. The outgoing label is the label received from the downstream router through the reservation message. This also means, of course, that we will not need LDP at all. It is traffic engineering, or RCP for traffic engineering, that takes care of the label advertisement hop by hop. And we will always have at every hop through the network, for every tunnel, one incoming and one outgoing label in the LFIP. So there's no need for LDP. Let's have a look at RCP signaling. First, we'll have a look at the path message. You create a certain tunnel on the head-end router, and you point it to a certain destination, the tail-end router. You can have some resource request like the bandwidth or affinity bit, whatever. And we will see later you have path options, either dynamic or explicit. In any case, after router A has calculated the path through the network, it will shoot off the path message towards the next hop router, and so on and so on. But what is inside a path message? Well, we always have this blue area. We have three fields there. The tunnel endpoint IP address, which is the IP address of the tail-end router, the tunnel ID, and an external tunnel ID, which are just fields which will make sure that the tunnel is uniquely identified at each point. So these three fields of information uniquely identify the tunnel anywhere in the network. In the green field, we will see what exactly the tunnel is about. We first have the session attribute. There we can find a session name automatically created by the router. For example, it could be that the name is tunnel A-E, meaning that the tunnel goes from router A to router E. There will be a bit set if protection is required. And then we have the setup and holding priorities. Basically, these setup and holding priorities are numbers between 0 and 7. The lower the number, the more important. These priorities are there so that certain tunnels might be able to kick out tunnels which have already been established. So it's possible that a new request for a tunnel comes in and it kicks out a tunnel which has already been placed on that link, for example. This would happen if the setup priority is lower, so a lower number, but more important than the holding priority number. So for example, if we are trying to signal a tunnel here with a setup priority of 1, the router notices that there is already a tunnel with a holding priority of 5, less important, then it is possible that the router might kick out that tunnel which is already there for the newly signaled tunnel. So that's what the setup and holding priorities do. We have the label request, very important, and then we have the sender T-spec. Basically inside there, the most important information is the bandwidth requirement. So it's possible to configure, as you can see here on the tunnel interface, a bandwidth requirement. Basically here, we are requesting this tunnel to be set up end-to-end with a requirement of 16,000 kilobits per second, so 16 megabits per second. And finally, we have the explicit route. This is the ERO, the explicit route object. Inside, we have the path spelled out by an IPv4 address, each time identifying a router along the path. So from router A, the next hop router is router C, then router D, then router E. This makes sure that intermediate routers like router D and E or C can forward the packet onwards to the correct next downstream router by looking here what the next downstream router is. You might think, well, can they not just do a lookup in the routing table? Well, no, because TE tunnels are often not routed according to the least cost path. So intermediate routers cannot just do a lookup in the routing table and find the least cost path. They really must signal the tunnel according to the path spelled out in the ERO. and the ERO was created by the tunnel head-end router. It's, after all, source routing. What about the reservation messages? These messages go in the opposite direction. So they will go from tail-end router back to the head-end router over the same path, but in reverse direction that the path messages took. Inside such a reservation message, we again have here the blue part, the three fields which uniquely identify the tunnel. And then the information carried is the session attribute, again the name, protection required, setup and holding priority. And then the most important is the label value. Each router, when forwarding the reservation message, will assign one local label, which will become the incoming label, and then we'll put this label inside this field here and forward the reservation message upstream. The upstream router will then read this label value, and there, this MPLS label value will become the outgoing label for that specific tunnel. And in the flow spec, in that field, again we have the bandwidth value. We have seen path and reservation messages, which by far are the most important messages in RSVP. But there are other messages as well, and they are typically used for notification purposes, so for signaling errors. We have a path tear message. This message is typically sent by the head-end router when it wants to kill off an LSP label switch path for a particular tunnel end-to-end. When would that happen? Typically when you shut down a tunnel. So when the tunnel goes admin down, the tunnel head-end signals downstream routers, okay, forget about the tunnel, it's gone. Another reason could be that an LSP re-optimizes. So we move a TLSP from one path to another. Then the old TLSP will be removed, and the tunnel head-end router signals downstream routers to remove information related to that TELSP by sending a path tier. Reservation tier is really the same, but it travels the opposite direction. So it goes from tunnel tail-end router to the tunnel head-end router. A path error message is also important. It's typically sent by an intermediate router when an error occurs and the intermediate router wants to signal the tunnel head-end router that something went wrong and that TELSP should no longer be used. Typically it's when a link goes down or something happens in the routing or something happens with the bandwidth. If there's not enough bandwidth anymore on the link that can be used, then the intermediate router will send a path error message upstream towards the tail-end router. The reservation error message is really the same like a path error message, but it is sent in the opposite direction, so it's sent towards the tail-end router. Let's have a look at RSVP in the live demo. Here we have set up already a tier tunnel from router 1 to router 5. Let's have a look at that. Here we have router 1. We'll have a look at the tunnel, show running config, and we can specify the tunnel 0. And we see that we have a tunnel from router 1 to router 5. This is the destination IP address. It has a certain requirement. One of them is bandwidth is 2400 kilobits per second. And then we are just going to route it over router 2, router 3, router 4, and router 5. So basically the tunnel will take the top path from router 1 to router 5. Is RSVP working? Let's have a look at router 2. What do we have there? Do we have RSVP state? Show IP RSVP installed. Yes, we do have some installed state for RSVP, namely one tunnel which requested 2400 kilobits per second from router 1 to router 5. And it's on gigabit 02, meaning on the interface coming from the tail-end router. So we have one RSVP state here. We can also look at this with another command, show IP RSVP sender, and again we see the same kind of information, 2400 bits per second for this tunnel from router 1 to router 5. So what kind of signaling do we have? Let's have a look at a debug for RSVP so that we can track what path messages come in and out and what reservation messages come in and go out. debug RSVP signaling. Let's stop the debug, undebug all, and let's see what we have here. So on this router is sending a path message further downstream, so towards router 3. And later on we see that it also receives an incoming path from router 1. So router 2 receives paths from router 1 and forwards them towards router 3. And the same occurs for reservation messages. This router is forwarding a reservation message towards router 1, so in the opposite direction, towards the head-end router. And it also receives a reservation message from router 3. So this router is receiving and forwarding path and reservation messages. Can we have a look at those path and reservation messages in more detail? Yes, we can. We have another debug for that. Debug RSVP dump messages. So this will dump the complete content of a reservation or a path message. Let's first enable the debug for a path message. Let's stop the debug and let's see what we have. So on router 2, we received an incoming path message from router 1, obviously. This is the session information we talked about. It's from router 1 towards router 5. The explicit route information is the ERO, so the explicit route object, and we see here all the IP addresses of the links that the tunnel must pass through. So router 2, 3, 4, and 5. A label request is inside. We have the session attribute with the setup priority and holding priority, a flag to say protection is required, and the tunnel name automatically created by router 1. We have the T-spec or the sender T-spec. Basically here we have the request for the bandwidth, but here it's in bytes per second, not bits per second. So the 2400 value must be divided by 8 here. We can do the same, but now we want to dump a reservation message. Debug IP RSVP dump messages, reservation. Let's see what this router receives. There we have one. Let's stop the debug. You shouldn't be able to wait longer than 30 seconds because both the path and the reservation messages will be sent every 30 seconds periodically. So here we have an outgoing reservation message from router 2, so it will go to router 1. Again, we have the session information, uniquely identifying which tunnel this message pertains to. We have the flow spec with the bandwidth information, but again in bytes per second, not bits per second. We have a record route object, which is actually an object which is present to record the actual path that the tunnel takes. So again, we will have here IP addresses. And these are the IP addresses of the routers that this tunnel goes through. And most importantly, what label to use. So here in the outgoing reservation message, the label that router 2 sends to router 1 is 16. That means that the incoming label on router 16 for this TELSP or tunnel is label 16. Router 2 also received an incoming reservation message. And there, that label is 16 as well. So the outgoing label is label 16 as well. So when the router 2 needs to forward a packet along the tunnel or TELSP towards router 3, the outgoing label will be label 16 as well. Can we verify that? Well, of course we can. We just need to look at the LFIP, the label forwarding instance space, and see what we have there as entries. Now, next to the possible entries due to LDP, for example, you can also have entries which are created for TE tunnels. And we have such an entry. So this is really a tunnel ID. So we have 10.100.1.1. This is really a tunnel ID. So this is a TE tunnel entry. It's not just a prefix entry. And indeed we see that the incoming and outgoing label is 16. And the next hop is towards router 3. So this is an LFIP entry created after the signaling of the traffic engineering tunnel by RSVP. Let's have a look at the routing and cost of TE-LSPs. How should the tunnel headend calculate the path? Well, basically, the tunnel headend router needs to calculate a path through the network towards the tail-end router. But it needs to keep into account the requested characteristics of the TE tunnel, bandwidth, affinity bits, and so on. And it needs to find a path that matches the link characteristics. This could be the shortest path through the network, or it could be a path that deviates from the shortest path. So some of the factors that the path is using: the path setup option, the setup and hauling priorities, the attribute flags or affinity bits, and re-optimization. Important is the path option. This is how the operator tells the router how to set up or route a tunnel. There are basically two main options: dynamic or explicit. If it's dynamic, the tunnel headend router independently calculates the path through the network for the tunnel. And it does that by looking in its traffic engineering database or TED. The other option is explicit. That means the operator or administrator explicitly tells the router how to route a tunnel through the network by specifying IP addresses of the links or routers that should be crossed or not crossed. And basically, each tunnel can have one or more of these path options. Each path option will have a number. The lower the number, the sooner the path option will be tried. So they will be tried in order low to high. And as soon as one of those path options gives a good result, so the path calculation is positive, then the signaling for that path option will proceed. And eventually, if that signaling, the RCP signaling, proceeds fine, then the tunnel will come up and the tunnel path will be based on that particular path option. You can have a path option with an explicit path. With the explicit path, you can have a few options. You can include a link IP address, meaning that a TE-LSP or the tunnel should pass that link. It should cross it. Or you can include a loopback IPv4 address of an intermediate router. That means that the tunnel or TE-LSP must pass that router. You can do exclusion, which is the opposite. You can exclude a link IP address. That means that the tunnel should not cross that link. Or you can exclude a loopback IP address of a router. That means that the tunnel should not cross that intermediate router at all through any of the interfaces connected to that router. And finally, you have a loose hop, which is typically only used when you do inter-area or inter-autonomous system traffic engineering. That means that the explicit route object is not completely filled in. Let's take the example of a tunnel that goes from one area to the other. The tunnel headend router in one area cannot calculate the complete path from tunnel headend to tunnel tailend because the tailend is in another area, and the tunnel headend usually only has the database or the topology of the area it is in. What it does in that case is it calculates the path from the tunnel headend router to the area border router, and then the area border router will expand the second part of the explicit route object and calculate a path itself from the area border router itself towards the tail-end router. And that's what the loose hop means. The loose hop means the tunnel headend router only calculates a part of the network, and some other router will then expand the ERO up to the tail-end router. Let's go through a few examples. This is the first example of path option. In this case, the tunnel just has a dynamic path option 1. The only requirement that we see there is that the bandwidth is 16,000, so basically 16,000 kilobits per second or 16 megabits per second. There's no other requirement. So if all of the links over the top path still have that amount of bandwidth free, router 1, the tunnel headend router, will calculate a path which is the shortest path, so typically over the top path. Because here, between router 6 and 7, we have a link with a cost of 100, whereas the cost of every other link is only 1. So in that case, the tunnel or TE-LSP will be routed over the top path. Another example is the explicit path option. And here we can put a number or a name. In this case, it's a name. It could have been a number. In both cases, it will refer to an explicit path that you need to configure on the router. And that explicit path will instruct router 1 to try and signal the path over that specific path. And here in that explicit path, we see that we have listed a number of IP addresses in a certain order. They are indexed. This is router 2. This is router 6. It's the link IP address of this link here on router 6. The 10.1.67.7 is the link IP address here. And the 10.1.57.5 is the link IP address here. So this will instruct router 1 to route the tunnel over the explicit path, which is not the shortest path, but here it is the bottom path. Path option example 3. Again, we have an explicit path option with a particular explicit path name. When we look at this explicit path that has been configured by the administrator, we see it only has one entry. This time it's not an inclusion, it's an exclusion. We exclude the IP address 10.100.1.3, which is the loopback of router 3. What does it mean? It tells router 1 to route this tunnel, tunnel 0, through the network, but avoiding router 3 altogether. Anything else is up to the router. So an alternate path could have been from router 7 to router 4 and then to router 5. But usually, when router 1 does a path calculation, it will try to find a shortest path, which be from router 7 to router 5, and not from router 7 over router 4 to router 5. The only real requirement is here, avoid router 3 altogether. And this is actually what has occurred. So let's have a look at this tunnel for the last example, for example 3. When you do show MPLS traffic engineering tunnels for tunnel 0 on router 1, you can see that this tunnel has a name, it's up, it did verify the path through the database and it's a valid path, and the signaling is actually connected. That means that the RCP signaling has proceeded already from tunnel head end to tunnel tail end router, and it was fine. The tunnel was set up according to path option 1, which is this explicit path option, excluding router 3. And we can see here that the path weight over this path, which is not the shortest path, is 103. So that's the cost according to the path, the actual path the tunnel takes. It has been set up for a bandwidth requirement of 2400 kilobits per second. And we can see that from this router 1, the next hop is out of gigabit Ethernet 0/1, and the MPLS label to be used for this tunnel is label 17. And a little bit down under the RCP signaling info section, we see that the explicit route has been spelled out here. We see that the TE tunnel or LSP has been routed over router 2, 6, 7, 5. And by the way, important for the next slide is that the actual cost, which will be seen by routing protocols, for example, of this tunnel, is a cost of 4. And I will explain that on the next slide. So what about the cost of the TE LSP? The cost of the TE LSP is always the least cost path towards the tunnel tail end router, no matter what the actual path is exactly that the tunnel takes. And that's very important, because we will see in the next lessons, once we start forwarding traffic over this TE tunnel, these prefixes will be put in the routing table into the RIB with the tunnel as a next hop, be it tunnel 0, tunnel 1, whatever. So the outgoing interface in the routing table will be a tunnel interface. Now the cost or the metric associated with those routes in the routing table will be this TE LSP cost, and not the cost of the actual path that the TE tunnel takes. Let's have a look at forwarding of traffic onto TE LSPs. Of course, tunnels are only useful if we get them to forward traffic. So somehow we need to get traffic onto the TE tunnels. while we have several options on how to do that. And here they are. We can just do static routing, we can do policy-based routing or PBR, we can do auto-route announce, AA, we can do forwarding adjacency, FA, we can make sure that we have direct mapping of layer 2 VPN traffic, pseudo-wires or virtual circuits, onto TE tunnels, and we have class-based tunnel selection or CBTS. Let's have a look at those in more detail. The first option is static routing. So basically you just need to configure a static route and point it to a tunnel interface, tunnel 0, 1, 2, 3, and so on. After you have done that, the static route for that particular prefix will just show up in a routing table. And that tunnel interface will actually be used as outgoing interface for that particular prefix in the routing table. And that's it. From then onwards, the traffic for that particular prefix will be forwarded onto that tunnel. So it will be MPLS label switched from head-end to tail-end router over whatever the particular path is that the tunnel takes. Second option was policy-based routing or PBR. In this case, you basically configure policy-based routing and you do that on the incoming interface. In this case, the incoming interface is gigabit Ethernet 0/0. You cannot really configure PBR on the tunnel interface itself. So it's something that you configure on the incoming interface and you need to specify a route map. And inside that route map, you specify which traffic you forward and how to forward it. For example, in our case, you specify which traffic by configuring an access list 100, specifying forward the traffic from this IP address going to that IP address. So you specify both the source and destination IP address. And then this traffic will be forwarded onto tunnel 0, which we have specified here. You could configure a few more things. For example, here I did specify the quality of service to be set or the precedence in the IP header as well. Third option is auto-route announce. And this is really a traffic engineering specific option. It can only be used with traffic engineering. Basically, if you enable auto-route announce on the head-end router, that will modify the OSPF or ISIS SPF, shortest path first, or Dijkstra algorithm. And from then onwards, automatically, the router can put the tunnel interface as an outgoing interface in the routing table for the OSPF or ISIS prefixes. How does it happen? Well, on the tunnel head-end, what it will basically do is, when it's running SPF, it will actually look at the prefixes connected to the tunnel tail-end router or beyond. If such a prefix is connected to a tunnel tail-end router or beyond, that tunnel can actually be used on the head-end router as an outgoing interface for those prefixes. Let's have a look at the example because it's a little bit more complex if you have multiple tunnels. From router 1, the head-end router, we have 3 tunnels. Tunnel 0 goes to router 2, tunnel 1 goes to router 4, and tunnel 2 goes to router 6. So, for all prefixes connected to router 6 or beyond, tunnel 2 will be used on router 1 as an outgoing interface. Let's have a look at tunnel TE1. All prefixes connected to router 4 and router 5 can now have tunnel 1 as an outgoing interface in the routing table of router 1. But not further than that, because prefixes connected to R6 or beyond will actually use tunnel 2 as an outgoing interface, because that's closer to the destination. And finally, prefixes connected to router 2 and router 3, but not further on, they will use tunnel 0 as an outgoing interface. Let's have a look at auto-route announce. Here we have a tunnel configuration on router 1, and we enabled auto-route announce with the command tunnel MPLS traffic engineering auto-route announce. So from now on, the SPF or Dijkstra algorithm will be modified on R1, and this tunnel, tunnel 0, can be used as a next hop. For which prefixes? While any prefix which is connected to R5 or is beyond can now have tunnel 0 as a next hop in the routing table. So when you do show IP route, when you look at the routing table on R1, you can see that for a few prefixes, either a prefix connected to R5 or beyond, tunnel 0 is a next hop. And in fact, for this example, for the prefix 10.1.57.0/24, you can see that there can actually be load balancing for that prefix, whereas one path takes the tunnel and another path takes the physical interface. So here we have load balancing between TE and a native IP path. Forwarding adjacency is another MPLS TE specific option. With forwarding adjacency, you really need two tunnels. You need two tunnels between the same pair of routers and one tunnel in each direction. As soon as you have that and you have enabled FA, then the combination of those two tunnels will appear as one link in OSPF or ISIS. And it will appear as a regular link, so it will be as if it's a link between R2 and R5 directly, with a specific OSPF or ISIS metric assigned to it. On the tunnel interface on both routers, you just enable FA by configuring tunnel MPLS traffic engineering, forwarding adjacency. And you can also specify the IGP cost on the tunnel interface. This will then be the cost assigned to the link as OSPF or ISIS see it between R2 and R5. Just to prove that this forwarding adjacency between R2 and R5 leads to a link which is seen by OSPF in its database. Show IP OSPF database and we'll look at the router LSAs of router 2. We can actually see now that in the router LSA, which specifies the links from router 2, we can see that there is a link towards the neighboring router 10.100.1.5, which is router 5. So in the database of OSPF, we see a link between R2 and R5, and the cost is 3, which is the cost that we configured for this forwarding adjacency. When would you use that? You would use it typically in a use case as I wrote down here. If you were not to use FA or forwarding adjacency, then if R1 forwards traffic, it will typically forward the traffic over the top path, because this is the least cost path. And R1 will never forward traffic over the bottom path, which has a higher cost. So in that case, again, we have maybe an overutilized path at the top and an underutilized path at the bottom. FA gives us a solution on how to fix that. If you were to configure two tunnels, one in each direction, between R2 and R3, and another set of tunnels between R4 and R6, then both of these forwarding adjacencies will appear as one link in the link state database. So now if R1 does a Dijkstra or SPF calculation, it will see a link from R2 to R3 and a link from R4 to R6. If you configure the cost of those two links to be the same, then R1 could actually choose to forward traffic both over the top and over the bottom path, because they will appear as having the same cost. And now you can do load balancing. So you avoid a situation where you have an overutilized path and an underutilized path. The other thing you can do is you can map layer 2 VPN traffic directly to TE tunnels. For this, you need to be using pseudowires or virtual circuits, of course. So when you have pseudowires or virtual circuits end-to-end between the PE router, by default, these pseudowires will be routed according to the routing protocol. So they will follow the least cost path. If you do not want this, you can make sure that the pseudowire or virtual circuits are routed through the network by using tunnels. Let's assume that you have configured a pseudowire or a virtual circuit from PE1 to PE2. You can tie this pseudowire through a pseudowire class to a particular tunnel. And then the traffic, the pseudowire, will not be routed over the least cost path, but it will use the tunnel, TE tunnel 0 in this case, and reach the remote PE router. Even if the tunnel would go down, this is not a disaster, because if the tunnel becomes unavailable, so it goes down for whatever reason, then the pseudowire will do fallback. It will fall back to normal routing, so to the least cost routing. That means that the pseudowire would then take the top path. And finally, we have something which is called class-based tunnel selection, CBTS. As the name implies, class-based, here we really want to do routing based on quality of service, the cost. How do we achieve it? Well, between the same pair of routers, in this case router 1 and router 7, we will create more than one TE tunnel. And then we can specify by means of configuration that each TE tunnel should take some quality of service classes. In this case, tunnel 0 takes the quality of service classes 5, 6, and 7. So experimental bits 5, 6, and 7. Whereas tunnel 1 takes the quality of service classes 0, 1, 2, 3, 4, the remaining ones. So when the traffic comes into R1 now, it will look at the quality of service or the experimental bits and then forward the traffic based on that, either over tunnel 0 or over tunnel 1. Let's have a look at fast reroute or FRR. What is fast reroute about? Well, first of all, it's about protection. We want to reroute traffic in case of a failure. That's the most important thing. Second is, it needs to be fast. Now, what is fast? We say fast is under 50 milliseconds. So we should repair or restore the traffic in under 50 milliseconds. Where does that number come from? It doesn't come from the blue sky. The 50 milliseconds is taken from APS protection or automatic protection switching, which is something that was used in the SDH or SONET world. We kind of taken that number from there, but it's not a hard-coded. It doesn't mean that we can guarantee that each and every time the repair will happen in under 50 milliseconds. But that's definitely the goal. The repair should happen in under 50 milliseconds. And fast means that the repair should be done locally. In the case of an event, such as a link going down or a router going down, the protection or the repair should happen as close to the event as possible. So what we do not want is that in all cases, the rerouting or the repair is done by the headend, because the headend router can be multiple hops away from the event, and that will incur a delay. So to make it fast, the repair should be done where the event happens, by that router. And typically, most of the time, that's a midpoint router. So if a link goes down, which is connected to a midpoint router, that midpoint router must do the repair. Obviously, if it's a link going down which is connected to the headend router, then it will be the headend router doing the repair, of course. Also, the protection that we do is always the infrastructure or facility kind of protection, meaning we will protect a complete link. This means that if there are multiple LSPs or tunnels crossing this link, we protect all of them. We do not protect a single LSP at a time. That would not be very scalable. The protection will actually be done by backup tunnels. So to protect one link, you will need to create and have one backup tunnel. And then that backup tunnel will protect the whole link, meaning all the TE LSPs or all the tunnels that cross that link. And also, of course, the backup tunnel must be pre-computed and pre-signaled. It must be ready to be used. Otherwise, the switch over the repair would be way too slow. So we need to create backup tunnels. Imagine here that we have a tunnel from router 1 to router 5, end to end. This is the primary tunnel. Now a particular part or leg of it, which crosses this link, R2, R3, is what we want to protect. Then you would have to configure a backup tunnel starting at router 2 and ending at the remote end of this link, router 3. This is another tunnel, a backup tunnel, which will take care of protecting all the LSPs crossing the link R2, R3. Because on router 2, we have on the one hand the link we are trying to protect, and on the other hand the backup tunnel, we will call this the point of local repair. And then where the backup tunnel merges again with the primary or the protected tunnel, we call that router the merge point. And in case we are protecting a link, this is also referred to as the next hop router. So in this case, we protect a link by ending the backup tunnel on the next hop router, the router at the other side of the link. But what if we want to protect the failure case when the complete router R3 goes down? Well, obviously we cannot have a backup tunnel that ends at router 3 because router 3 will be down. So in that case, we must have a backup tunnel which ends one hop further downstream towards the tail end router. In this case, this is router 4, and we call that the next hop router. So router 4 now becomes the merge point, where the backup tunnel merges with the primary or protected tunnel. In this case, we are protecting the complete router 3 going down. Now, one note, the switchover from primary LSP to backup tunnel will happen if R2 sees the link to R3 going down. But if R2 sees that link going down, it's not sure what exactly happened. Is it just the link that went down, or is it the complete router 3 with all its connected links that went down? Router 2 is unaware of that. So it's up to the administrator really to configure tunnels for link protection and maybe tunnels for node protection as well. Typically, if both are configured, then router 2 will prefer node protection. But if only tunnels are available to do link protection, then it will just use link protection. So for FRR backup, we need backup tunnels. We need a backup tunnel for each link we are protecting. And in fact, you will need 2 backup tunnels, one for each direction, because TE-LSPs are always unidirectional. Once the protection kicks in, the TE-LSP, the primary one, the protected one, will be rerouted over the backup tunnel, and it will stay there as long as necessary. That could be a long time. So to make sure that at the merge point, the path state doesn't time out, the PLR will make sure that the path messages are forwarded over the backup tunnel. Eventually, the tunnel head end will learn of the link or node failure, because the point of local repair will do the signaling for this. It will send it out through an OSPF or ISIS update, and the tunnel head end router will learn of this, and it will also send out a path error message upstream towards the tunnel head end router, indicating actually that the repair is active, meaning it should not tear down the tunnel immediately. Because the tunnel is protected, it goes over the backup tunnel anyway. Now the tunnel head end, as soon as it learns of this failure somewhere downstream, by both of these messages, it will react as soon as it got the first of these 2 messages, and then will try to re-optimize the TE-LSP. That means 2 things. It will do the calculation to find an alternate path through the network, and then secondly, it will initiate the RSVP signaling head-end to tail-end router. This complete re-optimization process takes about 20 to 40 seconds. The re-optimization occurs, traffic is switched over to the new alternate TE-LSP, and the old TE-LSP, which was protected, is just tore down. We have 2 kinds of local fast reroute protection, link and node protection. What the head-end router does is what you configure as an administrator. You can specify just to do link protection or link and node protection. If you have configured both, the router will prefer node protection. It's the safest thing to do anyway, because it's not sure that when it sees a link going down, it's just a link that went down or the complete router. But if node protection is not available, then it will do fast reroute link protection. And just make sure that the backup tunnels in your network, and you will have many of them because you have many links to protect, that they do not attract regular traffic. So do not configure auto-route announce or forwarding adjacency or static routes pointing to these backup tunnels, anything like that. There should be 0 traffic onto the backup tunnels unless the protection is active. Let's have a closer look at fast reroute link protection. Again, we have our network here. We have a TE tunnel from router 1 to router 5, and we are trying to protect one particular link here. From the point of local repair, we must have a backup tunnel which was configured before and pre-signaled. It ends at the merge point or the next hop router, which is just the router at the remote end of the link we are trying to protect. This TE tunnel or the TE-LSP crosses this link, so it will be protected by this backup tunnel as well. Let's have a look at the signaling. To be more precise, let's have a look at the reservation messages and the label advertisement. So we have the label advertisement hop by hop from the tunnel tail-end router to the tunnel head-end router. We have the same for the backup tunnel. There is also, of course, path and reservation messages on the backup tunnel to signal it, and we also have a label advertisement hop by hop for the backup tunnel. The packet forwarding will be in the opposite direction. So when the link is still up, the primary tunnel or the protected tunnel is used just as it is. So we have hop by hop label switching of the packet and penultimate hop popping at the end. Now when the link down event occurs, the point of local repair, router 2, will now switch over the traffic onto the backup tunnel. So when the packet arrives at router 2 with label 63, it will actually still swap this label 63 with label 19, but then put an additional label on top of it. And this additional label is the label that was advertised over the backup tunnel. The packet is forwarded over the backup tunnel. We have penultimate hop popping. The packet arrives at router 3 with label 19. And this is the remarkable thing. The packet still arrives with label 19 at the top, which is the same as when the link was still up and the packet was forwarded over the protected tunnel. The packet here also arrived with label 19. The only difference is now that router 3 receives the packet with label 19 over another interface, but that's not a problem. And then the packet emerges from the backup tunnel and is then forwarded onwards with label 23 towards the destination. Let's have a look at fast reroute link protection in the live demonstration. We have the lab network here again that we have been using throughout the traffic engineering lesson. We will have a tunnel from router 1 to router 5 explicitly routed over the top path, and we will be protecting the link gigabit Ethernet 0/2 out of router 2. We will protect it with a backup link explicitly routed over R6 and terminating at R3. Let's have a look at the protected tunnel, which goes from R1 to R5. So we have the tunnel here, it's up, the path is valid, and it has been signaled by RCP all the way up to the end. It's an explicit path R1 to R5. The outgoing label is 19 towards router 2. Now if we do the same command with protection at the end, then we can see that this tunnel actually requested fast reroute protection. So if down the path there are links which have backup tunnels, then the LSP will be protected over those links. Traffic going from R1 to R5 might go over this tunnel. Then it will use the labels on top of these packets that are used by the traffic engineering tunnel. Let's have a look at an example. The traffic towards router 5, its loopback, which is 10.100.1.5, will actually use these labels. How can we check the labels used for these packets at every hop? Well, we're just going to do a trace route. So trace route 10.100.1.5. So the packets go out indeed with label 19. So we are using the tunnel and we just do label swapping at every hop. Just to be sure, we can do show IP route 10.100.1.5. And indeed, we see that this prefix is pointing to tunnel 0. That's the outgoing interface, so traffic engineering tunnel 0, the one we are trying to protect. At R2, we are going to protect the interface gigabit Ethernet 0/2 towards router 3. So what do we have configured on that interface? As you can see, we have a backup tunnel configured. So this interface will be protected by backup tunnel 100. How does that tunnel look like? Show run config interface tunnel 100. We see it's kind of a regular tunnel, It's explicitly routed over R6. The one thing which is very important is that it does not forward regular traffic. So we don't have auto-route announce or forwarding a JCC or anything like that configured on the tunnel interface. So it does not attract and forward IP traffic. The only purpose of this backup tunnel is to protect TELSPs or tunnels crossing the link R3. Let's have a look at that tunnel. Show MPLS traffic engineering, tunnel 100. So we see that the backup tunnel is up, it's connected, everything is fine, and the outgoing label would be label 21 over the gigabit Ethernet interface 0/3 towards router 6. We can also use the command show MPLS traffic engineering fast reroute database, and that would tell us what is protected by whom. In this case, we have a tunnel from router 1. For this tunnel, the packets come in on router 2 with label 19 and go out with label 17 on gigabit Ethernet 0/2. And this interface is now protected with tunnel 100. If the interface goes down, now the status is ready. So at the moment, the protected interface is still up. So the protection is ready, but not active yet. So let's see if the protection will work. Let's do a shut of the protected interface, gigabit Ethernet 0/2 on router 2. We immediately see that the interface goes down, the OSPF adjacency goes down, okay. So now the protection should have kicked in. Let's have a look at the fast reroute database again. And indeed, we now see that the protection is active. So the traffic is being forwarded over tunnel 100, still with label 17. But an extra label is pushed, the label from the tunnel 100 itself that we saw before. If you do the detail command, you will just see a little bit more information here. Again, we are protecting the tunnel from router 1, going out of gigabit Ethernet 0/2, which is down now. And the fast reroute label is used, the one from tunnel 100. We can also do show MPLS traffic engineering, tunnels protection. And now we see that the tunnel from R1 to R5 is protected by tunnel 100. It says in use, so the protection is active. Let's have a look at router 1 again. So we look at tunnel 0 again. Is it still up? Is it still fine? Yes, it's still connected. So the protection worked and it is still using that protection forever. Why? While tunnel 0 here only had one path option, and that was an explicit path option. So it cannot reroute to another path option. And you see that here. It says reroute pending. There is no other path option, so it cannot reroute over another dynamic path, for example, or over another explicit path. This is not possible. Here the traffic will be forwarded over the tunnel, and it will always keep on being forwarded at R2 over the backup tunnel. How can we verify that? Well, let's do our trace route again for the IP address 10.100.1.5. And now indeed, we see that we push the extra label, the one from tunnel 100, at router 2 when forwarding the packets to router 6. So the traffic which is on the protected tunnel from router 1 is now forwarded over tunnel 100 at router 2, the backup tunnel. Let's have a look at fast reroute node protection. Again, we have this network. We have a TE tunnel end-to-end from router 1 to router 5. And now the part of the network we are trying to protect is anything that goes over router 3. So this is the part from router 2 to router 4 that we are trying to protect. The primary tunnel crosses R3. The backup tunnel should not. This is the regular signaling by the reservation messages from the tail-end router to the head-end router. At each hop, there will be a label advertised. One thing extra here is that as soon as R4 knows it's the next hop router, it knows that because there will be a backup tunnel that ends at R4, he will attach extra information to the reservation message. He will attach a label sub-object and the RRO or record route object with label 23, which is this label 23. And this label sub-object does not change at the next hop. Why is that? Well, this is to signal the point of local repair, router 2, that when router 2 switches over the traffic from the primary path onto the backup path, this label must be used on top of the packet. Because this label is the label that R4 expects, even when the traffic is forwarded over the backup tunnel. Alright, so we need a backup tunnel. The operator configures a backup tunnel from R2 to R4 as an explicit path, making sure it avoids router 3. We have regular signaling on this backup tunnel. So for example, this could be the labels advertised by the reservation message from R4 to R2. Packet forwarding. If the protected tunnel is still up and running, this will be the packet forwarding end to end. But what happens if router 3 goes down? Router 2 will notice that because the link R2, R3 goes down. He will then take any packet still arriving at router 2 with a top label of 63 and swap that out with this label that he learned about in the label sub-object, label 23. And then he will push on top of that the label which is used by the backup tunnel, in this case label 41. Then this packet is forwarded with regular label switching over the backup path. At the end we have penultimate hop popping, so we pop off the top label and the packet arrives at the next hop router or merge point with label 23. And this is the same label that we would see on top of the packet if the packet was coming in over the protected path when router 3 was still up and running. The only difference is that the packet now comes in on a different interface, but that is fine. R4 just does a lookup for label 23, swaps it with label 16 and forward the packet onwards. Let's have a look at fast reroute node protection in the live demo. Here we are again with the same network. Again we will have a tunnel from R1 to R5, which we are trying to protect with a backup tunnel. But now we are doing node protection. We are going to do node protection against router 3. We will do that by having a backup tunnel from router 2 over R6, R7 to R4. R4 is the merge point or the next hop route. Let's have a look what we have at router 1. Let's first have a look at this tunnel we are trying to protect. This is the tunnel from R1 to R5. It has a specific bandwidth requirement. Explicit path is the top path. R1, R2, R3, R4, R5. And this time we requested fast reroute, but we requested node protection. That means if node protection is available, that will be preferred. If not, we can fall back to link protection. Let's first have a look actually at how the packets are forwarded when the protection is not active yet. We'll do a trace route towards router 5. The loopback of router 5 is 10.100.1.5, and this traffic is forwarded over this tunnel. These are the labels used at each hop. Let's just make sure that this traffic is forwarded over tunnel 0. Yes, it is. Tunnel 0 is the next hop. Let's have a look at router 2 there, what we have configured. Let's first have a look at the interface that we are trying to protect, which is interface gigabit Ethernet 0/2. We see that actually we have two backup tunnels. We still have the backup tunnel 100 for the link protection, but this tunnel goes to router 3. We also have now a tunnel 101, and this is the one used for node protection. This is the tunnel going to router 4, the next hop. Let's have a look at that tunnel. Indeed, we see that for this tunnel 101, the tunnel destination is router 4, and we have an explicit path R2, R6, R7, R4. We are avoiding router 3 completely. So on gigabit Ethernet 0/2, we have a tunnel 101. It goes to the next hop, so it should provide node protection. Again, this tunnel is a backup tunnel, so it should not attract traffic, so you should not have forwarding adjacency or auto route announce on it or anything like that. Let's have a look at the traffic engineering fast reroute database and see what we have there. So here we see that we have a tunnel from router 1. We see the IP address 10.100.1.1. We will be protecting that tunnel. Those packets should be coming in with label 20 at the top and go out on gigabit Ethernet interface 0/2 with label 17. And now we are protecting it with tunnel 101, so we should provide node protection. And the label that should be pushed on top of the packets when this tunnel is in use is label 18. Right now, the tunnel is not used for node protection because the status is ready. All right, so let's see what happens if the protection kicks in. We are just going to shut gigabit Ethernet 0/2, which kills off the link between router 2 and 3. Router 2 now sees the link going down. He doesn't know if the link went down or the whole router 3 went down, so he will assume the worst case and assume that router 3 has gone down. Let's have a look what happened now. Show MPLS traffic engineering fast reroute database again. And now indeed we see that for tunnel 101, protecting the tunnel from router 1 to router 5, the status is active. So the protection is now active. At router 2, the packets coming in with label 20 are now forwarded over the backup tunnel 101. Let's have a look now at router 1. What is the difference in packet forwarding? Again, we will do a trace route towards 10.100.1.5. And now indeed we see that we push extra labels, notably label 18. And then we push the label which is used by tunnel 101. The packet arrives at router 4, the next hop router or the merge point with the label 18, which is what router 4 saw before as well. So when the protection was not active yet, so when router 3 was still up and running, the packets also arrived at router 4 over the protected tunnel with label 18. And again, we see that the traffic will remain like this. It goes over the tunnel, and at R2 it goes over the backup tunnel, and it will stay like that forever. And the main reason for that, of course, is that the tunnel 0 only had one explicit path option. There was no other explicit path option it could re-optimize to. There was only one path option, and that was the explicit one following the top path. Let's have a look at fast reroute path protection. With path protection, we will be protecting the complete TE LSP of a tunnel. How do we do that? Well, we need to have a backup LSP. This means that every TE LSP of a tunnel will be protected by a backup LSP. To make sure we can do the switchover from primary to backup LSP, we have to make sure that this backup LSP is pre-signaled. So this backup LSP will be signaled by RSVP end-to-end prior to the event of the failure. This can have an effect on the scalability, because instead of having one TE LSP per tunnel, we will have two now. We will have the primary LSP and one backup LSP. So we doubled the amount of LSPs in the network. Another thing to notice is something regarding the detection of the failure. It is the headend that does the switchover from primary to backup LSP. So the headend router needs to know about the failure. But the failure can happen multiple hops downstream. It's not necessarily the link connected to the headend router that goes down. It could be a link anywhere along the path at any midpoint router that could go down. The headend router needs to learn about this. It can learn about it in two ways, either by an IGP update, OSPF or ISIS, or by the path error. But this will take a little bit of time because the propagation has to be from the midpoint router where the failure occurs all the way back up to the head-end router. And that's why in this case, with path protection, we do not guarantee 50 milliseconds as a failover time. It could be slightly more. It could be 100 or 200 milliseconds, but it's not guaranteed to be 50 milliseconds. This is how you would configure path protection. You would have a tunnel from router 1 to router 5, and in this case we have a path option which is explicit. The number is 1. We have this path option 1 protected by a backup LSP. Both these path options have their own explicit path. It is up to the operator or the person configuring the router to make sure, of course, that the primary LSP and the backup LSP share as little as possible the same prefixes or the same routers. We can look at the tunnel that we have configured for protection, show MPLS traffic engineering tunnels, and we look at tunnel 100 with protection keyword, and we see that we have one LSP here in blue, which is the primary LSP, and it's backed up by the red LSP here. And by the way, the router will tell you how many links or nodes, routers, there are in common between the protected, or the primary LSP, and the protecting LSP. Let's have a look at MPLS traffic engineering when we are also using MPLS VPN. So when using MPLS traffic engineering, we can have any MPLS service. On top of the traffic engineering, we can transport MPLS Layer 3 VPN traffic, MPLS Layer 2 VPN traffic, 6PE, 6VP, and so on. But there's one thing to be careful about. We have to watch out how the MPLS TE tunnels are placed in the network. If an MPLS TE tunnel ends at a P router, so short of the PE router, then we will have to use LDP as well. Let's explain that on the following slides. If we have TE tunnels running between the PE routers, then we can have MPLS VPN Layer 3 or even MPLS VPN Layer 2 traffic on top of that. Of course, we will need TE tunnels in both directions, because the TE tunnel is unidirectional. In this case, when the TE tunnels start at and end at a PE router, there is no need for LDP at all. And the TE tunnels can even take different paths. It does not matter, as long as you always have a pair of TE tunnels, one in each direction, between a pair of PE routers. But what happens if a TE tunnel ends at a P router instead of the egress PE router? Well, we have a problem. First of all, if the TE tunnel ends at a P router, in this case the TE tunnel ends at P3, we still need to forward the packets onwards as labeled packets towards the remote egress PE router. To make sure we still have a labeled path from the P router where the tunnel ends towards the egress PE router, we might still have to have LDP running there. Instead of LDP, we could have also another TE tunnel. But if there's no TE tunnel, then we must have LDP here advertising labels for the remainder of the path towards the egress PE router. That's one thing. The second thing is a little bit more subtle, because even when we have LDP for the remainder of the path, it will not work. The LSP will be interrupted at P3. Why? Well, look at this TE tunnel. When the PE router PE1, which is the ingress router in the MPLS network, starts to forward traffic, it will put label 33, the label of this TE tunnel, on top of the packet. Then at P1, the label gets label swapped with label 21. At P2, we have penultimate hop popping. So the label is popped off, and hence at P3, the packet will arrive with no TE label. Because it's VPN traffic, the packet will arrive with the VPN label. But P3 is not a PE router. It's completely unaware of all the VPNs. So it doesn't know about the VPN label. Then it would just drop the packet. So to avoid this, we have a trick to make this work. And the trick is a targeted LDP session. When you configure targeted LDP from the tunnel tail-end router to the tunnel head-end router, we can make this work because LDP in any case will assign a local label for the loopback of the remote PE router, the egress PE router. This local label here is 83. LDP will send this label through the targeted LDP session towards the ingress PE router. And now the ingress PE router can use this label. And this label 83 will be used like a stitching or a binding label between the part of the LSP which is traffic engineering and the part of the LSP which is LDP. Let's see how it works with the packet forwarding. So when PE1 sends a packet over the TE tunnel, it will have, of course, the VPN label. On top of that, it will put this label 83, which it has learned over a targeted LDP session. And on top of that, it will put the label which is tied to the TE tunnel, label 33. We do the normal label forwarding over the TE tunnel, so label swapping. At the last but one router of the TE tunnel, we do penultimate hop popping. So we pop off this label 21, and now the packet will arrive with this LDP label that was received over the targeted LDP session at router P3. P3 knows about label 83 because it is the label that P3 assigned through LDP to this particular prefix, the loopback of the egress router P2. So now P3 can just do a lookup of the label in the LFIP, find the label, swap it out with label 17, which is an LDP label, and forward the packet onwards towards the remote PE router. There, of course, we still have penultimate hop popping as usual. So the LDP label is popped off, the packet arrives at the egress PE router with a VPN label, the packet will be forwarded out of the VPN. So, recap, if you have a TE tunnel that ends at a P router, you must have two things. You must have one LDP for the remainder of the path towards the egress PE router, and you must have a targeted LDP session from the tunnel tail-end router towards the tunnel head-end router, the ingress PE router. Hello and welcome to Lesson 9. This lesson explores segment routing, the latest big development in the MPLS world. I will provide an overview of what segment routing is and what the benefits are. Let us have a look at a new way of distributing MPLS labels in the network and a new way of doing source routing or traffic engineering in MPLS networks. Here's an overview of segment routing. So what is segment routing or SR about? It's basically about source routing. The head-end router dictates the path of the packet through the network. We'll have information advertised by IGP. And in case we are using MPLS, the extra information advertised by the IGPs or the routing protocols is the label. We will have the IGP advertise MPLS labels. Now we will have to use OSPF or ISIS, a link state protocol. Now OSPF or ISIS will distribute labels, but there is also a possibility to have IPv6 in the data plane. And very importantly, when we are using IPv6 or MPLS in the data plane to forward the packets when we are deploying segment routing, there is no change in the data plane. So there is no reason to change the hardware for the forwarding on the routers. So what are the benefits? Well, we can just do simple least cost routing even without LDP, so we do not need a label distribution protocol. We can reuse the existing data plane, MPLS or IPv6, so nothing changes with regards to the forwarding. We can still do traffic engineering, source routing, but without the signaling, so there is no need for RSVP for traffic engineering. And finally, we have a direct tie-in with software-defined networking, SDN, and with controllers. So what are the basics of SR? We'll have a segment. What is a segment? A segment is an identifier for any type of instruction. Since we are talking about MPLS forwarding, a segment in our case will be an MPLS label. And basically a segment will be a part of the path that the packet takes. So a path is really an order list of segments. An order list of segments, hence we have a list of labels or a stack of labels. So if the head-end router wants to send off a packet and he wants to send it according to a certain path in a network, he will just need to put a certain stack of labels on top of the packet and forward the packet. As soon as the packet has that particular label stack, the path through the network is fully defined. And finally, we do have protection, fast reroute protection, but protection here is provided by LFA, loop-free alternate. In fact, it's a special variant of loop-free alternate or LFA. It's TI-LFA or topology independent LFA. So we can have source routing with MPLS. How does it work with segment routing? Well, when the router A needs to forward a packet through the network, then he will just need to put a specific label stack on top of the packet, and the packet will then follow a path through the network based on the labels in the label stack. And this path through the network can actually deviate from the least cost path. Let's have a look. Router A receives a packet, an IP packet, and he wants to send it over the blue path. To do that, he will divide the path maybe in 4 segments or parts. For each segment, he will assign a label. And then in the right order, he will put the 4 labels on top of the IP packet. And router A will then forward the packet onwards. So he sends it off first with the top label of 16004, which is the label that identifies the first segment. This is the segment that gets the packet towards router C. Then, when looking at the second label after removing off the top label, that label identifies the second segment, which gets the packet to router F. Again, that label is removed. Router F looks at the label 16023, that identifies the third segment, and the packet is forwarded to router D. And finally, we have one label left, 16009, and that gets the packet over the last segment, segment 4, towards the destination router, router H. That's what segment routing is about. Let's have a look at IGP and label distribution. So we will have IGP, the routing protocol, OSPF or ISAS distribute MPLS labels. Now to do forwarding of labeled packets in a network, we need always incoming and outgoing labels, which need to be present in the LFIP, the label forwarding instance space, on every router. Otherwise, of course, we cannot use MPLS. But now we do not have LDP. So basically, we will enhance the IGP to carry the MPLS labels. We need a consistent view between all the routers in the same area or level. So that means that we can only use link state protocols. We cannot use distance vector routing protocols. There are really 2 kinds of labels that we will use: globally unique labels and local labels. The globally unique labels, that's typically one label assigned to one router, and that's globally unique. So that router is the only one assigning that particular MPLS label to itself. No other router owns that MPLS label. That label will be used to attract traffic to it. So if any other router in the network wants to send traffic to that router, it might use that particular global unique label that that router has. That unique label, which is global, we call that a prefix SID label. A SID is really a segment identifier. The prefix SID is one prefix assigned to one router, and the global unique label is assigned to that prefix. Typically, that will be the loopback prefix of the router. Those labels need to be globally unique. So we will take them from a new label range, which is specifically reserved for segment routing. And we call that the Segment Routing Global Block, or sRGB. This is basically a range of labels carved out of the complete label range. So starting at 16,000 from the so. So starting at 16 and ending at 1 million and something. Typically, by default, we start the range at 16,000 and the total range of labels is 8,000. So we will have a range of 8,000 globally unique labels. Reminder, one router only needs one of such labels. The second kind of labels are adjacency labels or adjacency SIDs. Those are labels tied to one particular link or interface of a router. Those labels are only unique in between the interfaces inside one router. In between different routers, they are not unique anymore. And by the way, these labels are not taken from the sRGB, the global block reserved for segment routing. They are taken outside of that block, so from the regular dynamic label range. These labels are also advertised by the IGP. So again, every router in the area or level will know which label is assigned to which link on a particular router. Again, when a label needs to shoot off a packet into the MPLS network, it will then know which label can be used to steer traffic over a specific link further downstream, because it will know which MPLS label is tied to that link on that router further downstream. This label has only significance to the router that assigned it to a particular link. That router might receive traffic with that particular label at the top. And then, when the router receives that packet, it will identify that label by looking it up as an incoming label in the LFIP, stripping off the label, and then forwarding that packet over that specific interface. Let's have a look at this IGP advertisement, prefix SIDs, adjacency SIDs, label stack, and the MPLS forwarding in the live demo. We have a network here. It's 7 routers. It's running ISIS, and I enabled segment routing on every router. On router 1, we're just going to look how the configuration looks like. Important for segment routing is that you as the administrator configure a globally unique label, the prefix SID label, to be used on every router. This is how it is configured. Here we have a connected prefix SID map. So this is basically one or more connected prefix SID on this router. Now 1 is enough, so we just have a range of 1. This is the prefix 10.100.1/32. This is also the loopback of this router. And the index is 1. Now, the prefix SID label is a label value. Our range by default starts at 16,000 and we have a range of 8,000 labels. You can either configure that label as an absolute value, for example 16,001 because this is router 1, or as an index. Index 1 would mean 16,000 plus 1. At router 2, you would either configure the absolute value 16,002 or an index of 2. So this is how you configure the prefix SID or the globally unique MPLS label used by segment routing. The second part of the configuration is under the routing protocol, OSPF or ISIS. In our case, we have ISIS. We have enabled segment routing. We have enabled the advertisement of the prefix SID. In the end, this will be labeled 16,001 for this router, router 1. And that's basically all that we need. With this configuration, segment routing is enabled. The prefix SID has been assigned by the operator. And the adjacency SIDs or labels have been automatically assigned by the router. So each interface where ISIS is enabled on this router will also have an adjacency SID label assigned to it. Let's have a look at the ISIS database, what we have there. Show ISIS database. This is just the overview. We see that we have 7 LSPs for the 7 routers we have here in the network where ISIS is enabled. And all of them have segment routing enabled. Let's have a look at one of these LSPs in more detail. Show ISIS database for R1, and we'll immediately look with the verbose keyword to see all the details. So what do we see here? We see that there is a capability advertised. So this is advertised through new TLVs which have been created for segment routing. And through these new TLVs, we can say to the other routers in the network, this router is capable of doing segment routing. The segment routing global block starts at 16,000 and the range is 8,000. Every router will advertise this. Further down, we will find the prefix SIT. Here we see the prefix SIT assigned to this router, index is 1. So the MPLS label in the end will be 16,000 plus 1, 60,001. And we know that because this is the loopback IP address of this router. So that's the prefix SIT label, globally unique at each router. Besides that, we also have the adjacency SIT labels. So if we have a look at the IS extended entries, which basically describes links from this router to a neighboring router, in this case router 2, we see now an adjacency SIT value, and this is the label 16. So this label is taken from the dynamic range that we have. For another interface, this is the interface from router 1 towards router 7, we have of course a different label, label 18. So all the adjacency SIT labels are unique inside one router and are all taken from the dynamic label range. On another router, you might find back the same labels used as well. Let's have a look at the MPLS forwarding. So we will have a look at the LFIP. Show MPLS forwarding table, and we see we have an LFIP, which is the same as we've always had. Incoming labels, outgoing labels, an entry for a prefix, an outgoing interface, and a next hop. There have been made no changes to the data plane for segment routing. So there are no changes to the LFIP for segment routing. The only thing we need to have is an incoming label and an outgoing label and an outgoing interface. But now you can see that the labels that we can have here could be the prefix SIT label, for example 16,002. So any router in the network can have this label as a local label. When this router would receive a packet with label 16,002 on top of it, it would mean forward the packet towards router 2. The same happens for adjacency labels. As we can see here, we have 3 adjacency SIT labels. They are marked with an A at the end of the prefix. These labels mean if this router receives a packet with a label 16 on top of it, then forward the packet over this interface. So adjacency SIT labels mean forward the packet over a specific adjacency or link. And of course, we always pop off the label. How can we verify this is actually working? Well, you could do a trace route, for example. Let's do the test where from router 1, we try to send a packet to router 5. Now, all of the routers are enabled for segment routing. So if we use MPLS forwarding end-to-end, then that packet should be forwarded with a label of 16,005 to get to router 5, because that's the prefix SIT label assigned to router 5. Let's see if that's the case. So we will send a trace route to the prefix 10.100.1.5, which is the loopback of router 5. With a trace route to 10.100.1.5, we see that at every hop, the label used is 16,005. That's because this label is the prefix SIT label of router 5. All traffic that needs to go to router 5 will get there just by the label 16,005 at the top of the label stack. And every router in the network knows that when it receives a packet with this label at the top, it needs to be forwarded towards router 5. It has learned these labels through the ISIS advertisements. Let's have a look at traffic engineering with segment routing. So with segment routing, we can also have traffic engineering. Basically, source routing is baked in with segment routing. So it's going to be easy to do traffic engineering with segment routing. But we don't need a signaling protocol. We don't need RSVP-TE because the labels are advertised by the IGP themselves. So either by OSPF or ISIS. The source routing is done by the head-end router pushing a complete label stack. And each label in that label stack identifies a segment of the complete path. That's how we will do the traffic steering or the source routing through the network. Both the prefix SIDs and the adjacency SID, so the prefix SID labels, global unique labels, and the adjacency SID labels, the labels associated with a particular link on a router, can be used for SRTE. And the protection will be done by a special kind of LFA, loop-free alternate, which is topology independent loop-free alternate. With that, we make sure that the protection path or the backup path is actually already on the post-convergence path. That means that when a link event occurs, the link goes down, then the traffic is switched over onto the backup path, and that backup path is actually the same path as the path after the network has settled, so has completely converged. What about the SRTE implementation? Well, the implementation actually looks and feels a bit like how traffic engineering was implemented with RSVP. Of course, without RSVP, the signaling protocol included. The CLI is a bit similar. We have tunnels that we can configure on the tunnel head-end router. We have path options that we can configure, multiple ones per tunnel. They can be dynamic or explicit. There's one new thing though, is that instead of just configuring a next address IP address, we can actually put a next address, the label. So we can put a label there instead of an IP address, and that's because the head-end router will know about which label to use for which segment. And finally, the protection, as I just mentioned, will be done by TI-LFA. The functionality is similar for SRTE when you compare it with TE based on RSVP-TE, but of course without that signaling protocol. So basically the head-end router will have to do path calculation of the path through the network. It will need to find a suitable path through the network. That can be done in distributed mode, which is very similar as the classical TE as we've had with RSVP-TE, whereby the head-end router will just look in its traffic engineering database and find a path that suits all the requirements that you configured on the traffic engineering tunnel. Actually, the path can also be provided by a controller, and we call that central mode. In that case, the head-end router will delegate the task of finding a path for a particular tunnel to the controller. And the controller will do the calculation and then provide the path for the specific tunnel back to the head-end router. And the other things are really the same as with the classical traffic engineering. We have the affinity bits or the resource bits, we have the metric control, and so on. Let's have a look at traffic engineering based on segment routing in the live demo. We're back here with our network, 7 routers, segment routing is enabled everywhere, the routing protocol is ISIS. So what do we have? Let's have a look at route 1. Of course, first you have to make sure that traffic engineering is enabled for segment routing. We can see that under router ISIS, we have segment routing enabled, of course, and now we have traffic engineering enabled. The router ID is loopback 0, and we enabled traffic engineering for level 1. This also means that traffic engineering is now enabled for segment routing. Again, this is segment routing. We do not need RSVP-TE. There's no signaling protocol. So this is what we did not configure. Let's have a look what we have in the database. Show ISIS database. This is just a summary, of course, the overview. We have the 7 routers in our network. Let's have a look at the traffic engineering information. So we'll have a look at the LSP of router 1 with the verbose keyword, so we see all the details. So segment routing is enabled, the sRGB is there, we have the adjacency SIDs of every link, and you can see that we also have some traffic engineering information here. So this traffic engineering information gets flooded by ISIS. And you can see similar information with show MPLS traffic engineering topology. You see the router IDs here of every router and the links that are being advertised. You can see TE metrics, shared risk link group information, which is something used by traffic engineering, and so on and so on. So there is the information used by traffic engineering. But of course, the most important are the labels, the prefix SID labels and the adjacency SID labels, which will be used to guide or steer the traffic through the network. Let's have a look at a tunnel configuration at the tunnel head and router. We have a tunnel configured at router 1. Let's have a look at that. This is our tunnel used for SRTE. It looks very similar to a tunnel that we are used to with the classical traffic engineering using RCPTE. We have a tunnel destination, which is router 5. We have auto route announced, so we can point traffic to this tunnel interface. It has a path option with an explicit path. The path is actually not the shortest path from router 1 to router 5, but the path goes over router 7. And we must make sure that this tunnel is not a regular classical TE tunnel, but is set up by segment routing. So we need to specify the segment routing keyword at the end. Let's have a look at this explicit path. You can see here that the explicit path has been defined, each time with a specific hop in the network, first router 7, then router 2, router 3, router 4, router 5. But here is something that we could not do before with classical traffic engineering. You can actually specify the next hop in the path as a label. And actually you can combine, some next hops are specified as a link IP address. This is router 7. Some next hops can be specified as a specific label, be it a prefix SID label, as you can see here, 16003 is the prefix SID label of router 3, or it can be even an adjacency SID label, meaning the label tied to a particular interface on a specific router. Let's have a look now at this tunnel. Show MPLS traffic engineering tunnels for tunnel 0, and let's see what we have. The tunnel is up, the path has been checked and it is valid. The router does this by verifying the path you put in the path option versus the TE database. And then we can see it's actually a segment routing tunnel, and this will be the path used. And for the rest, you have some regular traffic engineering characteristics mentioned here. Very important is the path info used by segment routing. You can see that the path is actually an order list of segments. This can be IP addresses, link IP addresses, maybe even loopback IP addresses, but it can also be labels, and the labels can be adjacency or prefix SID labels. Now let's have a look at the forwarding. Is the tunnel actually forwarding traffic? First we must have a prefix which has this tunnel as a next hop in the routing table. We have one. For the prefix 10.100.1.5/32, we have the tunnel 0 as a next hop in the routing table. So basically from this router, the traffic being forwarded to router 5, its loopback is 10.100.1.5, will use the tunnel 0. Hence, we'll use segment routing or SRTE to forward the packets from router 1 to router 5. And the actual path will be from router 1 over R7 to R2, R3, R4, R5. Is this the actual path taken? Well, let's test it. We can do a trace route towards 10.100.1.5. And we're just going to specify TTL of 1. So we're just going to send the first probe with the TTL 1. And let's see what the label stack is returned by the next hop router, which is router 7. So when we shoot off this packet, we can see that the complete label stack consists of these labels. Label 17 is at the top of the label stack. This is the label that R7 will look up because it's the top label. And then we have 3 more labels, which are actually the prefix SID labels. Router 3, 4, and 5. So router 7 receives the packet with label 17. What does that mean? Let's have a look at router 7. In router 7, we can look at the LFIP. And we can see that label 17 is an adjacency SID label pointing out the interface gigabit 2. So when router 7 receives a packet with label 17 at the top, it will pop off the label and forward the packet towards router 2. So this is an adjacency SID label, and it's basically used so that R7 can forward the packet over this interface towards router 2. And then the remainder of the label stack will be label 60,003, which gets the packet to router 3, 60,004, which gets the packet to router 4, and finally 16,005, which gets the packet to router 5. That's how SRTE works. Let's have a look how controllers can be used in segment routing networks. In the case where we have multiple areas or multiple autonomous system numbers, the router in one particular area or autonomous system cannot easily know the complete topology. It usually only knows the topology inside one area or inside one autonomous system number. But if the router wants to build an SRTE path, for example, from itself towards the destination in a remote area or autonomous system number, it will not be able to do so. And that's where a controller can come in to help. The controller can know the topology of each area or autonomous system. So it has the complete view. How does it do it? Well, the controller will be either connected to each area or it can be connected to each autonomous system number. So it will do that by participating in the routing. So it will run an OSPF routing adjacency or ISIS routing adjacency with several routers in the network. There is another way, that is BGP-LS or link state. That means that BGP will carry all the link state information from OSPF or ISIS from one or more routers and transport all of that information up to the controller. In any way, the controller will have a complete view of the network. And this controller is often referred to as the PCE, the Path Computation Element. And this term really comes from the PCEP, the Path Computation Element Protocol. Basically, this is a protocol used by the controller to talk to a router. And the router is often referred to as the PCC or the Path Computation Client. Normally, the TE database or TED consists of the IGP topology and the TE link attributes. But because we are using segment routing here as well, we also need to have the SIDs, the prefix SIDs and the adjacency SIDs inside that TED. And also the sRGB, so the SR global block. All of that together will form the database used by traffic engineering. And once the controller or the PCE has all of that information, it can take upon itself the task of doing the calculation of finding path. In this case, the PCC or the router, if it's a head-end router and wants to calculate the path of a tunnel, it can delegate the task of calculating the path for each and every tunnel to the controller. So it will basically send a PCE request to the controller and say, for this or that tunnel, please give me a valid path. A path meaning something which is operationally good and the path adheres to all the TE constraints that there might be. The controller then does the calculation and then sends the result of the path back to the router that requested the path. And basically that path, that will be an ordered list of segments. In this case, we are using MPLS, so we will basically get an ordered list of MPLS labels back. At that moment, the PCC can say, right, I have a valid path for that particular tunnel. The tunnel can come up and start to forward traffic. Also, if we do use a controller, we can have the task of doing the bandwidth control by the controller. What would you configure on the head-end router where you have SRTE, so an SRTE tunnel, but you want the controller to do the path computation. Well, you would just have a tunnel as you would normally configure, but at the end of the path option, you would just specify the PCE keyword so that it's the controller that has the task of doing the path calculation and not the router. So basically here the router delegates the task of the path computation towards the controller. If anything changes in the meantime in the topology of the network, that will be signaled to the controller by OSPF or ISIS or BGP link state, and it's the task of the controller to make sure it tells the headend router that the path has changed. We call that delegation, so the task of calculating the path through the network is now done by the controller. You can configure that on the router either per tunnel or globally, and then the PCE will have the task of doing the path calculation for all the tunnels for that specific PCC or router. Hello and welcome to lesson 10. This is a short lesson where I explain how the quality of service information is propagated in an MPLS network, and I also explain the different modes on how the service provider can transport the quality of service information of the customer when transporting their traffic over the MPLS core. Let's have a look at MPLS and quality of service, and more specifically, we'll also have a look at the uniform, short pipe and pipe modes. Let's first have a recap of how quality of service works with IP packets. There are basically two ways to indicate the quality of service of an IP packet: marking it. First of all, the old way is just using the precedence bit. So in the type of service or TOS byte in the IP header, the first 3 bits indicate the quality of service. So we have 8 levels of quality of service. Later on, diffserv was defined. With diffserv, we really have 6 bits that we can use for quality of service. We call those bits the DSCP or diffserv code point. Now the quality of service we talk about is PHP or per hop behavior. We also call that differentiated costs. The really old way of doing quality of service is the integrated quality of service way, which meant we did an end-to-end kind of quality of service. And that was done with RCP. So we needed a signaling protocol end-to-end to signal the quality of service or cost end-to-end. So the oldest of the two ways is using IP precedence. Basically, if we look at the TOS byte, we'll be using the first 3 bits for quality of service. And here you can see what we end up with. If all the bits are set to 0, then we have the routine quality of service. Or if all of them are set to 1, we have network control. In total, we have 8 levels of quality of service. With the diffserv way, which is a newer way to do quality of service with IP packets, we're actually using the first 6 bits in the TOS byte. So we have 6 bits, we call them the DSCP bits. There is an RFC 2597, that describes specific quality of service values. However, we have 6 bits here. With the precedence bits, we only had 3 bits. Now if we look at an MPLS packet, we only have 3 bits, the experimental bits or traffic class bits, to do quality of service. Here we have 6 bits, so that poses an issue. Now, to copy the quality of service level from an IP packet, we can only copy 3 bits, of course. With the precedence bits, it's easy, we only have 3 bits. With the diffserv bits, we now have 6 bits. The way we copy the quality of service is we are just going to take the first 3 bits of the diffserv value and copy that value into the experimental bits field of the MPLS labels. What is the default behavior for quality of service with MPLS? So here are 2 important rules. The default behavior is to copy the experimental bits to any label that is swapped or pushed when forwarding the MPLS packet. We do not copy the MPLS experimental bits value down to the newly exposed MPLS label if we are popping off. a label. However, if that's something you want, it can be done with CLI. So here's the default forwarding behavior for quality of service when we are forwarding MPLS packets. Let's have a look at all the possibilities. If an LSR receives an IP packet and the DSCP quality of service is set to 5, then this value will be copied into the experimental bits of the pushed label. The same occurs if we are actually pushing 2 labels or more. If the LSR is doing a label swap, then we are going to copy the experimental bits value into the swapped label, but also in any pushed label. If we just do a swap, then we copy the value of the experimental bits of the top label into the new top label. If we are disposing labels, so if we are removing or popping off a label, then we do not copy down the experimental bits value into the newly exposed label when forwarding the packet further onwards. Also, when we are completely removing the label stack, and hence we end up with an IP packet being forwarded, then we do not copy down the value of the experimental bits into the toss byte of the IP header. Having said that, we can have 3 kinds of tunneling modes. By tunneling, we mean transparently get the quality of service across the MPLS cloud. Typically, an MPLS cloud from a service provider will be used to carry customer traffic across. That customer traffic, usually IP traffic, will have a certain quality of service attached to it. The service provider most likely would like to carry that quality of service across and keep it. But while transporting that packet through the MPLS cloud, that quality of service of the packet is always the experimental bits value inside the top label and only the top label. The LSR will never look at labels at position 2, 3 and so on. At the egress LSR, because we are typically popping off labels there, the router actually has a choice. It can either use the experimental bits value or maybe the IP precedence or diffserv value for its quality of service behavior or the per hop behavior. In the end, we will end up with 3 tunneling modes. And the real difference between these 3 modes is what happens at the egress LSR. The first one of these modes is uniform mode. So let's have a look at the example where the MPLS provider carries IP traffic of a customer across its network. At the ingress side, by default, we'll copy the precedence or diffserv value of the IP packet and put it as an experimental bits value in all the pushed labels. At any intermediate router, the service provider can change the quality of service of the packet. That means change the experimental bits value only inside the top label. When we pop off a label in the MPLS cloud, that experimental bits value will be copied down to the newly exposed label. And even at the egress LSR, the experimental bits value gets copied down into the IP header as the IP quality of service level. This is not the default behavior. Also here, at the penultimate hop router, this is not the default behavior. If the service provider would like to do uniform mode, it would have to have CLI in place to make sure that this is the behavior that is wanted. In the end here with uniform mode, the idea is to have a uniform treatment of the packets end to end. So if at any place the quality of service of the packet changes, which is what happened here, it changed from 5 to 4, this change will be propagated into the labeled packets, but also into the IP header. So here in this case, the quality of service of the customer traffic, so of the IP traffic, has been changed. The second mode is the short pipe mode. Here at the ingress router, typically it is not necessarily needed to copy the IP precedence or diffserv quality of service into the label stack. But it might be. However, typically the service provider probably wants to set the quality of service of the labeled packet to a specific value that is done by configuration on the ingress LSR. Then the packet is forwarded through the network. At the egress LSR, the experimental bits value, which is the quality of service level of the labeled packet, is not copied down into the IP header. So in this case, we preserve the quality of service of the customer packet, the IP packet. Also important is to note that at the egress LSR, the classification and marking of the packet, so the quality of service treatment of the packet, is done based on the IP diffserv of OR precedence value, not the labeled one. So here at the egress LSR, we have IP per hop behavior. And the third mode and the final mode is the pipe mode. It's very similar to the short pipe mode. At the ingress LSR, the LSR can set the quality of service level of the labeled packet to any value. The packet will be forwarded. At the egress side, just like with the short pipe mode, the experimental bits value does not get copied down into the IP header. That's the same as with the short pipe mode. However, the difference is the behavior of the quality of service at router D, the egress LSR. Here, the quality of service behavior will be based on the experimental bits value and not whatever quality of service we have in the IP header. So here at the egress LSR, the classification, marking and so on is done on the experimental bits value of the top label. So here we have MPLS per hop behavior. Remember the explicit null label? We can use that to reverse the penultimate hop popping behavior. That means that when router D, the egress LSR, advertises the explicit null label, label value 0 instead of 3, implicit null, that we will always have at router D a labeled packet coming in. So the label value is 0, so it doesn't hold any forwarding vector or information, but we will use the experimental bits of the explicit null label. At that point, router D can do its classification and marking, any quality of service treatment, based on the experimental bits that we have in the explicit null label. Because now we still have a label. With penultimate hop popping, we would not have had a label when the packet arrived at router D. And here again is the command to enable the explicit null advertisement on router D. One more thing about the CLI. In Cisco iOS, we can use MQC to configure quality of service. And we can also use this CLI to modify the quality of service used by MPLS. There are basically two commands. We can use the command set MPLS experimental in position and then put a value from 0 to 7. This command will be put in a policy map. This command will set an experimental bits value to whatever value you have configured here on all the pushed labels. So you would do that on an ingress LSR. The next command, set MPLS experimental topmost, and again you can specify a value between 0 and 7, will set a particular experimental bits value, but only in the top label. So typically this is used when we are doing label swapping. So this will happen on an intermediate LSR. Hello and welcome to lesson 11. This is the final lesson and also another short one where I explain briefly how to use ping and traceroute to troubleshoot forwarding issues in MPLS networks. I'll actually first explain how traceroute works in an IP network and then highlight the differences with the behavior in an MPLS network. Let's have a look at troubleshooting MPLS networks and more precisely ping and traceroute. First of all, troubleshooting. If you really want to know how to do troubleshooting, you must know the theory. And I hope that so far you have learned a lot with this course on MPLS and specifically on all the theory. So that knowledge is something that we are going to use. Second, you need to verify the LSP, and I think I've given you a lot of information, a lot of commands, a lot of output that you can check to verify that the LSP end-to-end is working. You can do a ping, that's ping as you know it, but the output from ping is either, yes, it's working, 100% successful, or it's not working. Trace routing is a much better tool to see if it's working or not, and if it is failing, where it is failing. First, a word on trace routing in the IP world. Basically, what happens when you do a trace route? When you do a trace route for IP, we are sending out probes, and each time we are sending out a probe with an increasing TTL. So the first probe has a TTL of 1, then the second one a TTL of 2, and so on, until the destination replies. These probes can be UDP or ICMP packets. At Cisco, typically, they will be UDP packets. But to make sure that the remote end, the destination, doesn't send those packets to an existing port, we will use a UDP port, which is usually not in use. This is a port higher than 30,000. So as I mentioned, we will send out probes. The first probe will have a TTL of 1, the second probe a TTL of 2, and so on. Each time a packet hits a router, the TTL is examined. If the TTL expires, so it reaches 0, that router will send back an ICMP error message. This one is the code 11/0, meaning the TTL has expired in transit. Eventually, after some probes, the probe will hit the destination router, the one you are trace routing to. That router says, well, that packet is destined for me, but I don't have that UDP port assigned. So that router, the destination router, will send an ICMP message 3/3 back, saying the port is unreachable. Let's have a closer look at trace routing in the IP world. We have a network here of 6 routers, and we are trace routing from router A to router F. To be more precise, the destination IP address is 10.1.2.1, which is the loopback at router F. The first probe going out, it's a UDP packet, but the TTL is set to 1. So the TTL already expires at router B. What does router B do? It simply replies with an ICMP message saying TTL exceeded. And this is sent back to the router who sent the original UDP packet. So they send back to the IP address 10.1.1.1, which was the source IP address of the original packet. That was probe 1, now probe 2. The packet now leaves the router A with a TTL value of 2. It is forwarded by router B, TTL is lowered by 1, TTL expires at router C. C is now the one sending the ICMP error message back to router A. And this goes on, so we'll have a probe 3 and 4. Let's have a look now at probe 5, the final one. So the packet leaves at router A with a TTL 5, arrives at F, the TTL has not expired yet, it's still bigger than 0. But now router F says, UDP port 35,678, I don't know that one. It's not assigned to a particular protocol. So router F will now generate this error message saying port is unreachable and send it back to the source of the original packet, to router A. So now the trace route completes. And this is the output that we will see at router A. We just see the IP address of every router. To be more precise, this is the IP address each time at the incoming interface of the UDP packet. Here are the rules for MPLS TTL propagation. The TTL is always copied from the IP header TTL field to all the labels that are pushed in the label stack at the ingress LSR. At an intermediate LSR, we have label swapping. There, the TTL is copied after being lowered by 1 from the ingress label to the newly swapped label. At the egress LSR, the top label is popped off. The TTL, -1 of course, is copied from the incoming top label to the outgoing top label, the newly exposed label. In a push operation, that's also at ingress LSR, the TTL value is copied from the top label to the swapped and all the pushed labels, of course after subtracting 1. And finally, at the egress LSR, when the packet becomes unlabeled, so the outgoing packet is an IP packet, the TTL is copied from the incoming top label, subtract 1, and that value is copied into the IP header, except if the MPLS TTL value is bigger than the IP TTL value. And this is to avoid a possible routing loop if that packet would be forwarded again to the ingress LSR. In that case, if we would not follow this rule, the packet could be looping forever without having any kind of TTL expiry. So what about if the TTL expires? Well, an LSR, when it sees that the TTL at the top label expired, will also generate an ICMP 11/0 message, meaning that router will need to strip off all the labels, look at the IP header, generate this ICMP error message, and send the message back. First, ICMP has been enhanced so that it can carry also the extra MPLS information, the labels, the complete label stack. This is nice, because when you do a trace route, the packets coming back, the error messages, are ICMP error messages. And now they will hold the label stack. So when you do a trace route, you will not only see the IP addresses of every hop that the packet went over, but also the MPLS labels. But there is another issue. In some cases, there can be many of these cases. It could be that at the place where we have the TTL expiry at the top label, that router would not be able to send the error message directly back to the source. Why? Well, when it tries to do a lookup of the source IP address in its routing table, it might not find that route. And this typically happens in MPLS VPN networks. Because if you have a TTL expiry in the top label at a P router, the P router cannot look up the source IP address, because the source IP address is somewhere inside the VPN, and P routers do not have any routing knowledge of VPNs. Let's have a look now at trace routing in MPLS VPN, and we'll start straight off with probe 2. We have an MPLS network here, so at the edge we have PE routers and we have CE customer routers inside a VPN. Now we will have two labels. We will have an IGP label, the top label, and a VPN label, the bottom label. So when you do a trace route from a CE router, so inside the VPN, again a UDP packet is sent off, it's probe 2, so the TTL is 2. The ingress LSR puts two labels on top of the packet and forwards the labeled packet into the MPLS cloud. Now, the TTL at the top label has expired at P1 router. What does that router do? It removes the labels, looks at the IP header, generates the ICMP error message saying that the TTL has expired, and then it does not send the error message straight back to CE1. Because if it does a lookup for the source IP address, which is here 10.1.1.1, P1 has no knowledge of this route in its routing table, because this IP address is only known inside the VPN, not in the global context of the service provider. We can solve this with a trick. P1 will actually use the original LSP to forward the packet. So it will put two labels back on top of the ICMP error message and forward that packet onwards. Now the TTL in the labels is 255, and the idea is here that this ICMP error message is forwarded forward onto the original LSP, hoping that it will hit a router, like a PE router or a CE router, that can do an IP lookup for this particular source IP address, 10.1.2.1, which is the originator of the original packet, somewhere in the VPN. In the end, this probe will hit PE2 or CE2. That router can do a lookup of the destination IP address and forward the ICMP message back to where you have performed the trace route command. Now you might say, why does PE2 not do an IP lookup and forward the ICMP error message straight back? Well, if you look here in the LFIP of PE2, at the entry for this particular label, you will see that the outgoing label says no label. That means that when PE2 receives this packet, it will do a lookup, strip off the label and forward the packet. It will not do an IP lookup. The first router that does an IP lookup on the packet is the router C2. So here's the output. If you were doing a trace route on router C1 for the loopback of C2, this would be the output you have gotten. Two remarks. we don't see MPLS labels here. That's because we did not enable MPLS forwarding at CE1, so it will not show any label stack information. Second, of the egress PE2, you will see the IP address 10.1.3.2 in the trace route. This is not the IP address of the incoming interface, but the IP address of a VRF interface. Why do we do that? We did it on purpose. It is because in the trace route, we want to show the IP addresses inside the VRF context and not the global context as much as possible. So on a PE router, typically the IP address returned will be an IP address from inside the VPN context. Now here's another take at probe 2. We are doing a trace route again, but now the destination IP address is 10.1.3.1, which is the connected prefix here between PE2 and CE2. Packet expires at P1. Again, ICMP error message is generated and forwarded onwards. Now PE2 does a lookup for this particular label in its LFIP, and it sees as outgoing label aggregate, not no label, as in the previous slide. Why? Well, this prefix is connected to this router. So when this router needs to forward packets destined for that prefix, it will actually need to figure out, well, is it .2 or .1 of that prefix? So is the packet for me or for the remote end at the link? How can PE2 figure that out? Well, it will need to do an IP lookup and say, okay, the packet is destined to .2, it's for me, or destined for .1, it's for the CE2 router at the remote end of the link. It can only do that if it does an IP lookup. So that's why in the LFIP of PE2, we have an outgoing label which says aggregate. And this entry in the LFIP, this outgoing label, forces PE to do an IP lookup after the label lookup. Because it does an IP lookup, it will do the IP lookup, by the way, in the correct VRF table. It finds out the correct VRF table by looking at the label that was on top of the packet, and then will send the packet straight back to CE1. So here, when you are trace routing to a directly connected IP address on P2 or C2, or the link in between, the trace route is one hop shorter. Here is an interesting command, no MPLS TTL propagation. What does it do? Well, we have a command, no MPLS IP propagate TTL. As the command suggests, it stops the propagation of the IP TTL into the MPLS TTL, at the ingress LSR of course. So if you configure this command at the ingress LSR, whatever the TTL value is in the IP header, when the ingress LSR pushes MPLS labels, the MPLS TTL value at every label will be 255. What's the point? Well, if the MPLS TTL value is 255, those packets will never see a TTL expiry at the P routers. So when you do a trace route from a CE router to a remote CE router, for example, you will never see the IP addresses of the intermediate P routers. So the service provider can use this command to hide the topology of its backbone from a customer doing trace routing. This command basically stops the copying of the IP TTL to the MPLS TTL in every label for packets generated from the PE router or going through the PE router. There is a variation, no MPLS IP propagate TTL forwarded. With this command, you only stop the propagation for packets going through the PE or ingress router. Meaning, if you do a trace route from the ingress PE router, you would still see the complete topology of the MPLS VPN network. And typically, the people doing trace route from the PE router are people from the service provider. But if you do a trace route from the CE router, the packet traverses through the ingress LSR router, and then you don't see the P routers showing up in the trace route output. Here's an example of the usage of this command. So on the ingress PE router, and that's the only place where this command takes effect, you configure no MPLS IP propagate TTL. We'll have a look at probe 2. Again, you do trace route from CE1 towards CE2. The packet is arriving at PE1. PE1 now puts two labels on top of the packet, it's MPLS VPN, but the TTL value in the labels is 255. Now the packet will be forwarded towards the egress side. There is no expiry of the MPLS TTL in between, so it reaches the destination, router C2. This one will generate the other error message saying port is unreachable, and this is sent back to the originator of the traceroute probes. So in the end, the traceroute output on C1 looks like this, and we only have 2 hops. The first one is the IP address on the incoming interface of PE1, the ingress LSR, and the second one is an IP address of the remote CE. You no longer see any P router IP address showing up in the traceroute. So this is how the service provider can hide its topology from a customer doing a traceroute from one VPN site to another.